On behalf of the Office for Outer Space Affairs, who is the host of this 7th IAA Planetary Defense Conference, together in collaboration with the European Space Agency, I would like to welcome you to day 2 of this conference. Displayed is the program for day 2, which will focus on discovery and characterization, but we will also hear some very interesting perspectives from the legal and policy point of view, as well as the disruption and deflection options. Yesterday, we touched on the first exercise, INJECT. So the hypothetical impact is still very broadly defined, below 5%. Same Page and Iowan gave their initial assessments. We had a really nice discussion on decision-making issues, also from the perspective of the United Nations, the Committee on the Peaceful Use of Outer Space. So we are ready for today. A couple of points from my side in terms of organization. We really appreciate all the session chairs and panelists to keep within the allocated time, so we can proceed with the program as scheduled. Also, there were some good feedbacks received yesterday in terms of Q&As. So we would kindly ask all the participants to pose their questions to panelists in the Q&A section. This is in the WebEx bottom right, next to the chat. So you're welcome to chat with the individual participants, but for Q&As, we would like to ask you to post your questions there. So from my side, that is all that I would have to convey to you today. So we look forward to a successful day. Thank you for your participation. I think currently we have 72 participants. We will brief you during the day on the number of participants joining, and looking forward to a successful day. Alex, over to you.
Thank you, Romana. And on behalf of the conference co-chairs, I would also like to welcome you to day 2. The theme of today is discovery. So, and of course, we have, as Romana mentioned, the continuation of the exercise session with some very interesting discussions today. A few add-ons to the logistics, what Romana said. So during the green zone, we will have polls again during the breaks, which will also show up on the right hand side in the menu on your screen. And we have, during all breaks throughout the day, Detlef Koschny was kind enough to set up a Zoom room. So he prepared some breakout rooms. I will provide the link in the chat. You're welcome to join there during the breaks, and there are several breakout rooms, and that is meant for socializing. So you can mingle, meet new people, talk to old friends, and see what's going on. Hopefully, you will come back on time for the sessions, but just like a regular conference, if you get stuck at a coffee in an interesting conversation, that's of course also a good outcome and part of any conference. So I will post that regularly during the breaks, so you know where to go. And so that is on Zoom, so it's in parallel to the WebEx. You don't have to leave the program. You can leave it running on the side, so you can also hear when the sessions continue. It might make sense to maybe check your video and audio settings, although most of that would be for the panelists more than for the participants, obviously. And with that, we have 10 minutes to go, and I'm not quite sure with what to fill those. So our first session is on near discovery. That is being chaired by Kelly Fast. I've seen she's already here.
Thank you, Alex, and good morning, good afternoon, good evening, everyone. As we get started, I want to recognize and thank my co-chair, Alan Harris of the US, who worked very hard with me on session planning, and he handled just about all of the notification and reminders. I'm very appreciative of his help. Our deal was that he would handle notifications and I would handle the WebEx. And thank you also to Luca Conversi for serving as a backup co-chair should difficulties arise, although he's a panelist in this session, so hopefully all will go well. And let's get started. The first requirement of all of the activities in planetary defense is the ability to discover NEOs. You cannot mitigate a threatening asteroid if you do not even know that it exists. And so we have two exciting parts to oral session 5, NEO discovery, right now and later today. And I also remind you to view the e-posters and e-lightning talks related to this NEO discovery session. And now for session 5A, NEO discovery, with our lineup of 5 oral presentations, and then all presenters will participate on a panel for questions and discussion during the remainder of the hour. Each speaker will have 7 minutes for their oral presentation with overhead, and I will warn at the 1 minute mark. And so let's get started. Our first speaker is Professor Boris Shustov of the Institute of Astronomy of the Russian Academy of Sciences, and he will be speaking on System of Observation of Daytime Asteroids, SODA. Professor Shustov.
Thanks a lot to organizers for giving me a floor at this very important and interesting conference. Next slide, please. Next slide, please. Let me first remind major lessons of Chelyabinsk event of February 15, year 2013. Decameter-sized NEOs can be hazardous. We need to be warned about possible collisions with such bodies. Nothing can be done to prevent collisions of decameter-sized NEO. Civil defense is the only way to mitigate. Warning is in proper time, some hours before the collision, is a major caution. As it clearly seen from the known bolide chart by NASA to the left, NEOs coming from day sky, yellow circles, are as numerous as night ones, blue circles. NEOs coming from a large part of day sky cannot be timely detected at a regular basis by any ground-based or near space-based observational facilities. One needs a telescope located far from the Earth. After the Chelyabinsk event, there appeared some ideas. David Denham and colleagues in 2013 first suggested to put a 1-meter telescope in orbit around L1 point in the Sun-Earth system. The telescope was assumed to survey an annual region of the celestial sphere around the Earth once per day. Later, we proposed a variant of spacecraft with smaller 30-centimeter aperture telescopes, providing much shorter observational duty cycle. We named this SODA, System of Observation of Daytime Asteroids. Here, we present an optimized variant of SODA. Next slide, please. Major mission objectives are to detect all potentially dangerous bodies larger than 10 meters approaching from the Sun, to characterize object of interest, it is accurately determine orbit, approach velocity, and mass of the object. In a collisional case, to determine atmospheric entry point with highest possible accuracy and to ensure warning time of no less than 4 hours. Very general concept features are: it should be a low-cost mission. A variant of 2 spacecraft is optimal, 1 spacecraft still to be functional. Additional scientific payload, for instance, instruments for observation of the Sun, space weather monitoring, etc., is welcome. A global network of ground stations ensuring 24/7 regime of operation is required. Next slide, please. The SODA telescopes are to observe in a conic barrier mode instead of all-sky survey. Barrier mode of detection significantly reduces requirements to survey rate, telescope's field of view, detector size, etc. In the optimal variant, 2 spacecraft should be well distributed in orbit around L1. Main advantages of 2 satellites option in compared to single one are increased accuracy of orbit determination due to possibility of triangulation method of observation, solution of problem of missing bodies flying close to the spacecraft at distance less than 400,000 kilometers, increased detection area, improved system reliability for redundancy, for instance. We consider two modes of operation on the SODA. The first one is a regular regime of detection of asteroids coming from the sun direction. The second, it is a target mode to accurately follow up the NEO of interest at least by one telescope. Next slide, please. At this slide, a general view of the spacecraft is presented. Each spacecraft will be equipped with 2 or more telescopes. 2 telescopes option is a minimal variant. 1 telescope is still useful, but some bodies will be missed. 3 telescopes option is an optimal variant. Next slide, please. Major feature of the SODA telescope is that this is a telescope with a pre-aperture slewing mirror. This technique becomes popular for small aperture spaceborne telescopes. We suggest to put a slewing mirror in front of each telescope for quick repointing. This makes possible very flexible and independent observational program for each telescope. Main parameters of the telescope are listed at the left panel. Note short 3.5 minutes duty cycle. This makes it possible to observe an object crossing the barrier for 6 times in average. It seems to be sufficient for calculation of the preliminary orbit. Regular power consumption is about 50 watts. We indicated a peak value. For more details, see poster by Shugarov et al. Next slide, please. 3 telescopes can potentially absorb a large area, and at least a third can be absorbed by 2 telescopes at the same time. Of course, this is in a schematic picture. In a regular regime, we absorb only a relatively narrow ring with a radius of about 45 degrees and a width of about 4 degrees. A central region of 10 degrees cannot be absorbed at all, as a special mask will screen the Earth light. Next slide, please. Let's briefly consider a possible scenario of Chelyabinsk event if SODA worked. Input of this simulation includes 2 SODA spacecraft options. Astrometric accuracy of single observation is 0.5 arcsecond. Observation of the body of interest will be performed permanently after the detection. After final observation, we expect to have an accuracy of atmospheric entry point at the level of tens of kilometers. Next slide, please. A combination of SODA and ground-based survey telescope, for instance, ATLAS, is a way to provide an efficient all-sky system of detection decameter-sized NEOs in proper time. Combined zone of detection of 10-meter body with a ground-based telescope limiting magnitude 19 and the SODA limiting magnitude 17 is shown at the chart. The signal-to-noise ratio is marked by color, green and blue isophotes with 3 units increment. Blue and pink dotted lines show signal-to-noise ratio equal 9, which seems to be sufficient for detection. Next slide, please.
1 minute.
To conclude, the only realistic way to timely detect most of daytime decameter-sized asteroid is to use a system of spaceborne telescopes located relatively far from the Earth. SODA is an example. Some years ago, we presented the SODA Phase A study. Improvements of optical elements were made since that. These include a new optical design of telescope, pre-aperture slewing mirror, and a new CMOS detector. It is a relatively low-cost project. It is designed with existing technologies. We applied these to Roscosmos. International collaboration with other ground-based or space-based projects focused on detection of 10-meter class NEOs is welcome. Thank you for your attention.
All right, thank you, Professor Shustov, and thank you to those putting questions in the chat. We will answer, panelists will answer those questions during the panel session at the end. And our next speaker is Dr. Seitaro Urakawa, Senior Researcher, the Japan Space Guard Association. He'll be speaking on development of asteroid detection application COIAS, or C-O-I-A-S, for the Subaru HSC data. Dr. Urakawa.
Thank you. Can you hear me?
Yes.
Okay. Hello, everyone. I'm Seitaro Urakawa. I'm a researcher of Japan Space Guard Association. We started to develop the asteroid detection application for Subaru telescope. So today I'd like to talk about the progress of this development application entitled Development of Asteroid Detection Application COIAS for the Subaru HSC data. Next, please. To begin with, I give the background in our study. Hyper Supreme Cam HSC is a super wide field camera mounted with a prime focus of 8.2 meters Subaru telescope. The field of view is 1.5 degree in diameter. The HSC was mainly used the Subaru Strategic Survey, SSP. SSP is a deep multiband survey of 1400 square degree of the sky. In addition to it, some ecliptic plane survey were also conducted without the SSP. And the SSP is mainly designed for gravity lens, supernova, and Milky Way galaxy. All the HSC data are archived and opened a year and a half later from the observation. But there is a problem. A large number of asteroids, including NEOs with diameter smaller than 300 meters, will be imaged in HSC archived data. But the coordinate and brightness of these asteroids were not reported effectively to the Minor Planet Center MPC. I think this reason was there was no useful application system which can conduct the detection, measuring coordinates, photometry, and reporting to the MPC for the asteroid. Next, please. So we decided to make COIAS. COIAS is an application system for detecting, measuring coordinates, photometry, and reporting to the MPC. COIAS is composed of our developed programs and the relevant system. Why COIAS? The name COIAS has double meaning. The first is let's try to discover asteroid, namely common impacting asteroid. The second name meaning is come from Japanese animation, Koi Suru Asteroid. Its abbreviated name is COIAS. The English title is Asteroid in Love. Please check this animation by Google. This animation is a story of a high school student who tried to discover asteroid. We have a plan to use COIAS for education. So we adapted this animation title for our application name, considering the educational and public relation effect. Next slide, please. This is a flowchart of COIAS system. Let me skip the detailed explain due to the time constraint, but I'd like to talk the key point. The key point is we adapted the visual inspection to distinguish between noise and asteroid. Next, we explain the reason. Next slide, please. Why do we use the visual inspection? The HS data were obtained under a variety of conditions, such as exposure time, filter, and survey area. Of course, the machine learning algorithm has the potential to increase detection efficiency in the future, but it is difficult to be applied for the variety of conditions in the current situation. The other reason is the educational effect by using graphical user interface. The visual inspection gives the citizens and students the delight of asteroid discovery, and it is expected to have a high educational effect. Next slide, please. So we made COIAS version 0 and ran the asteroid detection test. The test data were obtained on 26 January 2015. The survey area is a Jupiter-Trojan region that is located around the opposition on the ecliptic plane. The image were obtained the exposure time of 240 seconds using the G-band R-band filter. The same area was observed 5 times at the appropriate time interval. The candidate of moving object is defined as a source that is detected more than 4 times. Next slide, please. This is an example of COIAS. Please, next, back, please. Next, 2 times next, 2 times back, please. One more time, next. Back, back. Sorry. As you can see from this example, the right side, right hand signal is a moving object candidate. The left side is a noise. After that, we input the left side blank frame, the name of the personal designation number. After that, we put output button to conversion to the MPC format. Next, please. Okay, thank you. This is there's a result of a test result. We detect more than 4,000 unknown objects and 874 known objects from the area of 16 square degree. We can't estimate the accurate orbit due to the short observation arc. However, about 90% of objects are main belt asteroid candidate. From 7 to 8% is a Hungary group candidate, and from 2 to 3% objects are near Earth asteroid candidate. This figure shows the R-band magnitude. Asteroid up to, you can see from this figure about 24.2 magnitude have been detected validity, assuming the albedo of the 0.1 and the semi axis of 2.5 AU, the brightness of 24.2 magnitude roughly corresponds to 200 meters in diameter. Next slide, please.
1 minute.
Thank you. Okay. Summary and future work. We started to develop the asteroid detection application COIAS for several HSC data. However, COIAS is in an early phase of development. The detection of moving object takes about 50 minutes per 10% of the field of view. The visual inspection requires around the same time for the same area. Therefore, we cannot say that usability of the present GUI is user-friendly because some process run by command line interface. I have a good news. We launch a new effort to improve the usability of COIAS by collaborating with a private corporation. In parallel, we will continue to improve the programs and increase the efficiency of the automatic asteroid detection. Last, HSC archive data will continue to increase in the future. COIAS will contribute to the discovery of asteroids, including NEO. That's all. Thank you for your attention.
All right, thank you, Dr. Urakawa. Our next speaker is Dr. Fabrizio Bernardi, Project Manager of SpaceDIS, speaking on new NEODES tools for the EU-funded NEO-ROCKS project, observations, support, and priority lists. Dr. Bernardi.
Yeah, thanks, Kelly. Good morning. Next slide, please. So what I'm talking here is some tools developed under the framework of the NEO-ROCKS project. NEO-ROCKS stands for the Neo Rapid Observation, Characterization, and Key Simulations. It's an EU Commission-funded project. And if you want to have some insights, please see the enlightening talk of Elisabetta Dotto. Next, please. So what we developed for this specific project is something related to a key point. So the speed for the orbit characterization process from the discovery observations, the orbit assessment, the imminent impactor assessment, and then going back to the observers to have the follow-up observations that are needed for the orbit improvement. Next, please. So since a few years now, there is what is called the NEOScan, is a service that is providing the computations for the so-called imminent impactor. So objects recently discovered and on the NEO confirmation page of the Marine Planet Center, which are going to impact within the next 30 days or so. Next, please. And within this NEOScan tool, we have all other tools that are in support of the observers. And in particular, I want to focus here for this talk on the left side part. That is the observation prediction tool and that is providing the position in the sky of the object for a specific observatory. Next, please. And the output is, of course, the ephemerides, the position, the visual magnitude, and several other parameters, and in particular, the plot of the uncertainty related to this specific target. On the right side here, you can see that there are several menus which are plotting the same uncertainty, but with a different color code. Next, please. In particular, for example, you can have the plot that is related to the color code of the visual magnitude for a scene for this specific object. And in this case, for example, you have visual magnitudes ranging from 18.5 till 22.5. Here you have also the background stars taken from the Gaia database, and the user can set up his own field of view so that it can figure out how it can cover the region and how deep it can go for the exposure. Next, please. Other color code of the same uncertainty region are showing not only the visual magnitude as the upper right side, but also other parameters like the MOID prediction. Next, please. Or the key that is related to the uncertainty, to the likelihood that the object is in a position in this uncertainty region. Or next, please. Or maybe you can also have an idea of the classes that are representing this uncertainty region. In this case, for example, the red bar are representing the main belt solutions, while the yellow are the scattered objects, and the blue are the neo orbits. So if you detect the object in one part of this region, then you can also figure out if it is an NEO or a main belt. Next, please. But what is very important is that not only we are showing the visual magnitude range, but also if the object is an imminent impactor, we can show let's say the solutions that are leading to the impact. In this case, the observer can focus only on the impacting, let's say, region. If the uncertainty is too big, for example, and you can only observe the impacting region, then you can figure out if it is going to impact, then we can improve the orbit process, and then we can figure out when and where the object is going to impact. If it's not there, and if we lose the object, then of course we are not in danger, at least on a short time. Next, please. This is the NEO confirmation page priority list. So we are taking the objects in the NEO confirmation page of the Management Center, and we sorted them according to a priority that is determined by the sky uncertainty, the visual magnitude, and also the parameters like the solar elongation, the moon position, and the galactic latitude. Next, please. Together with this tool, we are also providing a new service that is called a new priority list. This is regarding not the NEO confirmation page objects, but the full NEOs in our database. So this is following an algorithm that was developed 20 years ago by the group of the Space Guard Central Node, and this priority list has now been migrated to the new coordination center of ESA. But after 20 years, we decided to review it and to improve it. So we started from that algorithm, and we are also including other parameters like the moon position and the galactic latitude, and of course some consideration about negative declinations where there are less telescope resources in the southern hemisphere. Next, please. Together with this priority list, we are also providing a customized mailing service. So the observer can send not only the email where he wants to receive these emails, but is providing its observatory code, the limiting magnitude of that specific telescope, and the declination range. So we are providing on a daily basis at some customized time a list of targets which are visible from that position. Next, please.
1 minute.
Yeah. This is the layout of the mini service, and of course, the observer can select the targets for its night. Next, please. This is the layout of the new priority list. Next, please. And this is the table with several parameters. Next. Here there is the long list of parameters. I don't want to talk too much about this, but all the fields are sortable. In particular, the right extension is sortable starting not from 0, but from the sum position. Next, please. And the priority list is computed after making an analysis of the ephemerides for the next 10,000 days. So we computed the visibility window, the present visibility window, and the future visibility window according to several observational parameters. And then also considering the present in the risk list, the MOID, and also the other parameters. Next, please. So now we have two priority lists, not only the general priority list that is going down to 22 in visual magnitude, but and the solar elongation down to 40 degrees, but we are also providing the so-called faint objects priority list, so for targets between 22 and 25, and solar elongation down to 30 degrees. So the priority list is tailored for the general observers, either amateur or professional, with telescopes less than a meter, let's say, while the faint object priority list is more tailored for big glasses like a meter class and above for telescopes. Next, I think I'm done. Thanks, and I'm available for any questions.
All right, thank you, Dr. Bernardi. Our next talk is Dr. Luca Conversi, ESA's ENEO Coordination Center Manager at ESA, on ESA's ENEO Coordination Center Observational Network.
Thanks, Kelly. Good morning and good evening, everybody. So yes, I will present the evolution of our observing network within the Planetary Defense Office of ESA. Next slide. So this was the situation back in 2019. You can see that we had some, most of our telescopes were located in Europe. Plus we had the collaborations, which is still ongoing with the VLT telescope in Chile and the telescopes in Korea. Next slide. So last year we added some telescopes in the Southern Hemisphere, namely one in Namibia, one in La Réunion, and another one in Australia. This is via collaboration via a Polish company, the Six Road company. Next slide. And this is the situation that it's, again, we are going to sign soon a contract with Six Roads that will give us access to telescopes in Asia, plus the LCO network in yellow. Unfortunately, this is I updated the slides, but these are not the latest version. But okay, I will comment on this. So what happens is we have a set of in the last year we observed mainly with our facilities that are located in Europe, as I said in the previous slides. So we are using a 1 meter telescope, which is in Tenerife, the optical ground station, and that it's mainly used for observations of follow-up observations, but also to perform some ENEO survey. And this is used between 3 and 4 nights every moon cycle. Then we have an 80 centimeter telescope in the south of Spain, which is used 100% for our purposes. And last year it's been used for 150 nights. And for example, with that, we do not only follow-up observations, but also light curves. So we collaborated a lot for the Apophis campaign. We also do comet observation, and from time to time, we also do some observations of ARTSATs. Then as another activity we do is to help funding observations from other observatories in Europe, like LET at Tautenburg. And also we participated, thanks to a previous collaboration with ISON, we participated to the I1 campaign on 1999 KW4. and as well as the Bepi Colombo flyby. And so this is a bit the summary of our current activities. Now I will move forward on what we are, what's coming next. So next slide. Okay, so this was here. Okay, and this is what I just said. So you could see here a summary basically of our activities and observations that's been done in the past. The numbers of new observation in the past 12 months. Next slide. Okay, so ESA has developed in the past years 2 testbed telescopes. One is located in the south of Spain, in the Madrid area in Spain, the Cebreros ground station. And the second one it's been deployed last March in La Silla in Chile. Next slide. So the deployment has been delayed due to COVID. It was expected to happen last year. And so we managed to install it, but unfortunately, again, due to the COVID situation, we didn't finish the commissioning phase. So the TBT is a 56 centimeter telescope with 2.5 by 2.5 degree field of view. And the main idea is that we are trying the software and the software and the survey design that then will be later used for the bigger project that we have, that's the FlyEye. Next slide. So here are the first light images. Just right now, ESA and ESO are coordinating a press release about this. As I said, the commissioning phase is not over. We still have to improve, for example, the alignment of the telescope, but still we get very nice results. So in a 2 minutes exposure, we were able to went down to 20.2 magnitude, and if we stack 5 of such images, so for a total of 10 minutes exposure, we were able to get down 21 magnitude. And on the right, you could see the large field of view that will be very useful for either doing a survey or eventually to try to recover NEO, for which the uncertainty is very large. Next slide. Okay, then the last part of my talk, I will briefly discuss the situation of the FlyEye. So the FlyEye is the first big ESA telescope dedicated to NEO survey. It's a 1 meter class telescope, and which we have very large field of view, 6.7 by 6.7 degrees. The particularity of this design is that the field of view is split into 16 different cameras. Of these 16, 7 have been already qualified, and 4 have been mounted on the telescope, and 3 have been pre-aligned, as I will show you later. And we hope to finalize all the procurement, all the procurement of cameras by end of June 2021. Next slide.
1 minute.
Okay. So these are the first tests that we ran last winter. The test has been run in Milan in the factory facility. Unfortunately, over there the seeing is not good enough to achieve the proper alignment. So the plan is to move by the end of the year in the south of Italy at an Italian Space Agency site in Matera, where we will perform the alignment of all the 16 cameras. And then next slide. And by 2022, we will start. We will move the FlyEye in its final location. This is on top of Monte Mufara in Sicily, where we just signed the loan agreement to build the observatory. And here you can see the final design of the observatory. Next slide. And so here I am just linking to some related activities, related presentations that you could find the PDC website. Thanks.
All right, thank you, Dr. Conversi. And our final talk of this session is Mr. Igor Molotov, General Director of the Small Innovation Enterprise KIAM Ballistic Service Limited. on asteroid survey and follow-up observations with small telescopes in framework of ISON network. Mr. Molotov. Let's see, do we have him on the line?
I'm not sure, Kelly.
You know, I don't see him as a presenter.
No, we sent him an email. Boris, would you maybe know how to best reach Mr. Molotov?
I just will try to call him. It's strange. Okay.
All right. In the meantime, then maybe we can take a few. Go ahead and take some questions.
Yeah, sure.
Let me see if some of the questions are on SODA and if Boris is occupied. I'll say that. Let's see. There was a question, since it was mentioned about citizen science projects, and if there were any other presentations on citizen science projects. Alex Carl answered that he's aware of Frank March's having an e-lightning talk, which is available online. That's the only one we're aware of, though I know some of the larger efforts coordinate with some citizen science activities. There was also a comment or question. A comment from Atlas, from Larry Deneau, about Fabrizio's talk, that Atlas will address two of Fabrizio's issues we observe in the galactic plane, and we will cover southern declinations. And Fabrizio commented that that'll be useful for improving orbits for targets difficult to observe by the general observers. So, and Fabrizio, Melissa Brooker has a question. Are there plans for the new priority list to be adopted by the ESA NEO SSA page, or will they continue with their current version of the lists?
Well, I'm not sure if this question is really for me, but in case later on we will see if ESA is interested to adopt it or not. Probably at least not in a short term, for sure.
All right, understood.
Okay, I guess that Mr. Molotov will be in a second. He didn't calculate properly the time. It's not summertime, but the ordinary time. Strange. Okay.
Understood. Thank you.
I can answer for some questions in the meantime.
Please. I know there was combining some questions. There was a question about whether putting SODA further away than L1, if that could be achieved somehow, and if that would be more useful. And then also, how do the planned capabilities of SODA compare to the planned capabilities of NEOSM or the NEO Surveyor?
So let me answer to Jan Timo. That's SODA. Of course, there are variants of the realization of SODA. We used the technologies, the existing technologies, very simple, very cheap. That's why, and no research and development stage. That's why this solar electric propulsion for the larger distance for SODA we didn't consider, but we can do this if will be that wish. The next question was that it was not question, it was comment from Rudolf Albrecht. He thinks that it will be the panic if we announce for 24 hours before the Chelyabinsk event. But it is, in fact, it is the most important question should be discussed issue at the PDC. How and when to inform people, I mean the population, the authorities, how and when to inform them about the coming process. It is very important issue. You could smile, but nevertheless, it is one of our goals here. Then the question compared to NEOCM. Of course, NEOCM is an ambitious project. It will be infrared telescope of an aperture of 0.5 or larger. That telescope, it will be much more powerful, but it will be much more expensive also. We think that with this cheap instrument, what we proposed, it is an optical instrument. We solve only some specific task. Specific task is to detect 10-meter or larger asteroids coming from the daytime, from the day sky. The NEOCM is a much more, how to say, that's a broad project. That's to discover all asteroids, all NEOs. That's why we could compare only that we will wish to nail them the full success. Of course, it will be a very exciting instrument. Then how much advance warning time would SODA provide as impactor for the Chelyabinsk? We calculated his 15 hours. It will be the largest warning time we have. So the comment that in such an application of pure position nostrum, it will consider amplified CCDs. Yes, of course, we consider the amplified CCDs or EM CCDs. Now that's what I thought about this CMOS, as Молотов is calling. Игорь, чего вы? Подключились?
Okay, we are waiting for Mr. Molotov to join. And if there are additional questions, feel free to put them in the chat.
He will be in a second, I mean this Molotov. So that's we'll consider various technologically mature detectors. Now we have the CMOS as effective, as efficient as AMCCD in a sense. They have some advantages, some disadvantages, but it's a matter of the not negotiation, but considering. So we are open for all what I told you, that we are open to all the comments,
Hello.
Suggestions.
My presentation is about asteroid investigation in framework of ISN network. Okay. Please, next slide.
Thank you, Mr. Molotov. I'll let you know when you have 1 minute remaining.
This image is demonstrate a brief description of the International Scientific Optical Network. Our project started in 2004 year as open international project developed to be an independent source of data about asteroids and space debris. Main observation topics: space debris, asteroids, gamma ray bars of the globe. A core of ISN network is 30 own telescope, mainly 40 centimeter aperture, installed in 18 observation points. Additional lot of telescope we involved based for scientific agreement and submitted scientific proposal. Next slide, please. This map is demonstrated our network. A different color is a different status of telescopes involved. Green is our own telescope. Red color is telescope of observatories partners of our project. A blue color telescope, which observation time of which is received based for submitting scientific proposal. Yellow color marked telescope participated in observation of asteroids. Next slide, please. This slide demonstrates the list of activities of the ISN project, list of observatories which cooperate in asteroids research. Also, we sometime worked jointly with European Space Agency in providing follow-up and photometry of observation of asteroids for UN YAVN project. Now we cooperate with Chinese asteroid team. 1 meter Schmidt telescope provide discovered new asteroids, and our network provide urgent follow-up discovered asteroids. With our network provide following list of observations. Dedicated asteroid survey is now stopped temporarily. As my idea to adjust survey method with small telescopes with big field of view. Next, our idea is discovering new near-Earth asteroids as byproduct of space debris observations. Also, we provide follow-up astrometric measurements of new near-Earth asteroids and provide asteroids photometry to obtain the like curves. Next slide, please. Is descriptions of our test asteroid survey. We have two telescope 40 centimeter, one in New Mexico, USA, a second in Siding Springs, Australia, and both survey were scheduled, controlled, and processed in Keldysh Institute of Applied Mathematics to adjust the technique and software to survey of asteroids. In good weather, both 40 telescope covered 900 square degree per night with limited magnitude 20.5 magnitude. During this survey, it was obtained more than 1 million astrometric positions. It was discovered 17 near-Earth asteroids, 8 comets, and 1,600 main belt asteroids. Next slide, please. This demonstrated is the idea to detect new asteroids during space debris survey observation. In our cooperation with Roscosmos, it were produced for 6 telescopes, 4 with 2 tube and 2 with 4 tube, which provide very large field of view. Example 9 for 14 degree. Which good night it provides the scanning geostationary ring, and as byproduct, sometime it discovered new near-Earth asteroids. But the problem, this telescope, this observatory for Roscosmos have not code, MPC code, and his precision is not, his accuracy is not enough for minor planet center. Therefore, we try to adjust urgent follow-up. This observatory detected asteroids, and our ISON project provide the urgent follow-up and send the data to minor MPC. Next slide, please. Is our new subsystem developed to provide urgent follow-up of near-Earth asteroids. Is includes the telescope of 40 to 50 centimeter class is listed, and an additional telescope which involved in our more large telescope involved in our photometry observation also participate in follow-up of asteroids. We have 2-year cooperation with European Space Agency for UN YAVN project, and now we provide follow-up by request from Chinese Near-Earth Object Survey Telescope. Last year and this year, we provide follow-up from also we provide follow-up from NEOCP down to 2021 magnitude. During this work, more than 1,000 near-Earth asteroids was observed, and 5,000 astrometric measurements were obtained. Next slide, please.
1 minute.
Is there some summary our photometry project? Lot of telescope, 10 telescope, up to 2.6 meter in научный, participate in regularly photometry observation campaign. All the 1 meter telescope in CMEs of Institute of Astronomy of Russia, 1 meter in Tinshan, 2 meter CEIS 2000 in Rozhen, Bulgaria, and Terskol in Russia also is Interskol Observatories, Institute of Astronomy of Russia, and a lot of some less telescope. Which year we provide observation of 50 to 70 near-Earth asteroids during in sum 250 night observation night, and idea to determine the physical properties of asteroids, rotation, size, shape, etc. Also, our data are involved in discovering of binary asteroids, and also it was first time discovered the influence of Yorp effect to binary asteroids. Next slide, please. Outlook. With involving small aperture telescope, it was obtained good result. Our future development is connected with new class telescope. Is also 40 centimeter telescope, but he have field of view 22 square degree. Is demonstrated the sky image obtained with this telescope, and also we have idea to apply to this to discovery of to detection of asteroids. Our new telescope 28 centimeter with field of view 6 for 6 degree. First will be installed in Mexico in this year. Thank you for your attention.
Thank you, Mr. Molotov, and appreciate your being able to switch gears very quickly and jump right into your talk. So thank you so much. I'm glad you were able to make it. And we have all of the speakers. We can continue the questions with the panel, and we can have questions in the chat. And also, if the speakers here have any questions for each other, you're welcome to do that. Dr. Urakawa, there's a question for you from Gonzalo Tancredi. The Japan Space Guard Association developed in the early 2000s an education software for asteroid detection, Asteroid Catcher, ASTCAT. Is this project a legacy of that one? Are you planning to have a similar approach?
Thanks. Comment to Gonzalo. Yeah, that's right. I'm very happy to know this ASTCAT. Yes, you're right. This is COIAS is a legacy of the asteroid catcher ASTCAT. My motivation is the same with this ASTCAT. Thanks.
And you're welcome to ask more questions in the chat. Dr. Urakawa, I have a question. You mentioned that the data didn't lend itself well to machine learning. Why was that? Because of different observing modes, or why did you think that that could not be applied?
Machine learning. Yes, I think that to use the machine learning, but and some of my co-researchers try to adapt to the machine learning, but it is very difficult to, because as you can say, as I said, the HSC data was obtained very variety of the condition, imaged variety of conditions. So in the future, I hope to adapt to the machine learning, but in this current situation, I think it is very difficult.
Thank you. Are there any questions on the panel here of the speakers for each other?
Hi, Kelly. I have a question. My name's Stephen Lowry.
Yes, please, go ahead.
And this question is for Igor. I'm just wondering how many NEAs you're following for Yorp and BYorp, and of those NEAs, have you made any positive detections so far?
Excuse me, please repeat. How many?
How many asteroids are you following for Yorp and BYorp?
This work is we participate in investigation of Czech team, and it's my understanding, using our data, our colleagues discovered already 7 binary asteroids.
Yeah.
Not exactly is all the asteroids of mine belts.
No, Igor, it is a question about how many YORP asteroids
How
were
many YORP?
investigated
Sorry.
for YORP.
Thank you very much. It was already discovered 8 asteroids with YORP effect.
Okay, thank you very much, Igor.
Thank you. Are there any other questions or comments?
Hello, this is Petr Pravec. Maybe a comment to what Igor said about your targets they have been observing for our project in the Czech Republic. We have, as Igor said, data for 8 positive YORP detections have been published in the past years, and a few more are in works. So, Stephen, if you are interested about that, perhaps contact me offline by email, or maybe David Vokrolitsky could answer your question as well. So, if you are interested in some objects we have been observing and which we are going to publish, just contact me offline. Thank you.
Okay, thank you, Peter.
Yuri Kruglы wrote more than 10 asteroids with YORP effect.
Yeah, we have a few more in works that are going to be.
Thank you very much for your comments.
Yeah.
All right, any other questions or comments? I don't see any more in the question list here.
There was one for me, but I answered. There was Milos asking if we were planning to have an API for the priority list, but this is not on a short time. In case people can download the ASCII version of the same list, that may be useful as well.
Oh, thank you. Thanks for catching that. I didn't see that. Thank you for sharing. Any other questions or comments for the panel? I will mention at the end of this session that there will be a social breakout room as yesterday, and I believe the link for that will appear in the chat at the close of this session. If you would like to get to, in fact, there it is in the chat, if you would like to informally get to chat among yourselves, and since we're in this situation where we can't see each other in the hallway after the session, but and with so many people involved, it has to be very structured, but you can have some unstructured conversation there. So if there are no further questions or comments, I'd like to thank the speakers for today's session, and a reminder that later today there will also be the second part of the NEO Discovery oral session, and please also do browse the e-posters and the e-lightning talks that are related to the NEO Discovery session. And thank you again to our speakers and to Alan Harris and Luca Conversi for serving as my co-chairs. And I will turn it back over to Romano or Alex as we go toward the break.
And let me, on behalf of the speakers, to thank Kelly for this nice convening this session. Thanks.
Thank you.
Thanks a lot.
First talk is going to be by Dr. Petr Pravec, leading scientist at Astronomical Institute of the Academy of Sciences of Czech Republic. And his talk is going to be on photometric observations of the unrelaxed binary near-Earth asteroid 35107 1999 BH in support of the NASA Janus space mission, the detection of the spin-orbit interaction. So if Peter is ready.
Yes.
It's all yours. Thanks.
Thank you, Agata. Hello, everybody. It's great to be here. I'm going to present some of our results for one very interesting binary near-Earth asteroid, which is a planned target for the prepared NASA Janus space mission. I have several co-authors from as many as 5 institutes. Of course, me and my colleagues from ONGEOF and our American colleagues from the Janus mission team. So I would like just to point out at the beginning that while our interest is primarily in scientific understanding of binaries, of course, binaries are also important also for planetary defense, because obviously it would be very important constraint if you had to deflect a binary asteroid. So knowing them, understanding them is important. Next slide, please. So what our target is, the nearest asteroid 1991 VH was discovered in November 91 by Rob McNaught from Siding Spring from Australia. And a few years later, in 1997, it had a relatively favorable apparition for photometry. And we used then our small 65 centimeter telescope here from ONGEOF to take data over a little bit more than 1 month. And we found that the asteroid showed mutual events. That is eclipses and occultations between components of the system. So we found that it was a binary system. So the asteroid has a satellite, and we measured some basic parameters of the binary system, such as primary rotation period, orbital period, size ratio, secondary to primary size ratio, and same major axis. And we also estimated that the mutual orbit is not circular. It has non-zero eccentricity, which was quite unusual. The data in the plot are for the occultation light curve, for the mutual event light curve. It was relatively noisy data, but the events were clearly detected, and we were able to derive some basic parameters. Next slide, please. Then we took follow-up. Then we took follow-up observations in another relatively favorable apparitions in 2003 and 2008. And what was most surprising was that we found that the rotation of the secondary was non-synchronous. Its period was about 12.8 hours, much shorter than its orbital period, which is very unusual, because it's relatively rare among binary asteroids. We have also constrained or refined other parameters in the plot there on the lower right side. You can see the light curve decomposition. I wouldn't go into these technical details, but the data we obtained there were a little bit better than the discovery data from 97. So we were able to find the non-synchronous rotation. And additional data taken into 2007 showed that the secondary period was not the same as in 2003, so there was a first hint on that the secondary spin period is not constant. So we have already seen there that the 1991 VH is a unique unrelaxed asteroid binary system. Very interesting. The next slide, please. As such, it was selected by our American colleagues as a target for the prepared NASA Janus space mission. The mission will fly by two binary asteroids. One is our 99 VH and the other is 1996 FG3, which is an ordinary relaxed binary asteroid system. The JANA spacecraft will launch in the next year, and it will, following a 4-year cruise, it will fly by the two binaries in 2026. Next slide, please. So being motivated by the selection of the binary asteroid as a target of the JANA's mission, we took advantage of that it had another favorable operation last year, and we gave it very extensive observations. We gave it substantial fraction of our nights that we have available on our asteroid photometry projects on 1.5 meter telescope on LaCie, and our American colleagues contributed with 9 nights from Spacewatch telescope and 3 nights from the 2.2 University of Hawaii telescope from January to March last year. As you can see in the picture, the data are of very high quality. The scatter of the data is very low. The accuracy was about 10 millimagnitudes, which was about 2 or 3 times better than in the discovery and earlier follow-up observations. And the data, well, the picture shows just a small sample of the data. We have obtained many more data, but it would be several slides to present them, so I'm not going to do it. But I would just like to say that we found that both the secondary spin period and the orbit period changed again since the previous apparition. So we have seen some very interesting evolution. Next slide, please. We have also looked, tried to model the mutual orbit over all the 4 observed apparitions. The basic model with constant orbit pole can't explain the observations. In the plot.
30 seconds left. Sorry.
Okay. Okay. So maybe I will skip this. Just say that the orbit is inclined and precessing. Next slide, please. We have found the changing secondary and orbit periods, and they changed by about 1 or 2 hours for the secondary period and by about 0.2 hours for the orbit period, and they appear correlated. Next slide, please. We have looked into the energy budget, and we found that the model, assuming that there is an exchange of energy between the secondary rotation and orbital motion, can explain the observed data. So it suggests that there is present a spin-orbit interaction. Next slide, please.
Yeah, we run out of time.
Okay. Just last
sentence.
If you can wait. So we are going to we are modeling it with the general use binary asteroid simulator. Next slide, please. And this is one of the results that both the orbit period and secondary period change in correlation. And so this appears to confirm that there is indeed a spin-orbit interaction in the binary asteroid. And my final slide, please, is just a summary that this asteroid is in an unrelaxed state, and there appears to be spin-orbit interaction, and we are going to publish it in a paper later this year. Thank you.
Yeah, thank you very much, Pet. Next speaker is Dr. Julia de Leon, a researcher at the Institute de Astrofísica de Canarias, and she's going to be talking about characterization of NEAs in the frame of NHATS program using the 10.4 meter Grand Telescope U Canarias. So, Julia.
Okay, thank you. I hope you can hear me well.
Yep.
Okay, thanks very much. Yes, as you said, I'm going to present very preliminary results of our ongoing observational survey to obtain visible reflectance spectra of NIAS using the 10.4 meter Gran Telescopio Canarias in support of the NASA NHATS program. Of course, this work has been done with all the co-authors listed here. Next slide, please. So as you all well know, the NHATS stands for NASA Near Earth Object Human Space Flight Accessible Target Study. It's quite a long name. And it was initiated in September 2010 with the main aim of identifying any known near Earth object, in particular near Earth asteroids, that might be accessible by future human spaceflight missions. The NHATS team identifies high priority targets and sends alerts, so via email mainly, to the observing community requesting observations. So in particular, newly discovered NIAS are typically best observed in the following nights after the apparition, when they are brightest and closest to the Earth. And this is particularly true for those that are small in the meter scale. And in this way, apart from a rapid response, we also need to use large aperture facilities for this kind of follow-up observations. Next slide, please. So, as large aperture telescopes are best suited for this task, we are currently using the largest one, sorry, which is the 10.4 meter Gran Telescopio Canarias, or GTC, that is located at the El Roque de los Muchachos Observatory in the island of La Palma, in the Canary Islands, and is managed by, the observatory is managed by the Instituto de Astrofísica de Canarias, the institution where I work. And we started this observational program back in 2014. It was interrupted after 3 semesters or so due to several reasons. And we resumed it in 2019. I'm sorry, I'm taking some water because... Oh, man, thanks. So the program is currently ongoing. And for the observations, we use the OSIRIS camera spectrograph that is equipped with 2 CCD detectors, each of them with 2K by 4K. And we use the longest lead spectroscopic mode with a low resolution grism. And this provides a dispersion about 10 Armstrong per pixel and covers wavelength range from about 0.5 to 0.9 microns. Next slide, please. So here you can see just a few examples of asteroids observed with the GTC. The plot shows the asteroid spectra in black, normalized to unity at 0.55 microns, and its taxonomic classification overplot in color. We basically use the visible reflectance spectra of the asteroids to obtain their taxonomical classification, which is a way of inferring somehow its composition. We do this by a simple curve matching procedure that is already implemented in the M4AST online tool, which was developed and is maintained by our colleague Marcel Popescu. And I just take the chance to invite you to have a look at his e-lighting talk on characterization using visible spectrophotometry. And for this classification, we use the classes, the taxons defined in the Bas-de-Meo taxonomy, the Bas-de-Meo 2019, the Meo 2019 et al. Paper. Next slide, please. So here you have a table with some observational information, as well as some physical properties of part of the asteroids that we have observed. The majority of the targets were observed when they had an apparent visual magnitude between 19 and 21, very close to their discovery. For an example, on our fast response, look the case of asteroid 2019 WV, that was observed only 3 nights after it was first detected. And also for most of the targets, we don't have any albedo measurement, so we To infer the diameter, we use the mu-wise average of beetle measurements for the corresponding taxonomical class and their absolute magnitude. And then in this way, we infer the asteroid diameter. And as you can see here, the targets are, most of them are on the meter scale, and some of them are very, very fast rotators. Next slide, please. So this slide shows our preliminary results, summary of our preliminary results. So far, we have analyzed a total of 24 asteroids in the frame of the NHATS program. There are about 5 that with data that has not been reduced. We didn't have time to add it for this presentation. And in this pie chart, we have we present the taxonomical classifications we have found. And for the sake of simplicity, we have grouped together using green colors all the asteroids that are rocky asteroids. So those that are in the S complex, which are bright and rocky asteroids composed of anhydrous silicates, basically, and R asteroids, that's an N-member class, but still it corresponds to rocky objects, and also XE types class, which is associated to enstatites, and that's a magnesium silicate, so also rocky asteroids, okay? And on the other side, we have separated and grouped in blue-violet colors those having primitive taxonomies. So those in the C complex, so dark asteroids, rich in carbon compounds, organics, hydrated silicates. And the red slope asteroids, the T and D types, and also the XC types. So we find a slightly larger fraction of rocky taxonomies, about 59%. Of primitive classes, about 59%, compared to the fraction of rocky taxonomies, which is about 41. And this is very interesting because one would expect the opposite due to clear observational bias that favor bright targets. And we also have identified 2 D types and 3 T types, which are very interesting targets because they are found mainly in the outer belt and Trojans, and also in cometary nuclei. And there is a certain fraction of near asteroids. Yeah, I'm about to finish.
We are slowly running out of time. We have 30 seconds left.
So, as I was mentioned, if you see the histogram above, most of the asteroids are very small. They lie in the size range between 20 and 60 meters, with the 83% of the sample being smaller than 100 meters. And this is something that you can only achieve using large aperture telescopes. It is hard to say something regarding the size distribution within the classes because our sample is quite small, but in principle, we see no clear trends or any size preference within the classes. So next slide, please. I leave you with the summary of our conclusions. And of course, just keep in mind that these are only preliminary results and our sample is very, very small for the moment. Thank you very much.
Thank you very much. And our next speaker is Dr. Marco Fenucci, early stage researcher at the University of Belgrade. He's going to be talking about the low thermal conductivity of the superfast rotator 4999998 2011 PT.
Oh, sorry, I was not muted, sorry.
That's okay.
Thank you,
There's
Agatha.
a lot of lines there. It's all yours, thank you.
Can you hear me? Okay, thank you. Hello everyone, I'm Marco Fenucci and I'm gonna talk about the thermal properties of this NEO 2011 PT. And before starting, I'd like to acknowledge the other co-authors, which are Bojan Novakovic, David Vokorovitsky, and Robert Verk. So next slide, please. So I want to start with some motivation for this work. And it is known that asteroids smaller than 100 meters in diameter can rotate very fast, as you can see here in the plot on the right. And they can reach also rotation periods of few minutes. And there is general belief that these objects are monolithic objects because otherwise a rubble pile structure will not survive to such fast rotation. Also, they're supposed to be rocky objects because an eventual material lying on the surface will be expelled in the outer space, by effect of the fast rotation, and therefore they are supposed to have a high thermal inertia. In turn, a high thermal inertia makes the Yarkovsky effect less effective. However, recent measurements of the Yarkovsky effect performed on large data sets of asteroids by the Elvinian cohorts and Greenbergen cohorts have found some very small asteroids with a very fast Yarkovsky drift. So there's something going on. Next slide, please. So to understand better what's happening, we took into account the example of this NEO 2011 PT. We don't know much about it. We know that it is an Amor asteroid and it is very faint because its absolute magnitude is about 24, which puts the diameter at about 35 meters. The rotation period has been measured and it is 11 minutes, so it's a super fast rotator. And the Yarkovsky effect has been detected by the Elvinian cohorts, Greenbergen cohorts, and also by the JPL group. And these three measurements are very nicely consistent. The goal of our work, therefore, was to constrain the thermal conductivity and, as a consequence, also the thermal inertia of this asteroid. Next slide, please. To do so, we took into account a mathematical model of the Yarkovsky effect, which depends on several parameters, which are both physical and thermal parameters. In particular, parameters entering the modeling are the same major axes of the orbit, the diameter, the density of the asteroid, the thermal conductivity, which is the parameter we want to constrain, the heat capacity, the obliquity, and the rotation period of the asteroid. So if we assume that we have a measurement of the Yarkovsky drift, and if we also assume that all the parameters but the thermal conductivity are known, and this is reasonable because thermal conductivity is the most uncertain one, we can solve the model versus observed, the Yarkovsky drift equation, and basically determine the value of thermal conductivity that produces the measured Yarkovsky drift. If we assume further that this parameter has some distribution, we can solve the model versus observed equation for different combinations of the parameters, and basically use a Monte Carlo method to analyze statistically the outcome. So in the next slide, we can see what we got. Next slide, please. Okay, good, thanks. Okay, here on the left, in the upper panel, we can see the distribution of the thermal conductivity. And we found that these distributions are always B-model, with the first peak at around 7×10⁻⁵ in SI units, and the second peak at about 5×10⁻³ still in SI units, which are both very low. And moreover, the probability for K to be smaller than 0.1 is larger than 95%. And this is the first time that a low thermal conductivity solution has been found with such high probability for a fast rotator. Also, since we have the value of the density and the heat capacity, we can convert the distribution of thermal conductivity in thermal inertia that we can see here in the lower panel. And this is particularly useful because usually thermal properties of asteroids are estimated using thermophysical models, and thermophysical models usually give an estimate of thermal inertia. Next slide, please. So using this conversion, we found that the two peaks in thermal inertia are at 11 with a very small uncertainty, and at 88 in SI units with a larger uncertainty. And if we compare these values with other estimates of thermal inertia, we can see that big asteroids have very low thermal inertia, like Ceres, Pallas, or Vesta. And this is due to the presence of a regolith insulating layer composed by thin dust. On the other hand, the smaller asteroids, and in particular sub-kilometer asteroids, have a slightly larger thermal inertia, which is due to the presence of gravel and boulders of different size. And in general, these low values that we got is usually associated to regolith. So next slide. So in conclusion, our work is a first evidence that supports the hypothesis that regolith can be retained also on small and superfast rotators that has been found by Sanchez and Shears using mathematical models. However, this is not the only one, the only explanation. Indeed, we saw in yesterday's session that Hayabusa 2 and OSIRIS-REx missions found on Ryugu and on Bennu some large rocky boulders with low thermal inertia, but they were not covered with regolith. And this low thermal inertia was associated to a large microporosity, so to a specific property of the material. However, it is not clear if this is a property of C-type asteroids, and in that case, this will not apply to 2011 PT since it is supposed to be an E-type asteroid. Last hypothesis will be that this is a rubble pile, but this is highly unexpected. Of course, there is still more work to do. In particular, we need to characterize more of these small asteroids for planning deflection and redirect missions. And in the case that regolith is actually present on fast rotators, we should understand what are the processes and the time scale of the formation. And last but not least, it should be good to understand if 2011 PT is a good representative for the whole population of asteroids smaller than 100 meters. So I can stop here and thank you for listening.
Thank you very much. That was perfectly on time. Our next speaker is Dr. Alexei Sergeyev, a postdoc researcher at Observatory de la Côte d'Azur. And he's going to be talking about photometry of hundreds of NEOs from SDSS. So, Alexei, if you're here,
hello,
you're
everyone.
good to go.
Do you hear me? Are you hear me? Yeah. Okay. Okay. Hello, everyone. My name is Alexei Sergeyev. I'm postdoc on Observatory Côte d'Azur on Lagrange Laboratory. And today I will tell about photometry taxonomy of near-Earth asteroid from the Sloan Digital Sky Survey. This work is a part of NEAR-ROCS program. Next slide, please. At first, let's see the current asteroid statistics. At top figure, we can see the size distribution histogram of near almost 1 million asteroids from a novel asteroid database. Different dynamical classes shown by colors. Most of them, of course, is the main belt asteroids, but we also know orbital elements of almost 23,000 of NEOs. But how many of them were classified? Below you can see the statistics from the 3 latest NEOs observational program, MANOS, SHIELD, and NEOs. In summary, only 6% of near-Earth asteroids had a taxonomic classification. However, today a huge number of multicolor observations in the sky survey are available for astronomers. This data allow extract and analyze moving solar system objects, and today we'll tell about analyzing near-Earth extracted from SDSS. Next slide, please. SDSS is one of the oldest and biggest digital sky surveys. The final observation was done in 2008. It covers almost 15,000 square degrees on north part of the sky, excluding Milky Way area. CCD observations were obtained with 5 optical filters from ultraviolet to near-infrared. Survey provide a source catalog also as feeds images of all CCD observations. SDSS have a very important for classification feature. It is a quasi-synchronous multicolor observation. Thanks for scanline CCD registration procedure, SDSS images have a little time offset between observation and different filters. This allows to distinguish moving object on the images. On the other hand, this time is between exposure is not so big, something more 1 minute. So it's, let's say, about simultaneous observations that are important for estimation asteroid color. Next slide, please. And of course, Sloan survey data were used before for building catalog of solar system objects. The last release, Mach 4, includes observation of 100,000 asteroids. However, the only half available in SDSS archive data were processed for building this catalog. Therefore, we decided to build a new catalog of solar system objects where we repeated previous extracted procedure for all observation runs, but this time we removed fast-moving constraints as well as a star-like shape property. We also used an amazing Skyboard service to find all asteroid or no asteroid in SDSS frames. Then we merged both catalog. Of course, our weak constraints give us many false positive cases. Therefore, we did the extensive cross-match with span stars and Gaia surveys to exclude stationary sources like stars and galaxies. Our new catalog contains more observation linking with almost 400,000 known solar system objects, and included also 1,600 near-Earth asteroids. Next slide, please. Unfortunately, we faced with the situation that the fast-moving asteroids in time have not a correct photometry in the SDSS catalog data. Fast-moving sources could not recognize as one object or get an incorrect photometry for elongated tracks or even wrong estimated or 0 point in the frame. Therefore, we downloaded all nearest images from SDSS archive and did our own photometry only for news. We rebound all images to reference stars and did asteroid photometry in elliptical apertures. Next slide, please. When the asteroid had several observations, we stuck it. Next slide, please. Yeah. Okay. No. Previous. Something delayed. When the asteroid has several observations, we stuck it primarily normalized images to increase signal-noise ratio. For taxonomy classification, our very important infrared range. However, as they say, infrared data have a relatively low signal. Therefore, we selected only 500 near-Earth asteroids, which have enough signal for taxonomy. Next slide. Obtained asteroid color photometry was used for classification asteroids with widely used by DeMille taxonomy. Actually, we follow modified DeMille carry approach with the strict boundaries in 3D color space, G-R, G-I, and I-Z, used for computing probability of taxonomy complex. We crossed Gaussian distribution of asteroid color with boundaries to calculate probability. Next slide. Taxonomy color boxes were chosen in the way that the relativity color reflectance of asteroids coincides with the BAS-DeMille spectral template shown at the right figure, where we have blue boxes of SDSS reflectance and black line, it is BAS-DeMille templates. To check the taxonomy accuracy, we computed the confusion matrix of all new SSD taxonomy versus about 70,000 published before. It's visible on the left figure. Some rare classes like A and Q are underestimated because sometimes the SS photometry accuracy does not allow to clearly define a complex. Next slide, please.
Apologies, Alexei, we only have 1 minute left.
Yeah, I just finished it. The main result of this work is a taxonomy of 420 NEOs extracted from SDSS. On the top figure are presented color diagram and taxonomy boxes of classified NEOs, and below their distribution by dynamical classes. Next. this. We also use Gravlik 7th region model to check NEOs. It just have a good agreement with the previous works. Next slide, please. In the conclusion, I would like to demonstrate that the SES-NEOS histogram, its comparison with previously cited near-Earth observation campaigns. The obtained taxonomy are more than 400,000 NEOs in the Sloan digital sky survey, along with other obtained data, show a nice perspective for using data mining techniques for analyze asteroids. This method, with some modification, will be applied for extracted taxonomy from the other existing and future surveys. Thank you for your attention.
Thank you very much. And last speaker of this session is Dr. Nicholas Moskowitz. Do we have slides? Sorry. Yeah, so the last speaker of this session is Dr. Nicholas Moskowitz, astronomer at the Lovell Observatory, and he's going to be talking about the unique capabilities of the 4.3-meter Lowell Discovery Telescope for planetary defense. So, Nick, if you're with us.
Yes, can you hear me?
Yes, we can hear you loud and clear.
Great. All right. Hello, everyone. So yes, I'm going to be talking about the Lowell Discovery Telescope. This is our flagship telescope at Lowell Observatory. And I'll be talking specifically about some of the observations that we carry out at this telescope with regard to planetary defense and NEO characterization. I'll start by going over some of the capabilities of the facility, sort of a high-level overview of some of the parameters of the facility that make it such a capable asset. I'll then give some specific examples of recent studies that we've conducted to carry out some characterization campaigns of interesting targets. And then I'll finish by talking about how we might turn the LDT to our hypothetical impactor 2021 PDC. Next slide, please. So this is the Lowell Discovery Telescope. It's located in central Arizona, about an hour south of Flagstaff, 2 hours north of Phoenix. It's a 4.3-meter aperture telescope. And I'm going to really focus in on the next slide on what we refer to as the instrument cube. So it literally is a cube at the back end of the telescope. So at the top here is the primary mirror. The light enters the instrument cube from the hole in the primary. And we have a cube that has 5 sides. The top port is where the light comes in, and each side has an instrument mounted on it. So we actually co-mount 5 instruments at the same time. This is sort of a cartoon schematic of what that looks like. So what that means is that on any given night, we have 5 instruments available to us to conduct observations that are best suited to whatever's up in the sky that night. We can easily swap between instruments with movable fold mirrors that swing out of the way and can select the different side ports. And that generally takes about 60 seconds or so. So it really is a highly efficient facility that allows you to collect quite a bit of data in a pretty short period of time. And I'll show some examples of that in just a second. Next step, please. The instruments I'm going to be talking about, just real briefly, one is referred to as NITE. It's a near-infrared spectrograph that's good for collecting taxonomy and composition. Next. Yep. So the next is the Davini spectrograph. It's at visible wavelengths, again, for taxonomy and composition. And then last step on this page. So LMI is a large monolithic imager. It's a moderate field of view, visible wavelength imager that's good for astrometry, photometry, colors, and phase curves. So next slide, please. All right, so talking first about some of the astrometry that we do at the LDT. This slide is specific to a NASA-funded NEO follow-up program that Maxime Devogel is the PI of, started back in 2019. The histogram in the upper right shows the number of observations as a function of parent G magnitude for the targets that we've observed. So we've collected astrometric measures of several hundred, we've collected several hundred astrometric measures. And generally, the quality of the astrometry is very good, sort of 1/10 of an arc second or better in many cases. Next step. Here's one of sort of our highlight examples. This was a virtual impactor back in 2019. With just 5 300-second exposures, we got a what would be considered in the astrometry game a strong detection there. but this was a V of 25.5 magnitude object. So this is still the faintest object we've observed at the LDT for astrometry, but it shows the capability of the facility for faint object astrometry. Next step. Yeah, so we can collect high quality astrometry at V greater than 25. Next slide, please. We can also collect spectroscopy, and so this is a recent example from just a few weeks back during the favorable apparition of Apophis when it was flying relatively close to the Earth, not as close as in 2029, but it was the next favorable apparition, or the last favorable apparition before 2029. We collected both visible and near-infrared spectra using the Davini and Knights spectrographs, and all of this was collected within about an hour and a half or 2 hours. So being able to collect this comprehensive spectra in a short period of time is a highly efficient operating mode for the facility. And our result compares nicely with that of previously published works showing spectral properties of Apophis. Next step. So just the efficient collection of visible and near-infrared spectra in a single go makes it really a capable characterization tool for spectroscopy. Next slide. In terms of photometry, here's a nice example of a pretty faint object. This is a VMAG or apparent magnitude object of about 1/23. This was the Mini-Moon 2020 CD3, and this was a result published earlier last year, where we were able to get a decent light curve on a pretty faint, pretty fast-moving object. And if you go to the next step, please. The point here really is that we can do faint object photometry in a relatively rapid response mode. This was sort of a quick response to this interesting mini-moon that had been discovered, and we were able to get a decent constraint on the rotation period, which turned out to be pretty fast, just a few minutes. You can see the period there of 0.053 hours. So demonstrating the photometric capability at pretty faint apparent magnitudes here. Next slide, please. The last example here that I'm showing is photometry of Didymos. And so here we have the primary light curve up top and then the decomposition of the primary light curve on the bottom, showing the mutual events that we've been detecting from the LDT. This is just one example of data that we've collected. If you go to the next step, please. We've actually contributed quite a bit to the orbit solution for Dimorphos. So looking at just the data since 2015, all of those highlighted in this table were those occultation and eclipse events that were obtained with observations at the LDT. So we've made a major contribution to the Dimorphos orbit solution that's going into the mission planning for DART. Next step. And the key for the Didymos observations has really been high precision, 10 millimags or less errors on the photometry. And we've been able to achieve that consistently throughout this Didymos observing campaign dating back to 2015. And next slide, please. Okay, so let's imagine what we would do with LDT for 2021 PDC. So I would sort of step through this table here where we have dates, action, and the result of that action. So a couple days ago, 2021 PDC hit a 5% impact probability, so we got to get serious. So next slide, next step, please. So I don't know if the impact scenario organizers knew this, but the LDT proposals are not due until May 3rd. So that's great because we have time now to prepare our proposals for 2021B to secure observing time. Between now and the potential impact in October, we'll collect weekly astrometry at that high precision to be able to refine the orbit. The next step. We'll be able to collect photometric data as well. And I encourage you to check out the lightning talk by Annika Gustafsson, where she talks about photometric phase curves being a way to constrain albedo, surface properties, and then rotation state and morphology as well.
We have a few seconds left, so.
I've got just a little bit left here. I'm almost done.
Okay, thanks.
Right around this time, we would start trying to collect colors and low signal to noise visible spectra, which will allow us to constrain spectral type and coarse composition possibly. Next step. And it wouldn't be until sort of a few days before the potential impact that we would be able to get high signal to noise visible and near IR spectra. And that's just due to the faintness of the object. And at that time, we get a detailed spectral type and composition. So last step, I believe. Yeah, so the bottom line for 2021 PDC, we, from discovery through to impact, LDT could constrain a wide range of physical properties for our hypothetical impactor. Thank you for your attention.
Thank you very much. And so we have about 13 minutes left for questions in this session. So Stephen's gonna take you through how it's gonna look like.
Okay, thanks a lot, Agata. Just a few quick notes. Firstly, I want to thank all of the speakers for the great talks and for staying more or less on time. Just a quick note on the format of the questions. We'll do something slightly different this time. We'll work our way through the talks one at a time, and then we'll take questions. And if there's any time left over, then we can have it as a more general question and answer session. If the panel asks a question, could I ask you to also put a note in the or ask the speakers to put a note in the chat area too, so that everyone can follow the verbal questions as well as any comments that are in for those that are joining later. So with that, I would like to start the questions for Peter Pravic's talk, please. So there's the first question here was from Joe DiMartini, and the question is, why is it strange that the orbit for the binary asteroid is slightly eccentric, and does it indicate that the secondary formed relatively recently? And I know there is an answer in the text area already, but Peter, feel free to talk a little bit more about that.
Yes, sure. Of course, because the tides between the binary system components lead to circularization, so the stable end state is a circular secondary in a circular orbit. So the eccentricity for most binaries we observe are very close to zero. So having observed some with really non-zero eccentricity is rare. We don't see it very often. And why it's in such unrelaxed state, we can only speculate. Yeah? Of course, it could be a young system. It might have been formed recently, relatively recently. How recently, it's an open question depending on the tidal parameters, rigidity and quality factor. It could be a few 100,000 years, but it might be very different time. So we don't really know how young the system could be. It might also be that the system has experienced close close approach to Earth, and the gravity from the Earth changed the orbit and the rotation, or basically the orbit. So it could be both processes that could be at work. We don't know. Hopefully the JANAS mission will give us some better idea.
Okay, thank you very much, Peter. Agata, I think Agata has a question.
Yeah, I just wanted to know a little bit more about the numerical simulations. So they are constrained by the parameters that you get from observations, is that right? And how the uncertainties in those observations affect the outcome of those simulations?
Do you mean uncertainties of the parameters we have obtained, or I didn't quite get your question?
Yeah, so I was just like to know more about the simulations, because you had to rush.
Yeah. Of course, because it's in an unrelaxed state. We have not been able to get the orbit over all the years because it's precessing and inclined. So we do not have a unique solution for the precision. Yeah. So what we have got is a series of simulations that qualitatively explain the observed range of in which the orbit and the secondary rotation period is observed, but we don't have a unique solution because simply we don't have enough data to get unique solution. So we will present it in the paper later this year.
That's brilliant. Thank you very much. Should we
yes,
proceed to?
Yeah, thanks a lot for that, Peter. Yeah, let's move on to for questions for the next speaker, please. I'll hand over to you, Agata.
Yep. So first question is from Clark Chapman. He says, R types are rare. One spectrum you showed was very noisy. Are you sure these aren't S types?
I will unmute. I already answered this too, but yeah, that was a very unfortunate selection of an example of an R type. I agree with Dr. Chapman entirely that that might be also an S type because it's very noisy, but we have a total of 3 R types in our sample, and at least 2, the other 2 have high quality spectra, and actually one of them has a near infrared, and I can confirm is an R type, which is great.
Thank you. Yeah, so another question from Simon Ieva is, Hola Julia, great work. Are you considering observing these targets in near infrared too?
Yes, ciao Simone. That's a good question. Actually, many of these targets were discovered when they were very faint. So it's hard to get near infrared spectra when they are that faint. But we are currently starting to use the near infrared spectrograph available at the GTC to obtain near infrared spectra of potentially hazardous asteroids. So I encourage you, or those of you that have interest, to see the enlightening talk by David Morate, who is presenting very preliminary results at this respect. But yeah, sure, it would be great to have also the near infrared.
Yeah, and one quick question from me about the observing strategy. So what is your strategy for selecting the targets? Is this just the brightest NHATs available, or the one that has shortest time left on the sky?
We have an approved program with a certain amount of hours to observe at the GTC, and you know how these large telescopes work, that this is they work in queue mode, so they have to queue your observations with other observations of other scientific projects, and depending on the rank that your proposal had when they gave you the time, and also on the weather conditions and on the constraints that you impose on your observations. So whenever I receive an alert and whenever there's a good weather, I just add this target to my phase 2. And if it's possible and all these conditions are complied, then they observe it. That's how it works. So it depends on several factors, actually.
Thank you very much. And I think we'll proceed to questions for the next speaker. Stephen, do you want to ask those questions?
Yeah, sure. Okay, so this is a question for Marco Fanucci from Samuel Jackson. The uncertainties on H values from MPC data are usually large, giving a wide range of possible sizes for 4,99998. Does this large uncertainty in size propagate into your Monte Carlo simulations for the thermal inertia? And could this limit your interpretation of the data in the context of small, fast rotators?
Yeah, actually, we determine the value of the absolute magnitude independently using the Pan-STARRS observations, and Robert Werik helped a lot in this respect. But I would say that the albedo is more uncertain than the absolute magnitude and could perturb the diameter much more. But anyways, we obtain the thermal conductivity, allothermal conductivity solution down to sizes of 18 meters. So the results looked very, very strong in this respect. It was almost independent from the diameter.
Okay, thank you. Another quick question that just came in from Mallory DeCoster. This question is also for Marco. Very nice talk. What is the temperature of the asteroid that you measured? Is it possible to do a temperature-dependent study of the thermal conductivity of 4,99998 asteroid?
Yeah, thanks for the question. It's actually really interesting. Yeah, the thing is that we didn't use a thermophysical model, so we didn't know the temperature of this asteroid. We didn't have thermal infrared observations. We just used the value of the Yarkovsky effect. So I'm not really sure that with our method we could study the temperature dependency actually. But anyways, the orbit is not really eccentric, so probably it will not affect much the result.
Okay, thanks for that, Marco. Okay, we'll switch to the next speaker in the interest of time. This is questions for Alexei Sergeyev, and I'll hand over to Agata again, please.
Yep, so I have a quick question. What is the potential for sparse light curves from SDSS? So you were showing multicolor photometry, but is there any chance for light curves there?
Yeah, asteroid observation in SDSS vary made with frequency is 1 or more days. So it's almost not impossible to build light curves by this data. Maybe if the asteroid have a bigger date period, it is possible. On the other hand, the observation between different filters is about 1 minute and on 5-minute range. So it's not enough for build something, but for fast rotated asteroid, small asteroid like NEOS could be some light curve, but it is but this observation have not enough statistics for something good. Maybe different surveys who has several observation, but not as this.
Yeah, thank you very much. Anyways, the results are very interesting. So we have one more speaker. So are there any questions for Dr. Nicholas Moskowitz and the Lowell Discovery Telescope?
Great.
Not,
I have a quick question.
Yeah.
I have So can Nick say a little bit more about the tracking capabilities of the telescope? You know, can they track, you know, like fast moving targets across the sky?
Yes. So in short, the answer is yes. We can absolutely track quite quickly, and we haven't really hit a tracking limit yet. The tracking is not only able to go quite fast, I mean, essentially as fast as we've done artificial objects in low Earth orbit, so we're able to track really quick. But the tracking accuracy is quite good as well. One of our instruments only has a 1 arc-minute field of view, and so you have to be able to track on these fast-moving objects with a precision much less than 1 arc-minute to be able to actually keep up with them. And the telescope performs exceedingly well in that regard. So it works. It makes things more efficient, essentially. That you don't spend a lot of time trying to refine the pointing to get the object just right. It's just sort of once you get it there, it stays there.
Hi, Nick. It's Stephen again. I have several questions to ask you, but before I do that, there's a comment from Melissa Brucker on the chat. Melissa didn't quite catch on whether the V and NIR spectra were taken in succession or simultaneously. Could you maybe comment on that, please?
Yeah, sure. I didn't say that, so there was nothing to catch. But thanks for the question, Melissa. So the visible and the near IR spectra cannot be collected simultaneously. We collect those in succession. We do have a dichroic that feeds the near infrared spectrograph that allows us to obtain visible colors and near infrared spectra at the same time. So we can do visible colors and near IR spectra simultaneously.
Okay, thanks. I'll hand back to Agata.
Yes, thank you very much. It seems that we are on time with the session. So I would like to thank again all the speakers that presented today. I encourage you to join us for the section 6B, which is going to be in the afternoon, the second part of the NEO characterization section. And also this evening, at least in my time zone, 19 to 20 hours UTC, there's going to be an unofficial session with some additional presentations from people who contributed posters and e-lightning talks. So thank you very much again.
Will be, as announced yesterday on behalf of SamePage, and it will be on potential space missions to mitigate the NEO threat of this hypothetical object 2021 PDC, where we heard about yesterday. And this presentation will be given by Brent Barbie. And Brent is an aerospace engineer at NASA Goddard Space Flight Center and adjunct faculty in the University of Maryland's Department of Aerospace Engineering. And his prior work includes serving on the flight dynamics team for the OSIRIS-REx asteroid sample return mission, serving on the 2017 NASA NEO Science Definition Team, and being an author of the US National Near Earth Object Preparedness Strategy and Action Plan. He also performs space mission design research for planetary defense and is a member of the investigation team for NASA's upcoming Double Asteroid Redirect DART spacecraft mission. And Main Belt Asteroid 120208 was renamed Brent Barbie in honor of his contributions to asteroid missions and planetary defense. So I would now invite Brent to take the floor and see what are potential options for this threatening hypothetical object. And one additional piece of information, I see right now we have 236 participants at the start of this session, 237 and counting. Please, Brent, you have the floor.
Thank you, Gerhard. Good morning to everybody, or good afternoon, depending on your time zone. As Gerhard said, I'm going to provide an overview of our analysis of space mission options for the 2021 PDC hypothetical asteroid impact scenario. And this work is performed on behalf of the Space Mission Planning Advisory Group, or same page. And here on the title slide, you can see the list of co-authors who collaborated with me on this analysis. Okay, so this is a brief summary of the information that Paul Chodas presented about the 2021 PDC hypothetical object yesterday. On the right-hand side, you can see the object's orbit, including the point where its orbit intersects that of Earth and would have an impact in this hypothetical scenario on October 20th. As a reminder, this object is discovered only 6 months before its potential impact date. And so that leaves very little time to take action. As well, the object's physical properties are not known very well. All we know is its absolute magnitude or its intrinsic brightness, and the asteroid size could range from as small as 35 meters to upwards of 700 meters. So there's a significant uncertainty in size. If the asteroid's albedo or reflectivity is around 13%, which is sort of a typical average value, then its size would be only 120 meters. So the asteroid's orbit is very inclined with an inclination of 16 degrees, and that makes it difficult to interact with via spacecraft missions. The other important point is that the short warning time means that deflection is not practical in this scenario. Deflecting the asteroid on this short time scale would require so much change in velocity or delta V be imparted to the object that the object would not physically be able to tolerate it. As well, performing so much change in velocity on it in the first place would be very difficult. The other important point to make right away is that rapid launch capabilities to actually launch spacecraft in a short warning scenario like this are not currently available. The other important point is that enhanced INEO detection systems, such as NASA's INEO Surveyor space-based infrared telescope mission that's currently under development, can prevent short warning scenarios before they occur. It's much better to find these objects as far in advance as possible of their Earth impact dates, which makes it much easier for us to deal with them using spacecraft missions. However, late discovery of an asteroid, or most especially a comet, cannot be ruled out, which makes rapid launch capabilities still of importance. However, if we were confronted with this 2021 PDC hypothetical scenario in real life today, we would not be able to launch any spacecraft on such short notice with current capabilities. So today, for the sake of discussion only, I will describe space mission options for this hypothetical scenario that could be available if and only if we had the ability to rapidly launch spacecraft missions on these very short timescales. Because deflection is impractical, we consider disrupting the asteroid by a nuclear explosive device. In order to assess this and look at the performance of the nuclear explosive device, or the NED, we used approximate engineering models provided by Lawrence Livermore National Lab and Los Alamos National Lab. In an actual situation, detailed modeling would be necessary for the particular scenario at hand, but the approximate models allow us to assess performance reasonably well. So we also looked at the statistical distribution of the object's properties that Lorian Wheeler spoke of yesterday. And so we evaluated the NED performance against these large distributions of the object's possible size and density and mass and so forth. And what we found was that the uncertainties in the asteroid's physical properties are so large that we were unable to really compute useful, meaningful statistics for the likelihood of success for disrupting the object with an NED. So we assessed missions in terms of, delivering the largest possible NED to the asteroid, given our design constraints. Now, although rapid launch capabilities are not currently in hand, what we did was we modeled launch performance for what would be representative of a repurposed commercial intermediate class launch vehicle with a kick stage added to the rocket's upper stage, launching from Cape Canaveral. We set a launch no earlier than date of May 1st, 2021, which is only 12 days after the asteroid is discovered. And we also enforced a constraint that the asteroid cannot be reached any later than September 20th, 1 month before the Earth encounter. Notionally, this would allow at least 1 month for the disrupted asteroid material to spread out to ensure that it would not pose any residual threat to the Earth-Moon system. But of course, that would require a detailed analysis of the particular scenario at hand in practice. We looked at mission options for both rendezvous and flyby, both ballistic and with low-thrust solar electric propulsion. And we also considered mission designs for both reconnaissance and nuclear disruption. Here are our findings for the maximum delivered spacecraft mass trajectories in flyby or intercept mode. We looked at 2 different representative low-thrust configurations, as well as a ballistic trajectory option. And what we found was that the largest amount of mass that we could deliver to the target ranged between a little over 2,700 kilograms and up to a little over 3,000 kilograms. So that's the amount of mass that we have to work with. And bear in mind that some of that mass will be spacecraft structure and subsystems and other inert components of the spacecraft. And so that mass has to be set aside before considering how much mass of nuclear explosive device could be delivered to the asteroid using these trajectories. Note that these trajectories all launch in mid-June. So these are not bumping up against the earliest allowed launch date in the analysis. And so this would be launching just a little under a month after the asteroid was discovered. And all of these, however, do make use of the latest arrival date permitted in the analysis. All of them reach the asteroid on September 20th, 1 month before its Earth encounter. I didn't show the trajectory plots for the rendezvous missions, but in a moment I'll show the mass. It turned out that those missions were not practical. They were not able to deliver enough mass to constitute capable spacecraft. As well, the flight times are just too short for the low thrust propulsion to make a significant difference in delivered NED performance. We did look at flyby reconnaissance missions with earlier launch and arrival dates that could deliver in the neighborhood of 800 and 900 kilograms worth of reconnaissance spacecraft. And we also did a quick mass analysis and determined that the largest NED yield that could be delivered using the high-speed intercept missions I showed previously is about 4.5 megatons. Then calculating what that could do to an asteroid, we find that the largest size asteroid that could be disrupted by this device would range between 100 to about 210 meters, depending on the object's density. And so what we'll do next is we'll show how launching either a reconnaissance mission or this 4.5 megaton nuclear disruption mission could improve the statistical impact damage risk assessments that Lorian showed previously. So this chart here summarizes the potential benefits for deploying a reconnaissance mission. So if we assume that the reconnaissance mission could determine the diameter of the asteroid within plus or minus 10%, that substantially narrows the range of potential damage areas for disaster response. And it, for example, it reduces the maximum potential damage radius from 470 kilometers down to 160 kilometers. So this would provide a significant benefit for disaster response planners if they were able to obtain this information earlier in the scenario by virtue of a rapid flyby reconnaissance mission. Then we looked at how much the hypothetical nuclear explosive device mission could potentially reduce the risk of impact damage. So suppose that the 4.5 megaton nuclear disruption mission were deployed and sent to the object. And then, it's really a question of, all right, well, what are the chances that the object is in fact small enough that is not as large as it could be based on these large distributions on the uncertain size of the object. But suppose it's small enough that the nuclear device could properly disrupt it. Well, in that case, we find that 64% of the statistical cases considered in Lorian's analysis would be successfully mitigated. And so that reduces the chance of damage affecting any population by about 57%. And so the bottom line here is that even launching in the face of uncertainty, from a statistical point of view, deploying an attempt to disrupt the object does have a significant effect in terms of reducing the statistical risk that it poses in terms of impact damage. Okay, so here I'll summarize the findings and recommendations. Because of the 2021 PDC hypothetical objects, significant uncertainties in its physical properties, it is difficult to define requirements for mitigation missions in terms of, for example, what yield nuclear device needs to be deployed. And it's also difficult to estimate the likelihood of mitigation mission success. And this is all because there's such a very large distribution on the object's key parameters, size, density, mass, and so forth. The other important point is that current real-world infrastructure for spacecraft development and launch would not enable us to deploy either a reconnaissance or a mitigation spacecraft mission during such a short warning scenario. That being said, even if we could launch, deflection would not be practical because of the short warning time, and therefore robust disruption of the asteroid would really be the only practically viable mitigation option. The other thing to note here is that, although I didn't emphasize it earlier, these short warning mission options require high-speed flybys in the order of upwards of 10 kilometers per second at relatively challenging phase angles, meaning that the asteroid is not well lit by the sun from the approaching spacecraft's point of view. And that can pose significant guidance and navigation challenges for which we should be prepared to handle. Also, deploying a nuclear disruption mission in this situation could significantly reduce the risk of impact damage, and despite all the many uncertainties that we face in terms of the asteroid's properties. And we also saw that even if a nuclear disruption mission were not undertaken, simply deploying a flyby reconnaissance spacecraft would significantly reduce the uncertainties in the object's properties, and therefore significantly reduce the uncertainties faced by disaster response planners. And so that's my final chart. With that, Gerhard, I'm happy to take any questions.
Thank you, Brent. I think for this outlook, which is not too optimistic, but it is a realistic and challenging case that we have. I mean, not every time there is an obvious way of deflecting it and mitigating the risk. But let's open now the question and answering part. So if an attendee has a question, please put it under the Q&A and I will pass it on to the presenter. And those panelists, please put the question in the chat. I mean, obviously the time is very short. So if I understood it correctly, if I try to summarize it again, if we could launch more or less immediately, which is unrealistic, then there would be only two possibilities. Once fast flyby reconnaissance missions to at least perhaps get some additional information on the object. The size is very undefined, which is a very important parameter what the damage concerns. And the other option would just be, if you could show this again. And the other option would be to use a nuclear device and also during a flyby mission where you could be able to disrupt if the size is not more than about 200 meters, if this is what I figured correctly. So I see some first, some questions come in. And there's one question from Irmgard Mabu. How do you ensure that there will not be a launch failure? This would pose the most important risk on Earth.
That's an excellent question. So I think the best way I can answer that is that the same steps that are taken to preclude launch failures for existing nuclear launch systems, for example, ICBM systems, those same engineering measures would have to be put into place to provide similar assurances of safety in a launch scenario like this. But whatever the engineering solutions for that would be, I think that prior launch experience with those systems demonstrates that it's certainly feasible. But the point that Professor Marbo raises is very, very important, which is that safety would have to be a key concern and would have to be handled satisfactorily.
Yeah, thank you. I mean, there's a whole range of questions now. Let me just try to go in the order that have been answered. One question is, what sorts of investments would be needed to develop the capability to launch a recon mission a month after detection?
Wow. So I'm going to refrain from speculating on the financial investment needed to achieve that capability. So that's very difficult to estimate. It would have to be estimated in order to undertake those improvements to our infrastructure. Cost estimates would, of course, be necessary. We've just now recently started to look at what would be required to do it from a technical perspective. And it's also worth pointing out that there are other enterprises within the space domain that would also benefit from rapid launch capabilities besides just planetary defense. And so it is perhaps the case that the ultimate solution for rapid launch will not be solely planetary defense driven, but driven by other performance requirements as well. So I think at some point we're going to have a collaborative effort to estimate what those costs would be and who would bear them. So I don't have a dollar amount in terms of the investment required that I can provide. What I can say is that we've started to look at the technical aspects of it, but we've only just started, and so cost estimates will have to come a little bit later.
Thank you. And here's another question. I think several questions which aim more or less at the same point. Would it be meaningful if a spacecraft has been in orbit, in a parking orbit already, for example, L2, and would there be a specific type of orbit where this would have been most helpful for this case? Because you looked at one specific case, of course.
Right. That's a good question. For purposes of being at least mostly representative of what same page would be asked to do if this were a real situation, if this were not hypothetical, we tried to restrict our analysis to current systems. So we didn't look at what kind of performance you would get if you had something already in orbit. One of the challenges of pre-positioning something in orbit in the Earth-Moon system is that, and I'm going to have to get a little bit technical to answer this, but basically the outgoing asymptote, the direction you need to depart the Earth-Moon system in is going to be different for every asteroid scenario. And so if you park your spacecraft in an orbit around the Earth, you have to choose the inclination of that orbit. And your choice of that orbit inclination may not be compatible with where you ultimately need to send the spacecraft, and that can require a significant amount of extra propulsion to break out of Earth orbit and get going in the correct direction. So some careful thought would have to be given to exactly where to put it. Putting it at one of the Sun-Earth Lagrangian points might potentially be a better alternative. So that's something to be looked at. But the other thing to consider is that if you have complicated systems on board, possibly even nuclear systems, you're probably not necessarily going to want to pre-position that. You're probably going to want to keep it to where you could have access to it to inspect it and ensure that it's still in good working order before deploying it in an operational scenario. So there's advantages and disadvantages to putting something in orbit in advance, and we're going to have to look carefully at those trades as we go forward.
And another question, would it help to send a series of rockets, either with a nuclear device or even with a kinetic impactor? If you have enough of them, could you achieve something there with several rockets?
Sure. Yes, dividing it up into multiple impulses applied to the asteroid can offer some benefits. If you're trying to deflect it, it can help reduce the likelihood of accidentally breaking the asteroid up if that's not your intention. Similarly, it can allow you to get more deflection or disruption system mass delivered to the asteroid if you're utilizing multiple launches. Of course, the disadvantage there is that you have to have multiple launch sites and you have to be able to recycle the launch system very rapidly in order to get, a large number of spacecraft launched and on their way to the asteroid. But in the case of, so for kinetic impactors for deflection, yes, that can be advantageous. In this case, what we found was that, I didn't show it here, but it's in the appendices. The kinetic impactor mass required to deflect this object would be in the order of several 100,000 kilograms. So that's a situation where even having multiple launches would not necessarily make that feasible for the kinetic impact case. But in general, yes, the ability to deploy multiple spacecraft in series is, together so they can travel to the asteroid together is beneficial.
Here are some more physical questions. You mentioned that you could disrupt bodies up to 200 meters, accounting for densities 1 to 5 grams per cubic centimeter. Do these densities assume a monolith, or do they account for porosity?
It accounts for porosity.
Okay, and another more physical question. You ruled out deflection. And does this include also deflection by a nuclear device, by surface ablation, so without disrupting the body?
Yes, so perhaps this would be the time for me to flip to the chart in the appendices that that covers this. So now what you can see is here are the actual deflection requirements. This is a very busy chart, but the point is that it takes about 66 centimeters per second to deflect the thing if you apply that delta V about 3 months before the Earth impact. So a 1 megaton nuclear device could do that through surface ablation, and that's, it's relatively easy to deliver a 1 megaton device to the object. So a nuclear device could certainly provide the deflection delta V that you need. the problem is that that amount of deflection delta V is so large that it would make the asteroid anyway. And so in a situation like that, you run the danger of of having fragments remain on a Earth intercept course. And so it's much better to robustly disrupt the object very deliberately on purpose and you know, intentionally break it up into many small and widely scattered fragments, as opposed to trying to keep the object intact while imparting such a large delta V. So from a delivered spacecraft mass perspective, yes, a nuclear device with surface ablation could, you know, theoretically deflect this thing if the asteroid could take the hit, which it most likely could not. But what you'll see on this chart here also is that if you were to try to do the same thing with a you know, with a kinetic impactor, you know, you would need an enormous amount of mass, you know, several 100,000 kilograms, which would not be practical. I should also point out that those results are based on sort of the average asteroid size of about 130 meters. I was using that as a point of reference. Remember that there's a lot of uncertainty on the asteroid's size, and so if the asteroid were happened to be on the larger end of that distribution of possible sizes, then these numbers would no longer be valid. Then in that case, if the asteroid was too big, perhaps not even the nuclear ablation would be able to impart such a very large delta V to it for deflection.
Okay, thank you. So this has been at least considered in the analysis. Maybe I take one more question from the Q&A part and then look at the chat where we also have some questions. So if there is a nuclear explosive device explosion, would the asteroid fragments be radioactive? Would there be a risk of radioactive debris hitting Earth?
So I have not assessed the extent to which the debris might be radioactive. I would defer that question to my colleagues who specialize in the nuclear systems, and I would be happy to endeavor to get an answer to that and get back to the person who asked the question. I'd be happy to do that. What I can say is that the way that the asteroid disruption mission is structured, the idea is that only a very tiny fraction of the object's original mass will then go on to interact with the Earth-Moon system. And so even if there was some radioactive asteroid material, the intention would be that only a very, very tiny amount of asteroid material would actually interact with our atmosphere. And so that feature of the robust disruption might make the radioactivity of the asteroid material less of an issue. However, it's a good question, and I'd be happy to look into it more. It's something that we would certainly have to look into more anyhow as we get more into the details of assessing disruption performance.
Okay, I see. Let's look at some more questions. Would it make a big difference when we have a real big, like SpaceX Starship capability for these type of missions? So if you could really launch a much bigger payload into orbit.
Yes, having higher launch mass capability is certainly advantageous. The trick there is just how quickly could you launch it, and the other piece of the equation is would the spacecraft itself be ready? So remember that there's two parts to the rapid response. There's the availability of the launch vehicle itself, the rocket, on very short notice. And then there is also the availability of the spacecraft, ready to go to perform the reconnaissance or the mitigation mission, and also ready to be rapidly integrated with the launch vehicle. So, so the answer to the question is yes, having a rapid launch Starship class capability would be fantastic. But then we would also need to have the spacecraft ready to make use of the mass delivery performance of the Starship rocket.
And here's another question. Among the physical parameters possible range, what if the asteroid is a binary? This has not yet been ruled out for our hypothetical threat. So what would the net device output? Disrupting one component with some effect on the secondary's trajectory, or what would happen?
Great question. And this is actually one of the advantages of nuclear devices for asteroid mitigation, is that they're well suited to dealing with binaries. So remember that the radiation released by the device goes out in all directions. And so it's possible that positioning the device in between the two members of the binary system at the time of device detonation would allow both of the objects in the binary system to be dealt with simultaneously. Given that there's usually a size difference between the primary and secondary body in the binary asteroid system, for example, it might be possible to deflect the primary while obliterating the secondary, for instance. That's one possible modality. But in any case, the answer would depend on the specifics. It would really depend on just how large the primary and secondary were in this case and what their separation distance is. But fielding a 4.5 megaton device would give us, a pretty large performance envelope, and so we would have a pretty good fighting chance at dealing with the binary asteroid. But again, the details would matter.
Okay, and here's another question. You mentioned a 1 megaton nuclear device can be easily delivered. But are there 1 megaton devices readily available? And it's a bit unclear what is left in the inventory. So he says, it's actually from Randy Bell, I thought the weapons in the inventory had smaller yields.
I'd really need to defer that question to my colleagues at the National Nuclear Security Administration laboratories. But what I will say is that I undertook this analysis, with their guidance. And so what I can say in general is that what I'm showing here is reasonably representative of something that could be fielded, given current capabilities. But I can't go into any more detail than that. It's a fair question and one that we would have to look into. But I would say that, what I'm showing here is something that could reasonably be done if it had to be done, the rapid launch issues notwithstanding.
Okay, here's another more general question. Is it possible to prepare a mission at this time to protect the Earth from a medium-sized asteroid? Or perhaps one can add to this question, what is the minimum time you see that is needed realistically to launch a mitigation space mission?
That's a great question. Typically for deploying robotic interplanetary science missions, the approximate timeline is usually about 5 years from authority to proceed to launch. I recall that we were able to deploy the Lunar Reconnaissance Orbiter, which is not interplanetary, but it is, but it did, obviously go out to lunar distance, and I think that development time was about 3 years. So, if I were to speculate or make a guess, I think that if pressed, getting something launched within, the 2 to 3 year time range would potentially be doable, but it would be very, very difficult. And I would be concerned about the possibility of errors due to haste. I would be concerned about reliability. So I think that, that 2 to 3 years is kind of the approximate guess answer that I would give right now. And so in order to be able to respond to scenarios like this, clearly improvements would have to be made to the infrastructure in order to get the launch times down from there.
Thank you. Here's another question, or it's more like a comment from Tom Jones. So for the NED launch safety, could you choose a launcher that is human rated or equip the spacecraft with some launch escape system to recover the NED in case of a launch failure?
I think that sounds reasonable, certainly worth looking into, and I appreciate that suggestion from Tom. That's something that I'll certainly take back to my colleagues at the national labs for further discussion.
Maybe one more question. If you had the choice, perhaps in a case where you have a little bit more time and a more realistic chance to deflect the object or to disrupt it? Would you gain more advantage if you have a larger launch vehicle to either cut down on the mission time or to increase the delivered mass to the asteroid? What would be more efficient?
That's a good question. If you're, if you're trying to deflect it, then having the extra time can certainly be beneficial. So getting there faster could be helpful. In other words, if you could get there much sooner, months sooner, for instance, or even years, you could deflect it with much less delta V than you would require were you deflecting it at a later time. And that could be beneficial for a number of reasons. You would need less deflection system mass. You would run less risk of accidentally fragmenting the asteroid and these kinds of things. So, on the other hand, delivering more mass can also be useful for similar reasons. So I think it really depends on the details of the situation. The nice thing is that in the example provided by the person who posed that question, a launch vehicle like that gives you the choice, right? I mean, if the launch vehicle is powerful enough to deliver, significant mass to higher Earth departure energies, then it's up to the mission designer to choose how to use the vehicle. Launch at lower energies with longer flight times to reach the target and deliver more mass potentially, or launch on faster trajectories with shorter flight times that deliver less mass. But if you get there sooner, then perhaps, like I said, you could deflect with less delta V. So there's no generic answer to that question. The answer is that we would always trade those things against each other in the analysis at hand and see what would be the best solution overall.
And here's one more technical question. So is the concern of disruption with the kinetic impactor based on that being one or very few large spacecraft? Perhaps one could phrase the question a bit wider. Could you disrupt, let's say, a 150-meter object, which is in the middle of the size range, with a single large kinetic impactor or with a few?
So potentially, there's more modeling that would need to be done in order to assess the suitability of kinetic impact for robustly disrupting the asteroid. However, based on what we have looked at so far, from an engineering perspective, we would have much higher confidence in a successful, robust disruption if we were to perform it with a nuclear device. Achieving the same amount of momentum and energy imparted to the asteroid using kinetic impactors requires significantly more mass, to the point that the missions can become very unwieldy. So I would be reluctant to choose kinetic impact as the technique for robust disruption for that. I think that nuclear systems are the better choice.
And one more question: if there is sufficient threat of a large asteroid impact, should there be at least 2 vehicles ready for a deflection mission in case the primary vehicle failed? So should one always consider some backup?
Yes, and we this point came up at a couple of the prior PDCs when we worked those hypothetical scenarios, because in those cases the scenarios did allow enough time for launch, and so we had a more earnest discussion of sending missions. And in those discussions, we did indeed prescribe that there would need to be at least 2 vehicles to provide that redundancy. So yes, I agree with that.
Okay, I think we had a lot of questions. There were some more questions and also some comments, like on the decay of radioactive debris, that this goes relatively quickly, and it's a comment, not a question. I think we handled most of the question. I think we had a very lively discussion. So obviously, this is a subject that triggers a lot of interest, and I think we can conclude at this time and go into the break. Let me just check whether we have any more specific question in the chat, but I don't see one that is highly relevant. And then I would like to thank Brent again. I mean, you will also be a panelist where you will be available for more questions a little later. And let me point out again, there is again during the break, which will come now, the option to get into the Zoom meeting if you would like to have some more social chats or discuss any specific topics. And my apologies for those whose questions were not brought forward, but I think Brent did a good job and had a busy time to answer all of those questions. And I see just Alex has posted the link again for the Zoom meeting. And after this break, which will start now and last till 1:30. So we will start with, again, a special session, not a panel, and this time on legal and policy issues. So here we have planned 3 presentations on some legal questions which are a bit more in general, not just specific to this device. Obviously, I guess use of a nuclear device will be one important aspect. And so please be back on time at 1:30. So you have 17, 18 minutes. I see there is one more point in the chat. So it's just a pass code. And for this link is being provided. And I see we have another poll. So you are invited again to give your vote on this polling question. And with this, I would say enjoy the break and be back in about 15 minutes. And again, thanks, Brent, for your interesting presentation yourself. So we will now come to the second part. And this is again an exercise session, how we call it. And it's about legal and policy issues for deflection. We heard about the technical possibilities, which are not that many in the presentation before. And now we hear some more general considerations of legal issues related to planetary defense. And this session will be moderated by Alyssa Adagi, and she's the coordinator of the Same Page ad hoc working group of legal issues, which was established by Same Page because we realized there are many questions related to planetary defense which have some legal implications. And I would like now to hand over to Alyssa to take control of this session. Please, Alyssa.
Thank you very much, Gerhard, and hello, everybody. Today we will be talking about the legal issues regarding planetary defense. And this session is going to be a little bit different maybe than other sessions in terms of the structure. As Gerhard just mentioned, we are a group of lawyers working on the legal aspects of planetary defense for Same Page. 4 of these lawyers are here today and will give different kinds of presentations, but due to time constraints, we have moved a little bit around the structure. So we will first have a talk by David Koplow, who's a professor of law at Georgetown University, and he specializes in the area of public international law and national security law. And he will be talking about nuclear explosive devices and the legal aspects of those uses. Then you will have a 10-minute Q&A with him about this specific issue. And then you'll have a presentation from me on the legal working group and more specifically on the conclusions of our group report that was published last year. And finally, you will have a presentation from Ingard Marbo on more specificities of these reports, more specifically liability issues and decision to act. And after those 2 final talks, you will have again a 10-minute Q&A to ask questions to Ingard, myself, Alexander Suchek, and Cordula, who are also co-authors of the second presentation. On that note, I'll leave the floor now to Dave Koplow.
Thank you, Alyssa. And thank you all. It's a great pleasure to be with you today. And thank you also for accommodating my own end of semester teaching responsibilities. As Alyssa has explained, we're presenting the legal analysis a little bit inside out. I'm going to start by presenting one specific legal issue, and that is the possible use of a nuclear explosive device in a planetary defense mission. After my presentation and the discussion session, we'll then back up. I'll leave to go teach my class. We'll back up, and Alyssa and Erngard will present the bigger picture context, explaining the work of the ad hoc legal working group that was constructed to advise same page and a number of the other issues that we've addressed. But we'll start with the legal analysis of the possible use of a nuclear explosive device, and the ad hoc legal working group advised same page that there are 3 different treaties, or in one case, a group of treaties, that would be relevant in important ways to this kind of mission. Have the next slide, please. The first of these treaties, the one that is most familiar to this group, is the Outer Space Treaty, the foundational document for all of the work in outer space. And Article 4 of that treaty addresses the military or weapons aspects, and I presented here the first paragraph of Article 4. People often think that the Outer Space Treaty constitutes a very broad gauge prohibition on all nuclear weapons in space, but in fact, the coverage of the treaty is substantially more narrow than that. It prohibits 3 particular kinds of nuclear or other weapon of mass destruction activities in space. As I've highlighted on this slide, the 3 verbs of greatest interest are that the treaty prohibits placing in orbit around the Earth a nuclear weapon, installing such a weapon on a celestial body, or stationing the device in outer space in any other manner. Unfortunately, the treaty does not define those key terms, and there is no relevant state practice or precedent to inform our definition. So you have to interpolate what those words would mean. But importantly, the treaty does not prohibit a transit of outer space on a nuclear device. The negotiators wanted to retain the right to, for example, place a nuclear weapon on top of an intercontinental ballistic missile, which would carry the device briefly through space before it returns through the atmosphere to attack its target. So that kind of traveling through space is not prohibited as long as the device is not placed in orbit even once around the Earth, installed on a celestial body, or stationed in outer space. Therefore, the Outer Space Treaty's limitations on a planetary defense mission would depend upon the specific parameters of that mission. If the plan were to ascend the nuclear explosive directly into outer space, directly to attack the target, and directly to detonate next to the asteroid, that might escape the provisions of the Outer Space Treaty, as long as the device was never placed in orbit. Installed on a celestial device, a celestial body is somewhat more complicated. Would it count as installing if the device is landed on the asteroid, or certainly if it was burrowed into the asteroid? We also don't know exactly what stationing in outer space means, if the device is placed in a Lagrange point, or if it is if it travels on a parallel trajectory with the asteroid for a sustained period of time. Finally, on the Outer Space Treaty, I'll note that this treaty deals with nuclear weapons. And there could be an argument that a nuclear explosive device should not be categorized as a weapon if it is used for a planetary defense mission. In common language, a weapon is something that is used for warlike or criminal or other hostile purposes. And perhaps if the device is used for a humanity-saving mission, it should not be categorized as a weapon. The Ad hoc Legal Working Group considered this issue seriously, debated the different options, and ultimately concluded that the best interpretation of this treaty, the interpretation that is most consistent with a good faith rendering of the object and purpose of the treaty, the best interpretation would be to consider that a nuclear explosive device is inherently and permanently a weapon, despite its potential peaceful application. And in this judgment, I think we're joined by the majority of other international lawyers who have examined the question. But it is worthy of debate. Next slide, please. The second treaty that's relevant to the possible nuclear mission for a planetary defense operation is the Limited Test Ban Treaty of 1963. And I should emphasize that the Outer Space Treaty, the Limited Test Ban Treaty, and most of the others that we're addressing today are long-standing, joined by almost all the relevant countries around the world, and are considered essential to the preservation of nuclear stability and security on Earth. They were drafted long ago with purposes very different from planetary defense in mind. No one was thinking about the asteroid danger when drafting these treaties. But the provisions of these treaties remain in force, are tremendously important for international law, and embrace even a planetary defense operation. The Limited Test Ban Treaty is perhaps the most persuasive, most powerful of these. This treaty prohibits countries from conducting nuclear weapon test explosions in any environment other than deep underground, where the radioactivity could be confined away from the biosphere. And it explicitly addresses a prohibition on any nuclear explosion, including in outer space. This treaty, unlike the Outer Space Treaty, this treaty does not address the location, the placement, the trajectory of the device. It addresses the explosion, and it flatly prohibits all nuclear explosions in outer space. The treaty uses the term nuclear explosion rather than a term like nuclear weapon, so it avoids the problem that we were just talking about with respect to the Outer Space Treaty of whether something could be characterized in a different way because of its peaceful purpose. This treaty prohibits any nuclear explosion and would therefore constitute a very important impediment against the use of a nuclear explosive device for planetary defense mission. Next slide, please. Next, we turn to a set of treaties that address the problem of nuclear proliferation, trying to restrict the spread of nuclear weapons and the capabilities for nuclear weapons. The first of these is the Nuclear Non-Proliferation Treaty of 1968, the most important treaty in the area, perhaps the most important treaty in all of arms control. And it tries to restrict the spread of nuclear capabilities from the countries that already possess them to additional countries, and includes, in addition, a restriction on granting the non-nuclear weapons countries control over weapons or explosive devices, directly or indirectly. Again, unfortunately, the treaty does not define what is control, direct or indirect, but this language would have to be dealt with in any kind of a international planetary defense mission that included participation by some states that are allowed to possess nuclear weapons and some states that do not possess nuclear weapons. Whatever the non-nuclear weapon states do in the mission, it could not be allowed to constitute control, direct or indirect, over the nuclear weapon or explosive device, again, embracing nuclear devices other than weapons. Next slide, please. The second treaty that I want to talk about in the realm of non-proliferation is the newest instrument. This is the Treaty on the Prohibition of Nuclear Weapons that entered into force only in January of this year, just 3 months ago, and it already has attracted 54 parties and several other signatories. This treaty goes beyond a prohibition over the access to the control of nuclear explosive devices and requires its parties also not to control, but also in subparagraph E, they're prohibited from assisting, encouraging, or inducing anyone to engage in any activity that would be prohibited to a state party, including testing or using a nuclear explosive device. This language is so comprehensive that it would seem to prohibit the 54 parties from requesting the use of a nuclear explosive device in a planetary defense mission, supporting it, endorsing it, encouraging it, even voting in favor of such a mission in a United Nations body. So it too constitutes an important impediment in an international operation that would require the support or endorsement from other participating countries. Last slide, please. This is the summary chart recapping the restraints that the three important treaties would impose on the nuclear aspects of a planetary defense mission. The Outer Space Treaty prohibits 3 specific activities: placing the nuclear explosive device in Earth orbit, installing it on a celestial body, or stationing it in space. And we conclude that it applies to all nuclear explosive devices, regardless of whether they would be characterized as a weapon or not. Second, the Limited Test Ban Treaty is the most comprehensive prohibition on any nuclear explosion in space. And the non-proliferation treaties would prohibit the giving of control over a nuclear device to a non-nuclear weapon state, and for those that have joined the newest treaty, prohibit them from assisting, encouraging, or inducing their use. So that's a quick summary of the three main kinds of impediments that international law would impose on a nuclear planetary defense mission. I'd be happy to address any questions you might have about that, and then subsequent speakers will address the bigger picture context of the legal analysis of planetary defense.
You are perfectly on time. Thank you so much, Dave. We can now have questions for Dave and the questions of the legal aspects of nuclear explosive devices in space. So if you have questions, feel free to put it in the Q&A or the chat. And Dave, if it's possible for you, if you do have the time after the Q&A, when you have answered verbally, if you can answer in writing, this way, as I understand it, questions that are answered in writing in the chat are visible to everybody.
Good.
Great. I have not yet received questions, so let's see.
It's possible that my presentation was so persuasive that nobody has any rebuttals or any opposing thoughts.
This is what I think. Actually, I will do a follow-up question for you because we just heard from Brent and other speakers that in that specific scenario, we are lacking time. So in that situation, again, just as a speculative, what do you think would be the best option?
So a nuclear explosive device would not be anybody's first choice as a planetary defense operation. Considerations about environmental protection or safety or the politics would certainly urge resort to other less dramatic mechanisms. But if the time is short and if there's a need for prodigious amounts of energy to be deposited, then this option has to be considered. And the safest mechanism would be to avoid the Outer Space Treaty and have the nuclear weapon directly ascend and immediately upon rendezvous with the asteroid explode right away. That would avoid the three verbs of the Outer Space Treaty because the device would not be placed in orbit, installed on the celestial body, or stationed in space. But there's still the impediment of the Limited Test Ban Treaty, which prohibits for most of the countries of the world, most of the relevant countries, any nuclear explosion in space. And later presentations will discuss the possible legal workarounds, but that treaty is very direct in its operation.
Well, we do have a follow-up question by Joel Marks, who asks, and that is perfect for you because you're someone who works in national security and also on space law and the connection between the two. He asks, do the planetary defense people at the UN talk to the disarmament people at the UN? So I'm going to ask you, do the disarmament lawyers talk to the planetary defense lawyers?
Well, not very much. And in part, that's because there aren't very many lawyers in either of those categories. Until SamePage identified the need for an ad hoc legal working group, there was not much of an organized structure for international lawyers to address together the problems of planetary defense. And I think it's a tremendous tribute to SamePage that they've begun the process of assembling the relevant experts who could pay attention to this problem from the legal angle as well as from all the science and technology angles. The disarmament lawyers pay attention to nuclear weapons, and frankly, they are, to some large extent, horrified by the prospect that the effort to achieve control over nuclear weapons, to promote nuclear stability and nuclear security on Earth, the effort to restrict a burgeoning arms race in nuclear weapons, they're horrified by the prospect that something like planetary defense could provide an additional rationale for retaining nuclear weapons. The disarmament lawyers are interested in ridding the world of nuclear weapons altogether as a mechanism for preserving safety and security on Earth. And to the extent that planetary defense offers a rationale for the retention of even a small number of nuclear weapons, that goes against the grain of where the disarmament movement wants to go.
So we got a lot of questions that just came in, and we have 7 minutes left with you, so I am going to combine some so that we can talk about as many as we can. One is about ways forward. What do you think would be ways forward to enable the use of NEDs for planetary defense purposes? And this question is from Jan Osberg, and I will combine it with what are the implications if a nation violates a treaty? Because that's a classic of international law. So I'll send it to you.
Good. So both of these points are likely to be addressed in a little bit more detail in subsequent legal presentations where we try to present the solutions. My presentation is designed merely to identify the problem, but there are a number of possible solutions. Treaties can be amended. These particular treaties are difficult to amend. Their particular amendment provisions are cumbersome and time-consuming. Treaties can be withdrawn from. These treaties have provisions allowing a party to withdraw from a treaty, but that too is a somewhat cumbersome process that might not fit well with the compressed timetable, such as in the scenario that the conference is addressing this year. What we've concluded is that the best avenue for dealing with the entire array of legal problems, including the nuclear weapons problem, is to go to the United Nations Security Council. The Security Council has extraordinary power under the UN Charter, under Chapter 7 of the Charter, to make new law. And the Security Council has the power to supersede prior law, including these important treaties, if the permanent members of the Security Council agree to refrain from exercising their veto. That mechanism, a Chapter 7 resolution by the Security Council, we think would be the best route for modifying existing international law in order to accommodate the needs of planetary defense. There's no guarantee there because it does require the 5 permanent members to be unanimous, and there's no guarantee that will happen. Regarding violations of international law, these treaties are binding law in every country around the world. Treaties are taken very seriously. In the United States, the Constitution declares that treaties are the supreme law of the land, only under the Constitution, and therefore it is a significant legal impediment. The consequences for violation of a treaty or any other form of international law are somewhat restricted. International law does not have an adequate, robust mechanism for enforcing penalties, for inflicting upon violating states sanctions or other restraints. And that is and that's a problem for international law in general and here in particular.
I have a follow-up question from Steve Salmon, who asks, would it be possible to create addendums to the treaties just for planetary defense and just for the use of NEDs?
Good. So that's absolutely on the list of possibilities. And you could either amend the treaties or negotiate additional treaties or addenda. But that process is not quick. And there's no guarantee that all of the relevant countries would join in the process of modifying the existing legal restraints. And in general, international law requires that treaties have effect only for the countries that join those treaties. A country that was party to the original Limited Test Ban Treaty or the original Outer Space Treaty and did not support the modification would not have its rights affected by that modification. So that's a possible route, but it is, if anything, even slower and even less likely to achieve universal acceptance.
Well, we do have 1 minute left, and I'll bounce off to the point that you just finished with. One question asked, what would be the timeline if we had to make those addenda? What would it be possible, for example, in the scenario we're in, when they need to be a launch very soon?
So that's one of the virtues of the Security Council, is that that institution is established to be able to meet immediately and to address issues where there is consensus, to address issues in a very rapid timetable. Any of the other mechanisms requiring formalities of treaty law normally proceed at a rather stately pace and would not be able to meet the accelerated timetable of a planetary defense scenario. That, again, is one of the benefits of resorting to the Security Council.
And I will finish with one last question. It is about the definition of the term weapon. As you are an expert in that field, we have two questions here which ask, we're talking about nuclear explosive devices, we're not talking here about nuclear weapons. Would that make any difference for that to be able to pass?
So the source of the analysis is the treaty, or the Outer Space Treaty or the others. And the problem is precisely the difficulty of dealing with devices, implements that are capable of functioning in more than one way. And we're all familiar with this in ordinary language. A knife, for example, is a weapon when it's used to stab somebody. It is not a weapon when it's used to slice an apple. And therefore, the same implement can be characterized in different ways according to its immediate application. We've concluded that the best interpretation of the Outer Space Treaty is to treat the nuclear explosive device as a weapon inherently and permanently because of its unique nature. These devices, all of which were developed as weapons, tested as weapons, deployed as weapons, if you pluck one out of the weapon stockpile and use it for a different purpose, there's an argument that it is no longer a weapon, but we've concluded that that would undercut the effectiveness of the treaties by providing too easy an escape hatch for any state to say that we are putting nuclear explosive devices in orbit, not as weapons to threaten our enemy, but just because they might be useful someday for a planetary defense mission. Any country could evade the treaties in that way, and we think the best interpretation of the Outer Space Treaty, the interpretation that is most faithful to the object and purpose of that treaty, adopts a tougher definition of what is a weapon.
Great. Well, thank you so much, Dave. I know you have to run to your class to teach, and I will say to all the people who asked questions, thank you. There was a plentiful amount of questions. I'm very excited. I hope that we'll be able to address most of them in the two following presentations, as well as the final 10-minute Q&A. So thank you, David, and for the ESA commanders of slides, if you could launch my presentation. Perfect. So I will quickly introduce myself. As Gerard said, my name is Alisa Jihanadaji. I teach space law, policy, and ethics at Harvard University, and I'm the head of the ad hoc legal working group of SEMPAGE. Next slides, please. So today I will tell you a little bit about the context of this team that you've been hearing about for the past 30 minutes. Then I will go into the report's conclusions, and I will let you know about the sessions that you can join during the PDC, where we'll talk more about legal aspects of planetary defense past this session. Next slide, please. Next slide. Okay, so our team, it was created in 2016 by SEMPAGE, and it is currently composed of 15 international space lawyers from agencies such as NASA, ESA, DLR, the German Space Agency, the Mexican, Italian, Austrian, and UK space agencies. The role of the SEMPAGE Legal Working Group is to answer SEMPAGE legal questions regarding planetary defense mitigation missions. Next slide, please. So what do we do? I actually went up and took our terms of references so that we make sure that we don't say crazy things. The SEMPAGE Legal Working Group, its goal is to describe the existing legal context, in particular international law, relevant to the work of SEMPAGE, identify, formulate, and prioritize relevant legal questions and issues requiring clarification, where necessary, suggest possible ways forward to deal with legal questions and issues, and provide general legal advice to SEMPAGE. Little disclaimer before the rest of my presentation, the report's conclusion represent the views of the participating experts. So even though they have been nominated from space agencies, they do not reflect the position, the official position of national space agencies, ministries, and governments. So when you join the team, you present and share your views as an expert, not as a representative. And small addition to this slide, if you are interested in joining the legal working group, you can do so as currently for the next, I think, 6 months. There has been a call through SEMPAGE, and we would welcome you very much. Second disclaimer, these are preliminary conclusions. As you can imagine, we worked for 2 years on this report that is, I think, 95, 100 pages long. So in a 5 to 8 minute presentations, I will skip some things. So you just need to know that many points are matters that the legal community has not previously addressed and that remain debatable. And as new relevant data comes to light, revision may be necessary. So we will not talk about all of the conclusions. Also, the conclusions that we came up with are absolutely open to debate. Next slide, please. So let's get into the report's conclusions. Next slide, please. First of all, we are looking at international law. You know that when we look at space law, we can look at international public law, but we can also look at some national space laws. Well, for our report, we are focusing on international law. Based on international law, we all know that states are obligated to act in accordance with their international legal obligations, which mean that planetary defense missions must be carried out in accordance to international law. That's why we're staying in that pool. Also, under the Outer Space Treaty, each party is internationally responsible for the space activities of its governmental and non-governmental entities, such as private corporation, and is required to authorize and continuously supervise non-governmental entities. The reason I put this point here is because one of the first questions we get is, if there is a private sector company who decides to go and do a planetary defense mission, what would happen? We turn back to the Outer Space Treaty. This would be of the relevance of the state where this company is. So this is why we're staying at the international law level for this report and to answer this question. Next slide, please. So most importantly, first of all, obligation to inform and liability regarding misinformation. What happens if a state has information relevant to the prediction of a near-Earth object impact threat? Do they have to make this information available? Well, based on Outer Space Treaty Article 9 and Article 11, such information should be made available and shared. But if any planetary defense-related information is shared by a state or an international group, such as SunPage and I1, but that information turns out to be false, what would happen? Would those groups, would that state be liable for this false information? Well, if diligent and well-founded probabilistic information was provided in good faith, then they're not liable. However, you could have some legal action under national law in domestic courts that could not be excluded here. If that information is distorted or misinterpreted by a third party, let's say, for example, a liable information is sent out and somewhere biomedia there is a misinformation and there is a distortion of that information, then the original source that was liable would not be liable for that distortion. However, if a state releases information that it knows to be false in a grossly negligent manner and even deliberately, there might be a basis for a claim to compensate for international wrongful act in that situation. Next slide, please. Now we're going to jump to obligation to act. In a case of a near-Earth object threat, a state has legal obligation to try to protect its territory and its population. However, this will depend on the existing capacity and availability of resources of the state in question. A non-impacted state, however, would not have any legal obligation to assist another state at risk to be impacted. Next slide, please. Yes, great, thank you. Legality of planetary defense methods, where we're not going to go back to what Dave was just saying. I'm going to skip this relatively quickly, but as you've heard about the different mitigation methods during the beginning of this conference, there is the slow push and pull methods with gravity tractor, enhanced gravity tractors, ion beams, shepherds, and laser ablation. But those do not raise any particular issue of legality under international law. The main, I don't want to say problem, but the main debated aspect would be the use of nuclear explosive devices in space, and that I will refer to the previous presentation from Dave. I put it in the slide here, the main reason based on the Outer Space Treaty and the Limited Test Ban Treaty that Dave talked about, just so that when you check this presentation, you know why this solution would be debated. Next slide, please. So now let's go to liability for damage. A state has liability for damage done by any space object for which it is a launching state. For damage inflicted on Earth, the liability is absolute. That means that it applies even without any wrongdoing. So in the case of planetary defense, Absolute liability includes cases where an asteroid is insufficiently deflected and impacts at a different location compared to where it would have struck if it had not there had not been any intervention. Also, in case of malfunctions, failure, and damage caused on Earth or in outer space, the general rule of responsibility and liability apply. And I'm stopping here because a whole part of this is explained in my colleague's presentation that is following by Irmgard Marbo. Next slide, please. Finally, decision-making bodies. Again, I will not go too deep into this because this will be explained in better details in the following presentation. But regarding possible decision-making bodies for planetary defense action planning, the United Nations Security Council has extraordinary powers to supersede rules of international law through a decision which requires the vote of 9 out of 15 members and no opposing vote by one of the permanent 5 members of the UN Security Council. Other international institutions and organizations could provide valuable political support for a planetary defense action, and that again, for those other decision-making processes, I will refer to Professor Marbo's presentation. Next slide. So to know more about this, if you are tingled by legal aspects of planetary defense now, next slide, I would invite you to check out our report. It is full, it is with plenty of resources, and all of the authors of this group are listed. You can have the free download using this link, or even if you just Google Planetary Defense Legal Overview and Assessment, you will find it. And you will have at the beginning an executive summary, and at the end the full conclusions of the report if you don't have time to read all of it. Next slide. And finally, in the session decision to act on Friday, this Friday, April 30th, noon to 1:30 p.m. Central Time, so European time, you will be able to have 3 additional oral presentations, one on liability waiver, another one on this obligation to participate in planetary defense action, and finally one on reacting to near-Earth object impact, exceptional circumstances based on international law. And that is all for me. I will now let the floor to Irmgard Marbo for her 8-minute presentation before we then have again a 10-minute Q&A with Irmgard Marbo, Alexander Suchek, Cordula, Panosh, and myself. And before that, I just would like to say that Irmgard Marbo is professor of law at the University of Vienna and is the head of the National Point of Contact for Space Law at the European Center for Space Law. She specializes in areas of international law and space law. Irmgard, the floor is yours. Yes, thank you very much, finally. Oh, now I see all videos, which is not so okay, strange. Okay, but I see my slides. Thank you very much for Isa to taking care of the slide presentation. I have put my clock on that I will really keep the time of 8 minutes. And I will, as it was announced, delve a little deeper in some of the aspects which were discussed in the report of the ad hoc legal working group of SEMPAGE. Briefly, this will be about the obligation to inform and to act, liability, responsibility, and international decision making. Next slide, please. The next slide shows a little bit the overview of the kind and types of legal documents we looked at. First, of course, the Outer Space Treaty. In this case, it was with respect to the obligation to inform about a new impact threat is Article 11, which provides that states shall inform to the greatest extent feasible and practical about the nature, conduct, locations, and results of space activities. But also there's a second type of source which we looked at. These are the principles, the UN General Assembly principles, in this case, the remote sensing principles. And here we have Principle 10, which states that states participating in remote sensing activities that have identified information in their possession that is capable of averting any phenomenon harmful to the Earth's natural environment shall disclose such information to states concerned. However, I would like to highlight the General Assembly resolutions are only recommendations. They have no legally binding effect on states, but they are political commitments agreed by the General Assembly, which per definition can never issue decisions which are binding. They are only recommendations, but they have quite an important political weight, and states are in general try to follow them and be faithful to their political commitments. But then there is a third source, which are, for as an example here, the elementary considerations of humanity, which are unwritten principles, for example, here drawn from the International Court of Justice Corfu Channel case of 1949, which speaks in favor of a duty to share information in order to avoid the loss of human lives. So this is an unwritten source of international law, which we have then to distinguish with the written sources, the treaties, and then the written instruments which are not binding. So this makes a little bit, shows the picture of the sort of texts we looked at. Next slide, please. Obligation to mitigate, as Alisa already said, there is no explicit obligation to mitigate a near-impact threat. We looked here in this context to the UN Charter, which provides in Article 1 and 2 purpose of the United Nations to cooperate and solve international problems, also for humanitarian character, and that in Article 2, all members shall give the United Nations every assistance in any action. But this is too general in order to really provide a specific obligation to act in a specific way. We looked also to the human right to life, which is incorporated in a number of international treaties, such as the ICCPR, the International Covenant on Civil and Political Rights, the African Charter on Human and People's Rights, the American Convention on Human Rights, and the European Convention on Human Rights. They all include the right to life, which includes a due diligence obligation of states to ensure the right to life of those under their jurisdiction, including appropriate steps to safeguard human lives, taking into account their respective capacities and availability of resources. So this is just to give you also an overview of what we looked all at and which are the obligations. Next slide, please. Why is it important to look at real obligations and also to distinguish them from non-legally binding obligations such as recommendations? Namely, the consequences are different. We talk only about responsibility when we talk about the breach of an international obligation. And there's a difference to liability. A state may be held internationally responsible for a wrongful act even though there is no material damage. But a state may be held internationally liable for damage even though it did not act wrongfully. And on liability, I will talk a little later. Article 6 was already mentioned before, which is specific to space law, that also for non-governmental entities there is international responsibility. Next slide, please. Liability, burden, and protection was already briefly discussed by Alisa. Mainly the liability convention differentiates between the liability caused on the surface of the earth, which is absolute and unlimited, and is a very unique victim-oriented liability regime, which is why it can be a burden and for possible planetary defense mission. And Article 3, which is there to regulate liability if it is caused in outer space, so to another satellite in Earth. And here we have only the fault liability. And now, the next slide, please. We looked at the specificities to planetary defense. We looked at what the definition of the launching state, because only the launching state is liable. But who is really the launching state? Okay, the territorial facility of a space launch where a space object is launched. But there are also other possibilities like the procurement. So we try to define the two bullet points on the bottom of the slide to raise the question, who is a launching state and who is a victim, a third party or innocent bystander who should be protected. And we discussed, well, is a state that requests, supports, or endorses a planetary defense mission a launching state because it procures the launch? Or if not, if the state is a victim, third party, or innocent bystander entitled to full protection. Next slide, please. Also, the causation has been discussed, but in the end, I have to skip a little bit here this whole arguments. The result is yes, indirect causation may likely be sufficient to trigger liability and be legally actionable. So this is the result of liability. Next slide. What are the possible measures to mitigate the risk of being held liable? First, an agreement between the launching states, which can be several, 2 or more launching states. They are jointly and severally liable. And Article 5 of the Liability Convention suggests agreements among those regarding the apportioning of the financial obligations between them. So there could be envisaged an agreement of states directly carrying out the planetary defense mission with states asking for or agreeing to it, perhaps procuring it. And this would exclude their role as beneficiaries of the space liability regime. Next slide, please. A second measure would be agreement beyond the circle of launching states by an international mandate, for example, by the Security Council decision, which would embrace all UN member states. Also, an international understanding or agreement is possible. Yeah, okay. Oh, my own clock shows that I'm in the end. Here these agreements beyond, but next slide shows this. We have discussed several general aspects of reaching an agreement, that the instruments should be developed before the planetary defense missions are carried out, and templates could be developed. The last slide is then about international decision making. Who can make these agreements, or what other decision making bodies are relevant, possible? We discussed United Nations General Assembly with the advantage of universal membership. But the decisions resolutions are only recommendations. As I said, they are not binding, and they cannot alter existing prohibitions or liability regimes. So perhaps then we considered also the UN Corpus, which has a specific expertise and experience and can take input from I1 and SEMPAGE. It can report then, or does report regularly to General Assembly, which, next slide, can put the matter in front of the United Nations Security Council. So this idea is that we have these various possibilities of preparation, but in the end, probably at the end, it comes to the United Nations Security Council with its 15 member countries, which have majority decisions, 9 out of 15 votes, the right to veto. But it also has been highlighted that those are also those states with significant space capabilities. So it is an important forum and probably a very appropriate forum. But it has also been considered, if political differences arise or anticipated, another option, alternative, could be an ad hoc decision-making group, but specific structures and decision-making procedures would have been to set up, and the financing, timing, and legitimacy would need to be discussed and can be challenged. Generally, multilateral approaches would give more legal certainty to the states than unilateral actions. That's my end of my presentation. Thank you very much. Perfect. Thank you so much for this. And I am rude to cut you off, but the conclusion that I know you have are directly linked to some of the questions that came in. So I would like first to say that this presentation that Irmgard Marbo has just presented was written also by Cordula Panoche, who's the Faculty of Law at the University of Vienna, and Alexander Suchek, who's the head of the International Law Division of the European Space Agency. And the three of them are present for this Q&A to answer questions that you may have. As we're running a little late, I've made a pre-selection based on the question that you've already put in the chat. And I will start with this. Irmgard, what do you see as the current gaps in the legal framework? I mean, the gaps we see, we have presented the different challenges. I mean, liability regime is there. We have the prohibition of nuclear explosive devices. We have a lot of real challenges, not gaps. It's a challenge, and even some, prohibitions and some liability regimes which you cannot escape. So there is no way out. There's not a gap. It's clearly regulated. The only way we can find a way out, and by an agreement, as I put quickly there, or the Security Council resolution can deviate from existing prohibitions or alter also the liability regime. Perhaps these two problems are the most important. So how to deal with the prohibition of nuclear devices, if it is considered to be important. And the second is liability regime. There is no way out.
the language is so clear in the treaties that absolute liability occurs. So for anything that goes wrong in the mission, the launching state is liable and has to pay. And this is a burden and a deterrent even for states prepared to conduct such a mission.
Thank you, Ingard. We have an excellent question from Samuel Jackson, who says, how is the law reconciled with a country's legal obligation to protect its territory and population when a country is a signatory of the Treaty on the Prohibition of Nuclear Weapons, and the only option to protect its citizens is to use an NED?
I mean, this refers to the exceptions from responsibility, which we also discussed. So the circumstances precluding wrongfulness, that's the technical term. And there is the circumstance which is called a necessity, but it has a very strict conditions, and it is only valid for each particular state. So unilaterally you could try to say, well, I'm precluded from wrongful taking, but then you have to prove that's the only option and there is no other means, and every state has to do it unilaterally. So that's really what the group concluded. That's really a big burden and hurdle to say, well, each individual state must make this, must fulfill these criteria in order to avoid that it acts unlawfully. So it will not provide certainty. It would be very insecure, but there is this possibility, but it's dedicated for unilateral acts or for specific acts and not such an international multilateral endeavor, which planetary defense is.
Makes sense. I have two final questions, which are both for ways ahead. And as we understand, this report itself was to look at law as it is, but as your presentation highlighted, there are potential decision-making bodies that we could turn to and different way forwards. So currently, how do treaties impact the ability of nations to prepare mitigation missions? For example, if now, based on the scenario, a country wanted to get a spacecraft ready for deflection missions and send it to space, how does the law lies right now, and what could be done to make those deflection missions possible?
I mean, the general in international space law applies with all its parameters, responsibility and liability mainly, and also jurisdiction on space objects and everything. And it would not be different in any manner from any other space activity, and only the nuclear explosive device question is specific and is not on the table currently of any other space activity.
And I wish to respond to one question which asked in my presentation, I didn't talk about impactors. Yes, impactors would not create problem except if this impactor, an NED, was attached for some reason. And final question was, what can be done ahead of time? That's the big question, right? So what can be done ahead of time based on the legal aspects of planetary defense?
Yeah, ideally, I mean, things start right now. Ideally, you have more time to prepare, not only 6 months, which we have now in this scenario, which is really a very specific challenge. But also usually technical preparation for deflection mission also take some time. So at least that time of 1, 2, 3 years would be good to have to prepare such an agreement between states, prepare some waivers of liability, alternative scenarios. I think if there is political will, this can be done in 1 or 2 years easily, but half a year is really a challenge. So half a year, I see only actually the Security Council, which, as Dave said, it can immediately take decision. But if any other agreement on a more broader scale would need more time. But usually, if you start now, we are prepared for real scenarios which come up in 2 or 3 years, and then we have already mechanisms in place which then can be applied. So I'm optimistic. If we start now, we can be prepared. It's not impossible. Only the 6 months is quite a challenge, I would say, on purpose. The drafters of the scenario this time made it very hard.
Thank you very much, Ingard. Well, I will leave the floor back to Gerhard.
And as panelists, we have Brent Barbie, aerospace engineer at the NASA Goddard Space Flight Center. We have Detlef Koshny. He's the acting head of the ESA Planetary Defense Office. Lindley Johnson is with us. He's the Planetary Defense Officer at NASA's Planetary Defense Coordination Office. And we have Gerhard Rotzhagen, senior expert at the University of Oldenburg and chair of Same Page, the Space Mission Planning Advisory Group. We also have standing by our legal experts from the previous session. And let's get started. So we have heard about the potential risk that was announced by IWAN, and also heard about potential deflection disruption options, as well as the legal issues that would be involved with taking action. Gerhard, as chair of Same Page, you came up with these option, or I don't know if I can call them recommendations, but who would be next in line to make a decision what course of action will be taken? Who do you pass these options on to, especially given the large uncertainty on where it might hit or if it will hit at all?
Well, you start with a very different question. I mean, the experts for Same Page, in this case it was Brent Barbie, presented technical possibilities, and for this hypothetical threat PDC 2021 or 2021 PDC, it looks like there are not many options. Effectively, there are no options in the present situation. So therefore, the technical analysis only showed what in principle could have been done if we had something ready on the launch pad, more or less. And then there are open questions enough. So we could perhaps discuss if there would have been a different option, a realistic option, then what would be the way forward? And this maybe is not a question that I can answer. It is an open issue and perhaps something that can be discussed. So I noticed Alex seemed to have a little problem with his connection. I'm sure he will come back at any moment. And maybe I'll just pass it on to one of our legal experts, this question. Either Alyssa or Irmgard, what would you see as a way forward, just from your point of view, how a decision could be taken, if a decision has to be taken soon on this only possibility, assuming we have available a nuclear device on the launch pad, or as alternative, a reconnaissance mission? What would you suggest? Whom should we contact?
I would quickly say that, to me, rehearsal is the best policy. So the fact that today on this call you do have experts, legal experts, but also policymakers, the fact that this information is going out and that the information is starting to circulate this way will enable for quicker decision and more collaboration. But for more details, I would prefer to leave the floor to Irmgard. Yeah, thank you. Thank you very much. We depicted a little bit the institutional structure of how the UN works and so on. And IWAN and Same Page are technically reporting to the subcommittee of COPUOS. And then COPUOS reports to the General Assembly, and then the General Assembly can put the question in front of the Security Council. But we do not have the time here to follow this path. This would be the normal path, and you would. The General Assembly starts its session in September, so this is way too late. So probably we need to skip several of these steps, but still the role of IWAN and Same Page are key here. So these are really dedicated groups of people who have knowledge, who have the experience and can provide answers to questions. So probably in this case, the different steps, so subcommittee, main committee, COPUOS, General Assembly, would need to be skipped and just directly inform the Security Council. The Security Council then needs this information and should gather these people around to proceed
with decision making, and then that ultimately would there be the possibility and even authority to decide, and even make it legal and lawful, even to deviate from the treaties which Dave has depicted and described in this very, very critical situation of so little time, which is really, as I said, a challenge. But I'm glad that, and we see how glad we should be to have IWAN and SAMPAGE. No, so we and also this group here of people, Planetary Defense Conference participants and experts, which have developed expertise over the years, and do not only include the very powerful spacefaring nations with all the expertise, but also other groups and experts from different countries. So there is a way to inject considerations and arguments also a little bit from outside, from the expert world, outside the P5, which are then the Security Council so decisive. So I think in this path we could work forward. So together the experts of IWAN and SAMPAGE, and perhaps they can also get some other expertise from PDC conference participants to inform the decision makers in the Security Council.
Thank you, Irmgard. So I'm not sure if Alex is back. He still seems to have certain problems. Alex, maybe we could ask our experts from the space agencies. Perhaps Lindley, could you comment? What would you consider a potential way now to act in view of what results we have on the technical side?
Well, to take what Irmgard talked about and talk about the role of IWAN and SAMPAGE, it's not just when an event like this is discovered, an object like this is discovered, but we have with IWAN and SAMPAGE a ongoing responsibility to work with our space agencies, space institutes, to educate them on this problem, like we're doing now at this Planetary Defense Conference, and also to inform our governments, so our government leaders. So if we do get into a situation like this, we already have some basis upon which to build. And then, as suggested, you know, the P5 nations of the UN Security Council are then able to quickly gather the information and meet on what the proper solution, what the agreed international solution is to address the threat.
I think Alex is back. Maybe you take over again.
Yes, sorry, my computer decided to switch off for some reason, so I had to switch devices and improvise a little. I didn't catch the last question, so I hope I'm not repeating my question. But I heard it was about the decision-making process, and it would go to the Security Council. Assuming a mission would be approved, how would that be coordinated between the nations involved, and who would eventually pay for this?
If I might, just like a number of other missions, humanitarian missions, conflict de-escalation missions that are sponsored by the United Nations, it is a correlation of the willing. The nations that are willing to step up to address the problem are then, you know, given the charge by the United Nations to do so. But you know, with that collaboration, volunteering for such a collaboration, comes the responsibility, the burden to fund those operations. So I see addressing a impact threat as being no different than a number of other international missions which are undertaken. It's the process is essentially the same.
And if I might add, Lindley, and maybe that's a question for Irmgard, because I think one thing that is not the same is if something goes wrong, you're not only paying for it, but also legally liable. So I'm wondering if there might be a way to address that before the mission starts, just to have a sort of insurance.
Exactly. I totally agree. That's the difference between such a mission, a space mission, and an other humanitarian mission on the ground. So exactly, you do not only have the burden to carry the financial burden to finance the equipment and people, but also if something goes wrong, the launching state, and we have seen it's not only the territory of launch, but also those cooperating and procuring the launch are also liable. But I think then in the Security Council decision, there is room to provide in a paragraph, a provision, to change this. Because the Security Council can also change the strict liability regime of the Liability Convention. This is this unique power of the Security Council it has. It cannot do it in any situation and arbitrarily, whatever, but in this specific situation of a threat to Chapter 7, threat to international peace and security, and the Security Council probably would not have a big difficulty to define such a threat as a threat to international peace and security under Chapter 7, under Article 39. Then it has the power, and with this mandate in this situation, to provide that the strict liability regime is changed, is altered to in another way, and at the same time it could be considered, nevertheless, how victims nevertheless could be compensated, or how the compensation of victims should be organized. But it can do so. It can deviate. And it should not forget to do so if it issues a resolution, should not forget to do it, because otherwise the launching states would be liable.
Now, well, those participating states need to remind the Security Council we need that liability release.
Yeah.
That's a good thing to keep in mind. My next question goes to Brent. So if we would launch or mount a deflection or disruption mission, how can we make sure that it succeeds?
Well, so a lot of that goes into the design of the mission. When we design robotic science missions to send them out to interplanetary space, we go through a lot of design cycles where we look for potential faults in the system, and we add layers of redundancy and do redesign to make the system very fault tolerant. So one of the tasks set before us in crafting planetary defense mission response plans is to perform that same kind of analysis and to design systems that are robust to faults, and look for points of failure and add redundancy where needed. So the other point is something that was raised by one of the other audience members earlier today, which is that certainly when possible for a planetary defense mission when the stakes are high, we would endeavor to launch not just a single spacecraft, but in fact, even a redundant copy. So that way, if something were to go wrong, we would have a second spacecraft available as a fail-safe in a situation like that.
Okay. So far, we've been assuming that the Security Council would approve the use of the nuclear explosive device. I want to switch scenario a little bit and pose the question: if there would not be an agreement to use such a device, and there's nothing could do in that sense. How would that be communicated to the public in the affected area?
Are you asking how the public would be informed that, you know, there's a technological solution available, but a policy decision has been made to forego it? Are you asking how that would be communicated to the public?
Yes, that was where I was aiming at. And I'm not sure who might be willing to pick this question.
Mm-hmm.
That's kind of a hypothetical here, Alex. In the situation we're in with this scenario, there really is no in-space mitigation action that can be credibly taken. Maybe something to be cobbled together, but I would dispute the credibility of it. The best action here with this scenario, I think, is to get the most information that we can on the object, its orbit, its size and characterization, to provide the best information available to the emergency response community. It might be possible, more possible, to launch some kind of flyby characterization mission than any kind of deflection and disruption mission because of the technical problems involved, or other order of magnitude above just doing a flyby characterization mission. But direct to your question, I mean, again, this falls to the governments involved in, negotiations between the governments, the activities, discussions at the Security Council. They bring in and inform the governments that could be affected by this, still be affected by this impact, and work together to get the best information out that is available. And again, this is where the roles of I1 and same page to a lesser extent in this scenario, I think, are important, that we don't just show up when the threat is discovered. We are working continuously to develop better understanding of the nature of this natural disaster that is not as well known because it's so rare, but with the additional information and the work that's been done over the last 2 or 3 decades, it's becoming better and better known, and better and better understood by the emergency response community, as we're going to see here later in the rest of this conference.
Yeah, and indeed, that is on day 4, I believe. You bring up a good point with the disaster managers. When, and maybe I'll ask Detlef for this one, when would be a good point in time to bring in the disaster managers to the discussion, Detlef?
This is basically what Lindley was saying. As space agency, we will communicate with the disaster response agencies. We would not directly communicate with the public. It's not up to the space agency to decide whether, a city needs to be evacuated or something. What we would be doing is we would coordinate that with the response agencies very early on. And we will hear more about that, I think, tomorrow in the sessions about response, where we involve the response agencies in this conference.
Precisely, and my short answer to that is as soon as we know.
I like that answer. That's a good one. I will pick up a question or two from the audience. So I think this is for Irmgard again. It's actually coming from Gerhard. So assuming there's a spacecraft with a nuclear explosive device ready, and it will be launched against the law, and it is successful with the mitigation, would there be any legal implications?
Yes, certainly. The state would act unlawfully, and then it could try to argue that perhaps it was a state of necessity, which was alluded to in the previous question and answer session. So one single state would then have to try first to explain, well, there was a state of necessity. It was the only means to combat a threat to an essential interest of the state. And this would be the argument. But the risk is that other countries would not accept it and would still think it was a breach of international law in various aspects, namely the use of nuclear explosive devices and let them explode in outer space in contravention to the Limited Test Ban Treaty, for example. And so if it is successful, I think, Gerhard said, if there is, and you assume that there is no damage caused, so on the contrary, there is sort of damage prevented, this would not change the unlawfulness in a way, so that the state would have a hard time in a way to be always confronted with this allegation of unlawfulness. But if fortunately no damage occurred, no one has to pay compensation, and otherwise there will be no consequences and financial ways other than that state has violated the treaty. And treaty violations are a problem in such, because if one state starts violating a treaty, other states may follow, and then in different circumstances perhaps. So then they will find other excuses in other circumstances why they use then nuclear explosive devices. So this is a dangerous start of a possible chain of violations of for example, the Limited Test Ban Treaty. So it's a high risk of a government to take a decision unilaterally without approval by the Security Council.
You mentioned nation states and governments. What if a commercial company would be involved?
It is the same because under the space law regime, states are responsible, and this is the term responsibility. I tried to make it clear that there is a difference between responsibility and liability, but anyway responsible for their national activities in outer space. And what is the national activity in outer space? And this includes activities by non-governmental entities. And that is why the countries have enacted national space laws, and no private actor is allowed to perform space activities without permission of the home government and home state, because ultimately the home state is responsible under international law.
I have one more legal question. So we don't know yet where and if even the asteroid will hit us. And we have been talking about the Security Council playing a major role in launching any mission, especially if it's involving a nuclear explosive device. What if the region that would be affected is not represented in the Security Council? Do you think there are any implications that the nations are more like not necessarily wanting to address it in that case? I can imagine if a member of the Security Council would be directly affected, they would push for taking action, while a different country might not have that advocacy.
Yes, the system of here works in the United Nations as a system of representation of the 193 member countries. They are represented in matters of international peace and security, particularly in the Security Council. And it is not only so that we have the 5 permanent members, but we have 10 other members, and they are elected on the basis of regional representation. So you can identify for each state that there is his or her representation in the Security Council somehow as a regional representative, because it has been government has been elected for a period of 2 years. And so there is this at least regional representation. And so the views of this particular country can be presented by that region, for example, a regional representative, but also there is a possibility to invite the affected country to the Security Council. There is a provision in the charter to invite affected countries to make their case, to present their case to the Security Council, but they have no right to vote or anything, but there is a possibility to be heard in front of the Security Council.
Okay, thank you. I'm going back to some questions from the audience. Is there a boundary for Earth defense? So if an asteroid, and if we could predict, obviously, its orbit well enough, threatens some of our assets in orbit, like orbital or satellite constellations, would that be something that is taken into consideration, or because unless there are humans involved, it's filed under collateral damage?
To clarify the question, Alex, is the question about if a important orbital asset was being threatened by being struck by an incoming asteroid that would miss the Earth but damage or destroy the satellite or the spacecraft, would that warrant a mitigation mission? Is that what you're asking?
That's my question, but now since you're asking, I think the original question was if we can maybe add that as a second point, whether using a nuclear device in orbit would have any collateral effects on our satellite constellations.
Yeah. So that is a different question, right? So to clarify, the mitigation mission concepts that use nuclear devices that we're considering all involve detonating the nuclear device when it's very far away from the Earth. So the device would be detonated, generally hundreds of millions of kilometers away from the Earth, and it would not have any effects on the Earth whatsoever. Now, there have been some papers that have looked at the possibility of sort of a suborbital intercept of an incoming asteroid. So when it's only a few hundred kilometers above the Earth's surface, and trying to do a nuclear intercept there. If that sort of concept were pursued, then yes, that would have the possibility of causing electromagnetic pulse and things like that. So that would be a different scenario. But to be clear, the scenarios that we have been considering in our work to date have involved detonating the nuclear device when it's very far away from the Earth, and it would not threaten the Earth at all.
Only on launch. So this is my question in your previous presentation. So if the launch, how could a safe launch be secured? Because there is the important threat on Earth and outer space, probably not to humans and so, but the launch risk is significant. And you said, well, there are intercontinental ballistic missiles and so on, and they have been tested, and so you rely on this technology.
Yeah, I mean, It's important. The safety is very important, and that would be my recommendation as the starting point for assessing it. Would be to look at heritage systems that have a long history of the capacity for safe launch operations, and start there, because that would provide good guidance. But it's something yet to be assessed.
Well, there is a whole regime for safety for launching of nuclear devices, because several interplanetary spacecraft have been launched with RTGs on board, and most recently Mars Perseverance. And so that's a rigorous regime for safety that both in the U.S. and other countries already have set up, and so that would be followed probably to the nth degree in the case of an NED.
Yeah, I agree with that.
Just looking through if we have any more questions from the audience. I don't see any, so let me invite the audience to, if you have more questions, please put them in the Q&A. In the meantime, and I think there's again a legal question for Irmgard. Sorry. Yes. Having this scenario with an asteroid potentially hitting the Earth, do you think that would maybe trigger some discussions within the UN system to look at the possibility of using a nuclear device for planetary defense? Even if it wouldn't hit, at least it gives us a warning, so we have some time to prepare for the next time.
I think it has been said before that this would not be the first option, or one of the options you would equally consider if you had enough time. So time plays here a crucial role. And as understood, the more time you have, the less likely is any discussion on nuclear devices. And all governments and space agencies involved work hard now and to prevent the need for a nuclear device. If you detect an asteroid long before, you have numerous different options, and this is certainly preferred. And that's why I think that a lot of money is now also invested by various space agencies exactly to early detect and characterize and know more about NEOs. And it's really impressive how the success is here visible. Every year there are more and more objects detected and characterized. And so if these efforts are successful and continuing that pace, it should always be, almost be excluded that there is a scenario that you have only half a year to decide, which we have here. So I think it would really be a very, very emergency scenario, which everyone tries to avoid, and really does not lightly take into consideration as another technical option. It's very separate from the other technical and options which space agencies would prefer. This is my understanding. So we have really only in this particular scenario the 6 months where very unluckily that's really such a surprise. So I think the work space agencies are now doing is amazing and helps a lot to avoid that.
And it is true that that would be the case for short warning scenarios. And indeed, the more we discover early, the better, or the less of those scenarios we will encounter.
Yeah. If I might add, the best solution to the scenario is not to get into it in the first place. Now, maybe that sounds like I don't accept the no-win scenario. But that's really the strategy that needs to be pursued. An impact of what we're looking at here is a very rare event. That doesn't mean it couldn't happen in 6 months based on what we know in the population right now. And so that's why it is so important that we have a strategy that develops capabilities to find these objects as far in advance as possible so that we do have the time to address them. And that's entirely within our technology to do right now. We just need to apply the resources to it. It's very likely, even with this object, that it was accessible, visible to telescopes in the past. I suspect in scenario world right now, they are scrambling, going through all the image archives to see what they can find from previous apparitions of this object to be able to eliminate some of the uncertainty in the orbit. And but if we'd had the capability back whenever that was to better detect and track these objects, then we would have the 6 years, 8 years, whatever that time interval was. And so that's a real strategy to pursue. We have the technology to do that. It's not overly expensive in the case of space missions world. And we just need to apply the will and the resources to get that kind of capability into space to be able to do that.
Yeah, I absolutely agree with what Lindley said. Early detection is absolutely key and very doable with our current technology. The only thing I would add there is that the work that's being undertaken now in the legal sphere to pave the way for a nuclear response, should it be necessary, is still very important. And so it's important for that work to continue so that we're not confronted with the need to act, but then the inability to act effectively because we didn't think ahead and lay the groundwork. So that work should absolutely continue so that if we are caught unawares, which can never be ruled out, we're as well prepared as possible to respond as effectively as possible.
And in such a case, how would the, so if we had more time to prepare a defense activity, how would the space agencies coordinate among each other? Is it something that's happening within same page, or is it more in a bilateral or coalition of the willing group?
Gerhard, do you have comments on this from the?
Well, I would, as part, let's say, as chair of Same Page, I would say Same Page will provide potential technical options. I mean, in this case, we just talked about the nuclear device as only feasible option. But if we have more time, then there could be a kinetic impact and other slow push or pull methods. You would have many more options. And of course, then the Same Page would list these options, and it also would point out perhaps you need a coordination, or you need resources or launchers from different space agencies, and it would just point this out, and then this would be forwarded, as was explained before, to the member states of Same Page via the UN, also to space agencies, and then it's more or less a question to them. How do they coordinate? It's also one of the open questions, but perhaps we could put this question to Detlef and Lindley as two representatives. How would they see it if Same Page comes up with a solution requiring a coordinated action?
Lindley, you start.
You tossed it to me. Is that what? I didn't quite hear you, Detlef. Well, sure. That's what Same Page was set up for, to specifically address the issue of collaborative efforts for in-space mitigation missions. The IATA mission, which we heard about yesterday, or IATA collaboration, which we heard about yesterday, the asteroid impact deflection assessment, although the origins of that preceded formation of the Same Page. It is the kind of thing that Same Page was set up for, was to foster those kinds of collaborative efforts space agencies will work together on developing and testing the technologies and techniques that can be used for deflection of an object while still in space. So I just see that as more and more agencies become part of same page, that continuing and growing. So we're doing DART, HERA now, and Aussie is involved with the Lucia Cube, and other nations as well, with instruments and scientists on that team. That will be conducted here in the 20s. And so same page should be looking at what's next. What do we do after this kinetic impactor test? Another kinetic impact mission, or do we test some of the other techniques like gravity tractor, or some of the other ideas on ablation of asteroids? Over to you, Detlef.
Yeah, I think the way I see it is that same page is the platform where we start discussions. The A in same page stands for advisory, so it's not a decision body, as we keep reminding people. However, actually at the last same page meeting, I was approached by colleagues that said, hey, can we discuss this or that collaboration? I would hope that at some point same page has like scenarios in the drawer where we can say, okay, with this threat that we have, this is the collaboration that could work. But in the end, it's a proposal by same page. But of course, with us all being part of the group, we can then go to our respective, in my case, the Director General of ESA, and I can say, look, we could be doing this. Can we not decide to talk to that and that space agency? And that's how we would then set up a collaboration. So the final decision is always with our agency management, but it will be definitely strongly influenced by whatever same advising.
Great. Thanks, Detlef. Thanks, Lindley. I go back to questions from the audience. Here's one from John Marks. Why do we not have preparation for short warning impactor when we have massive preparation for a threat by an earthly adversary? I guess it's maybe more for the politicians than for the...
Well, let me take a cut at it. Threats from other peoples, let me say, has been the history of human civilization. So we've known of that threat and understood that defense was important. The threat from celestial objects, impact threat, has only really begun to be understood here in the last 3, maybe 4 decades. First by the scientists, of course, and the politicians. Leadership started to get into the act into the 90s, kind of driven by the impact of Shoemaker-Levy 9 on Jupiter. Kind of brought it to light. So now an understanding has been created and is growing, and so the resources that are required are starting to be applied in this direction as well. It's just a matter of history, and it takes a little time, but we're headed in that direction.
Here's a question from Rob Seaman. During the 6 months while 2021 PDC approaches, there would be many other close approaches of small asteroids. The public would likely overplay all of those and perhaps underplay the threat of 2021 PDC as a result of crying wolf. Do you think that's a possibility, and how should the NEO community respond to that?
Alex, I would be skeptical of this because the upcoming close approaches that are known, which would be the ones that would be at issue here, are well published online. You know, at NASA, we provide, you know, close approach tables that show upcoming close approaches so that they're you know, known events. And for those events, it can also be shown on the same website that for those, the impact probability is you know, not alarming. And so PDC 21, the hypothetical object in this scenario, would stand out significantly from other coincidental close approaches during the same time interval. Lindley, do you have other thoughts on that?
Well, in the age of social media, I think anything is probably possible, and the information that we publish on the web pages is only as good as the people that will go look at it, you know, and really try to find out what the facts really are. I would not dismiss that this could be a problem. The only thing that can be done to counteract it is put out the correct information as quickly as we can, as often as we can. You know, not only when we get in a scenario like this, but as you point out, you know, this is a continuous activity of both the Center for NEO Studies here in the U.S. and the ESA's Near Earth Object Coordination Center, publishing all the close approaches that we detect, so that people can be informed of what is continuously going on, and so an event like this, should it occur, isn't completely you know, out of left field.
Thanks, Lindley. There's a question: to what extent does the collaboration also include Russia and China? This could be important for a future Security Council decision.
Maybe I can answer this. So Same Page has right now 19 members, so space agencies and space offices, and both Russia and China are members of Same Page. So they are already involved, and if some plan is brought forward by Same Page, they should be involved in the coordination and discussion activities. And we expect more members to join soon. And so we try to get a broad consensus. Same Page works by consensus. And of course, I understand it's good if we have those that are important for a potential decision in this Security Council, if they are also member of Same Page, and if a proposal comes from Same Page, they have been involved in supporting and preparing it. That's very clear.
Gerhard, Boris Shustov is speaking. I had contacts to authorities of Roscosmos. I asked them why they are so passive in the SM Page, and I was told that next year, next meeting, they will be participate in more, how to say it, in more active manner. Okay, so that's it. It was a promise of the head of Roscosmos. Thanks.
Thank you very much for this comment. That's good news. Perhaps I could add something that Same Page is also considering to try some exercises, not quite as involved as a 2021 PDC, but to see how a coordination and the cooperation and the flow of information could really work in case of a real threat that is within the criteria and thresholds where Same Page gets into action. Maybe as a reminder, Same Page has the criteria that it will only start an assessment if there is an object roughly larger than 50 meters and has an impact probability larger than 1% within 50 years. So many of these close approaches are much, much smaller and than 50 meters, and so Same Page would not get into action. It only looks at bigger objects where it might be worth to perform a space mission. And as we have seen for this exercise case, there may be no realistic option right now with our present technical developments. And this is not unrealistic, but Same page just assesses what is possible, and in some cases also what would have to be done to make it possible to start a space mission for deflection. So same page is carrying on, and of course we hope it makes progress and learns more and fosters more coordination and cooperation.
And I like the idea of same page conducting some exercises, as I know that IWAN is doing the same for observing or trying to coordinate observation campaigns. So that certainly be nice to get some lessons learned. I think we have time for one more question. So in the current scenario, how would you deal, and that's probably for Lindley, how would you deal with the political and public optics of a possible impact in October when DART, a planetary defense mission technology demonstrator, is basically already on the launch pad?
Well, DART isn't on the launch pad yet. In fact, it does not ship to the launch pad until September. But I mean, one could say, you know, if this was really a real world right now, is there somewhere we could rush DART to the launch pad and that kind of thing? Not out of the realm of possibilities, but the fact of the matter is the DART impactor is not massive enough to do anything. For at least what we think the nominal size of this object is, to change its velocity enough that it would make it a miss instead of a hit. I make a pretty good crater on it, but it's not enough time for the change in velocity to accumulate enough that it would be a miss instead of a hit. If it is indeed on an impact trajectory, but we don't know that yet. So that's why we need to get to the next INJECT.
No, exactly. That's the perfect segue. First of all, I would like to thank all panelists and all experts, legal experts, for participating and supporting this panel. And I'll hand it over now to Paul, who has the next exercise INJECT for us. So let's see what happens.
Thank you, Alex. Let me share my screen. Let's see what we've got here. Are you seeing the screen? Oh. Can you see the screen?
Yeah, good.
Yes, we are, Paul.
Very good. Okay.
Presentation mode, though.
All right. Thank you. INJECT number 2. The scenario date has advanced only 1 week, and it's my unfortunate position to report that the asteroid has been confirmed to be on an impact trajectory with the Earth. The impact site that we compute using the latest data is in Europe and North Africa. I will show you that shortly, but this is the news item, and this just happened in the last few days. Let me explain what happened. Newly uncovered observations of the asteroid have established that the asteroid will indeed impact, and with 100% certainty. The new data are actually pre-covery observations. Lindley gave a little foreshadowing of this in the previous panel session. Pre-covery observations are pre-discovery observations that are dug out of archival images. In this case, archival images from 2014, 7 years ago, and also by Pan-STARRS, the telescope that discovered this object. The way it works is as follows. Observers would notice that the object must have made a distant passage by the Earth in 2014 because we can predict the orbit backwards to that time era. And they can predict the region of the sky where the asteroid should have been back then. Now, a search through the archival images then would identify which of them should contain the asteroid, and it's a limited series of images. And then those images would be searched. Now, the asteroid was in fact too faint to be discovered in 2014, but shifting and stacking of these images with the known motion of the asteroid back then has resulted in detections. So this is what we call precovery detections. Now, we had some precoveries just in the days before discovery this year, but this is a technique which can be used to extract very important information from years ago. Now, lengthened to 7 years, the new data arc, which we're using to produce the orbit, is now much more accurate because, as I said in my previous talk, the quality and accuracy of an orbit depends most critically on the length of time over which you have observations. So now this has led to a much smaller predicted uncertainty region when the Earth passes through the asteroid orbit in October. And in fact, now the entire uncertainty region now intersects the Earth. So that means that the impact is 100% certain. Now, the general region of where the asteroid will impact, I'll show on the next slide, but we can now predict that because now the whole uncertainty region can be predicted, and where it hits the Earth can be predicted. The second last point here is that the asteroid size and shape and the energy of the impact are essentially unchanged. They're still highly uncertain. So the update today is really only on the orbit, and we still have the same uncertainty on the size. The bottom line there gives the URL, which has just come live, that talks about and gives all the details of this update. This is the predicted impact location as of May the 2nd in the scenario. The impact date, of course, is the same. The large red region now shows impact probability with 3 different contours. The probability that the impact will occur in the entire region is 99%. Inside the middle contour, it's 87%, and inside the central red region, it's 40%. My final slide alludes back to what Lindley was saying a little bit earlier, and I'll explain that in a minute. We have on our website a deflection app, and the URL is given at the top of this slide. And we have loaded the asteroid trajectory for PDC-21 into that app. And we've loaded it for 30 full years. So you can now go into the app and actually try to deflect the asteroid. You'll find that it's very difficult, and this is with kinetic impactors, I might add. You'll find that it's very difficult with only 6 months to deflect the asteroid. There really are no good options with known launch vehicles for kinetic impactors. However, if this asteroid had been discovered 7 years ago, and we had been tracking it, and we knew that it would impact, we would have had much time to deflect the asteroid with the kinetic impactors. And you can see that by trying out different deflection dates and different launch vehicles in this app. And I'll end there.
As we get started with this second part of NEO Discovery, I want to again recognize and thank my co-chair, Alan Harris of the US, who really worked hard on session planning and handled just about all the notification and reminder emails, which I appreciated. Our deal was that he would handle notifications and I would handle the WebEx. And thank you also to Luca Conversi for serving as a backup co-chair should we have difficulties. And again, as I said in the first part earlier today, the first requirement of all the activities in planetary defense is the ability to discover NEOs. You can't mitigate a threatening asteroid if you don't even know that it exists. And this was brought up in the exercise panel just now. We don't even want to find ourselves in the scenario position. So we had a very productive first half of the oral session 5 NEO Discovery earlier today. And as we start the second half, again, I would like to remind you to view the e-posters and e-lightning talks related to this NEO Discovery session. And now for session 5B, NEO Discovery, with our lineup of 5 oral presenters. And then all will participate in a panel for questions and discussions during the remainder of the hour. Each speaker will have 7 minutes for their oral presentation, and I will warn at the 1-minute mark. And so our first speaker is Dr. Lynn Jones, research scientist at the Rubin Observatory, the University of Washington Department of Astronomy, and the Drac Institute. And the title is Discovering and Characterizing Near-Earth Objects with Versi Rubin Observatory's Legacy Survey of Space and Time, LSST. Dr. Jones.
Thank you. And good morning or from here, I guess it's good evening where you guys are. So I'm Lynn Jones. Thank you for the opportunity to talk today at the Planetary Defense Conference. I'll be giving an overview and an update on the Near Earth Object Discovery and Characterization capability of the Rubin Observatory's Legacy Survey of Space and Time. Next slide, please. So in overview, Rubin Observatory is a big telescope, an 8.4 meter diameter telescope with a very big field of view, 9.6 square degrees, and also has data processing pipelines to generate exquisitely calibrated photometric and astrometric catalogs for each image. The LSST itself is a survey that will be carried out with Rubin Observatory and consists of 10 years of images in UTRI-ZY filters. This legacy survey has 4 primary science drivers. Inventorying small bodies throughout the solar system is an important component of these science drivers. The LSST survey footprint will concentrate primarily on the southern sky, as Rubin is located in Chile with some extensions to the north, primarily around the ecliptic. On the upper left there is an image of our under construction telescope, and this was taken earlier this year. Next slide, please. So in terms of planetary defense, the LSST will discover a large number of near-Earth objects and potentially hazardous asteroids. With the current baseline survey strategy, after 10 years, we expect LSST to discover 50 to 100,000 NEOs larger than H of 25. In the grand total, including smaller objects, is likely to be a factor of 2 more. However, there is a certain amount of uncertainty in that. Part of that is coming from the fact that we don't really know what the underlying NEO population is like, especially at these small sizes. But there's also uncertainties in the survey strategy itself, small details and linking requirements and weather conditions. So this uncertainty has the greatest impact on the smallest objects, and of course the smallest objects are the most numerous. The number of expected NEOs as a function of H magnitude is shown in the plot to the upper right. We expect to discover between 62 to 67% of the NEOs larger than H of 22, and this is consistent with prior work. Including other ongoing surveys increases the overall total somewhat, and then adding other next generation surveys such as NEO Surveyor can raise the final completeness to 90% for H less than 22. Next slide, please. So unfortunately, COVID has led to a delay in the start of operations. We now expect to start operations no sooner than fall of 2023. So this is a slip of about a year. However, there is still a lot of exciting progress to report. So at the bottom left, you can see an image of a photograph of Vera Rubin, which has been taken with the actual camera put together. Next to that is a photograph of one of the camera filters, which has been delivered for testing and mounting in the camera. And on the right is the telescope dome with the top end assembly being lifted into the dome in early March. And there's an amazing video of that lift at that link on the slide. Next slide, please. We're also working on defining the details of the survey strategy. The timeline for that in some detail is on the right. We are currently working through cadence notes, which were submitted by the community to the Survey Cadence Optimization Committee, the SEOC, in response to a large series of survey simulations. 2022 will be spent fine-tuning an updated survey strategy plan and incorporating early science goals. At the end of 2022, an initial survey strategy for the LSST will be announced. Aspects of this plan will be tested in commissioning through 2023, and then operations will start in late 2023. Next slide, please. So we've completed hundreds of simulations, variations on the survey strategy, and continue to investigate new options as well as improve the fidelity of the observatory model and weather conditions. Most changes to the survey strategy do not significantly impact the NEO discovery rates or characterization metrics, such as the fraction of the population which receive observations sufficient for light curve inversion or color measurements in 2, 3, 4, 5 filters. And you can see that in that very messy plot at the bottom. Next slide, please. However, one option we are investigating is the option of adding a mini survey with a series of short 1-second exposures during twilight. This would be specifically in place for NEO detection. So here we would spend some time between nautical and astronomical twilight to do triplets of 1-second visits in RIZ filters at solar elongations less than 65 degrees. This enables the discovery of VITIRAs, interior to Venus orbit objects, and it improves discovery of the largest virtual impactors. These can be seen in the bottom two plots below, which show cumulative completeness as a function of H magnitude for these various twilight NEO survey simulations. The decision on whether to incorporate this mini-survey will be part of the overall decision on survey strategy for the SELC. Next slide, please. So we are obtaining hundreds of observations in multiple filters for the largest NEOs, and this is shown at the top right. Using sparse light curve methods, this enables the measurement of colors, rotation periods, phase curves, and even shapes. In addition, these frequent observations will provide the opportunity for detection of activity due to volatiles or collisions. Next slide, please. I wanted to go through very quickly the data products which are relevant to planetary defense that will come from the LSST catalogs. These include 60-second alerts and daily catalogs. Alerts are issued 60 seconds after every image and contain measurements of all of the moving sources in each image. The daily catalogs are an orbit database which is updated each day with newly linked objects. There's also a yearly data release catalog available, which is built with only LSST detections. So this will be excellent for building debiased population models with well-understood selection effects. The alerts will include any observations of known asteroids. Tracks or tracklets are not required for objects with accurate ephemeris predictions. And trailed source fitting will also allow quick identification of trailed sources, known or unknown in alerts. A brief summary of these data products is available at the link shown. The development of the data management pipelines is ongoing. And so recently there was an integration test with the MPC, which was very successful. And we're also working on testing a new linking method, HelioLink 3D, which shows significant promise to link detections in a heliocentric space, permitting the generation of high purity and high completeness tracks. Next slide, please. So in summary, Ribbon Observatory's LSST will be a significant resource for planetary defense and the discovery and study of NEOs. We anticipate discovering between 50 to 100,000 NEOs with H less than 25. Construction of the observatory and pipelines is ongoing and the survey strategy is being refined. And I just wanted to take a second to highlight there's 2 lightning talks in the NEO characterization session by Edlu and Ivizic, which add details on the first year of LSST discoveries and the possibility of size measurements accurate to 20 to 25% from optical colors. And finally, the LSST science collaboration is an additional great resource. So thank you very much.
All right, thank you. Our next talk is being given by Professor Amy Meinzer of the University of Arizona. The title is NEO Detection and the Future of Planetary Defense. Professor Meinzer. I think you're on mute. Oh, still not hearing you. Yeah, we're not hearing, even without the headset maybe? Or just unplug the... Oh, no, we're not hearing. How about let's try, we'll go to the next talk and we'll come back, see if we can solve the difficulty or dial in. All right, thank you. If you wouldn't mind moving to the next slide set, thank you very much to our organizers. I'm going to move to the next talk. I hope she's all ready. Now I'd like to introduce Dr. Federica Spato, astronomer at the Minor Planet Center, Harvard-Smithsonian, speaking on the new Minor Planet Center NEO confirmation page, improvements and results. Dr. Spato, sorry to catch you off guard.
Hi, no worries. Thank you, Kelly. So yeah, I'm Federica Spato. I work for the Minor Planet Center at the Center for Astrophysics, Harvard-Smithsonian. I'm going to talk about recent improvements and developments that we made at the Minor Planet Center and I'm going to focus especially on the NEO confirmation page. So next slide, please. Okay, so for those of you, I don't think there are a lot of you that are not familiar with the NEO confirmation page. This is a screenshot that I took a few days before sending the presentation, and this is how it looks like. So the Minor Planet Center is really aware of the importance of the INEO confirmation page, especially in the in what concern helping and facilitating a rapid follow-up after INEO is discovered. And as you can see on the histogram on the bottom right, we have the number of observations and the number of objects that were currently on the INEO CP when I got the screenshot. And a lot of those objects have a really short arc. So that's why I'm going to explain a little bit what kind of algorithm we used. But before doing that, next slide, please. Let's start with some recent improvements that we developed at the Minor Planet Center. The first one is that we are going to use an ORFIT version that we are developing, and we are collaborating with the whole ORFIT consortium. And the main, I mean, there are a lot of improvements in doing that, but some of the main ones are the use of the orbital elements uncertainties and the use of a new weighting scheme, which goes along the use of ADAS. So I'm not going to explain in detail the weighting scheme, but the idea is that we analyze all the available post-fit residuals and we group them using by the observatories, the year of the observation, the stellar catalog, and the magnitude class. So we divided the observations into four different magnitude class, 5 if you include the objects with the observations with no magnitudes. So the plot on the right is a simplification of what it might be the error model. So these are just the weights that we're going to use for the T08 according to a fixed magnitude class. In this case, it's just, those are the objects with magnitude between 17.5 and 20. So an explanation of the color code. The color code is the year of the observation. The size of the point depends on how many observations we use to produce the statistics. So just a few points, since I'm also team of the Gaia mission, I'm really pleased when I see that observatory started using Gaia DR1, and then they moved to Gaia DR2, and then they will move to Gaia DR3, because as you can see, this really improves a lot the performances of the observatory. Next slide, please. Just to give you an idea on how the error model looks like, so the first screenshot, it's our weighting scheme that we're using right now. So we can divide all the, I mean, we can use all the different information that we have with the year, observatory code, stellar catalog, and then we have the RMS. This is something that it's really useful because we also starting using ADAS at MPC. So I really recommend you to submit observations in ADAS and to make studies on the RMS from the observatory, because this is, for example, still an example from T08, in which you have the RMS that they sent in the middle plot and the RMS that we're actually using for the objects with the same year, I mean, close year, same catalog code, and same magnitude class. And in this case, the weights that they give us are really close to the weights we are using, which is good. So just a note, let's say that we trust the observers when they send bad residuals, so, which means that if the RMS of the residuals of the sent residuals is less the RMS that is computed, we are going to use the RMS that we computed with the error model. Otherwise, we use the RMS that has been sent, because it means that there were some kind of bad conditions for the observations. Next slide, please. So I put a diagram, a schema, diagram flow of what the code looked like. Can you move on of 2 slides, please? There should be 2. Oh no, okay, sorry. You can go back to the other one. There's something that went wrong, but that's fine. So the idea is that there's supposed to be a red box around the second part. So the first part, the pink one, represent, I mean, the NEOCP code that we developed contains more than just the NEOCP. So we're able to deal with natural satellites. It's better able to deal with TNOs, and it also contains a huge part which is based on which is done for the NEOCP itself. there are a few points that I wanted to show you with this diagram flow, and is that we want to have one single code as much as we can, that it's easy to deal and that is mostly automatic. So we don't want to have a lot of manual intervention, so we can have less errors than expected. And the other thing is that we want a fast code so that we can post results and so help with the follow-up as soon as we can. And that's why when we can, we try to compute a nominal orbit instead of using the systematic ranging. So what I didn't say is that the theory, which is at the base of this code, is basically the systematic ranging when the arc is really short. Otherwise, we try with a different orbit preliminary IOD, so initial orbit determination algorithms. And then we also compute the variant orbits to give an idea on how it looks like, both for the orbital elements and on the sky. Next slide, please.
1 minute.
Thank you. So this is what we have. We try to analyze 3 possible options for the nominal solution. So this is how it looks like. We have orbit with the minimum RMS or other kind of orbits. So we are testing all these different orbits to give you the best nominal orbit that we can. Next slide, please. And as has been mentioned before, what we have, we did this very successful exercise with the LSST observatory. And the idea is that we wanted to demonstrate that the MPC is able to ingest multiple nights of LSST data. And also we wanted to test our new software that performed really well. If you look at the plot on the right, in which you have the color crosses are the orbits, the simulated orbits from the LSST, and the black points are all the orbits that we found without knowing the real solution. So next slide, please. I will leave you with the conclusion and some near future plans. So as I said, we want to work on the NEOCP. We are testing the new software, and this will lead to have a new NEOCP page. We will produce and publish orbits and residuals using RFIT. And then I think a lot of you already saw that, but we also using Jira. So please use Jira to submit requests and suggestions. And then we also start plugging to the artificial object. It will be public starting from May, and I can post everyone so the editorial that came out. Thank you very much.
All right, thank you. Let me ask Amy, can we hear your audio at this point?
Sure. How does that work? Can you hear me?
It sounds so much better, yes.
Great. Thanks.
So if we could move the slides back to Professor Meinzer's presentation. She'll present on NEO detection and the future of planetary defense.
Great. Thanks, Kelly. Next slide, please. Nothing like a little WebEx fun to get everybody going here. Okay, so from my perspective, there are just a couple critical questions we would really like to know about the near-Earth objects. First of all, we'd like to know when the next major impact might occur, and we'd like to know how bad it might be. There's quite a quote here from Michael Bloomberg that I think Kelly kind of said, which is, if you can't measure it, you can't manage it, and you can't do anything about it. So we want to find out when and how bad. The when part comes from finding the objects and getting good orbits, good enough at least that we can predict where they're going to go reliably. And the how bad part really boils down to measuring kinetic energy, which of course scales very strongly with the diameter. In fact, is the diameter cubed. Linearly with density, velocity squared. Of course, we get the velocity from the orbit. And the diameter, though, that is really particularly important to measure. So if we go to the next slide, we can talk a little more here. So what have we learned so far? Well, we have an existing space infrared telescope called NEOWISE. My colleague Joe Massaro is going to tell you a little more about that. But one of the things we have learned is that if you have good infrared measurements, that's just a modest number of them actually, that more or less span a rotational light curve, depending on the exact set of wavelengths that you have, you can measure the diameter to within about 10 or 20%. This is because asteroid fluxes consist of both a reflected light portion as well as an emitted portion. And the reflected portion there you can see in the box scales linearly with the bond albedo, whereas the emitted light scales as 1 minus the bond albedo. So that is a little less sensitive to variations in albedo. So something we've learned from NEOWISE, we can spot the dark asteroids as well as the bright ones, and we can get their sizes quickly. As soon as we have a measurement and an orbit, we can calculate the diameter. If we also have a visible light point, we can now calculate albedo. And that's important because it correlates with the density and the composition. Not a perfect correlation, of course, but it gives you some information. If you only have single visible light measurements at one wavelength, the diameter errors are much more uncertain. It's about roughly a factor of 2. And of course, one of the great things about surveying from a space telescope is it's very consistent. We don't have weather or seeing or anything like that. And we have a survey that is equally sensitive to both the bright and the dark objects, more or less. Next slide, please. So just taking a look at what we've learned when we look at the sample of asteroids that are selected based on their thermal infrared fluxes, what we find is that roughly a third, or about 30% of the population, are very, very dark, like Ryugu and Bennu, just a few percent albedo. What that means is in terms of reaching that 90% completion limit for 140 meter and larger objects, is that if we're going to survey, we need to actually target H of 23 instead of H of 22 magnitudes. In other words, finding that last chunk of the dark population is pretty hard to do because they're just intrinsically quite faint. And so we need a system that can find the dark objects as well as the bright ones. Next slide. And this is just yet another way of looking at this. These are data from NEOWISE. When we make the selection in the left-hand plot based on the 12 micron flux, in other words, the thermal flux, and we plot albedo versus diameter, what we see is that it's a relatively consistent ratio of a pretty large span of sizes. In other words, there really is a population of, kind of few 100-meter class dark NEOs out there. And on the right-hand side, you can see that the NEOWISE discoveries, in other words, discoveries made based on thermal and infrared fluxes, tend to be dark, as opposed to the cyan points, which are near-Earth objects discovered by other surveys that are operating at visible light wavelengths. So next slide. So we think there's a bit of a challenge in finding that last bit of the dark NEOs that are out there. To that end, we've proposed a new mission, the NEO Surveyor, and that is because NEOWISE is kind of not going to last forever. And we've been very lucky to have it as long as we have. But we would like a more capable infrared space telescope that can help really fill out the population of NEOs. You can see here, its objectives are pretty simple. It's basically to go out and find a large chunk of the potentially hazardous asteroids in 5 years. We'd like to be able to reach that 90% point, and I'll show you a little more about that in a second. But basically, this will give us our very best information about the population when we combine it with the existing and planned ground-based assets. You can see the spectral energy distributions of several NEOs there on the right, varying the different albedos. And you can see that the two red bands there, those are the two proposed NEO Surveyor band passes. They span the thermal infrared peak there. The Vera C. Rubin Observatory's bands are shown in gray, and you can see that basically, regardless of the albedo, the flux in the infrared is pretty much the same. So next slide. So the idea here is to put this telescope at the Sun-Earth L1 Lagrange point, and then basically put a very tall sunshade on it so that we can spend a lot of our time surveying the region around the Earth's orbit. You can see the yellow shaded cones there are the instantaneous field of regard. The idea is basically to try to catch the NEOs, the most potentially hazardous objects, in the most circular orbits where they spend a lot of their time. This survey has no other science objectives. Its sole purpose is really optimized around near-Earth objects, and in particular, the potentially hazardous objects. So to that end, we are really optimizing the cadence to do this, meaning we collect a set of 4 linked observations, or what we call a tracklet, separated in time by less than 12 hours. And then we come back about a dozen days later and we revisit the same area and collect the same set of observations. And the idea, if we keep doing this over and over again, is that we will build up a highly reliable catalog of potentially hazardous asteroids. We expect to see a few 100,000 near-Earth objects at all sizes and millions of main belt asteroids, but of course the primary objective is really the larger NEOs. And we really want to try to get those very thoroughly, as well as get good orbits for them, good enough that we can predict where the object will be at the next apparition. We do have the ability to interrupt the survey if there is a target of particular interest. In other words, if something looks potentially hazardous, we can actually stop and follow it specifically while it's in our field of regard. And next slide. And you can see that there's a lot of synergy to be had between Vera C. Rubin and the NEO Surveyor. One of the great things about working in this field is that we have learned that planetary defense really is a team sport. It takes many, many, many people and many hands to catch these objects and follow them as they make their way across the sky. Rubin Observatory will be an opposition-centered survey, meaning it'll be very sensitive to NEOs that particularly spend a lot of their time outside of the Earth's orbit, such as the Amors and some of the Apollos. Whereas Surveyor is really trying to target, like I said, the interior regions around the Earth's orbit. So it'll be particularly sensitive to Ottens, some of the Apollos, and interior to Earth orbit objects. In other words, we're really looking for things in the most circular, most potentially hazardous orbits.
1 minute.
If we combine these two, oh, thanks, Kathy. If we combine these two surveys, we should really have our very best look at the NEO population. One of the things I think that needs to be highlighted is that Rubin Observatory is going to really provide an excellent catalog of main belt asteroids, which are a significant source of contamination when you're trying to discover NEOs. They outnumber the NEOs by about 1,000 to 1. So we really want to build that wonderful and robust catalog. So basically, these are two really complementary techniques that work together to provide both diameters, albedos, thermal inertias, as well as a robust set of detections. So next slide. And the last one. So this is what we think, putting it all together, the population would look like if we're really going after the objects that are larger than 140 meters. And I apologize, that should be potentially hazardous objects larger than 140 meters in diameter, as opposed to the NEOs, or all the NEOs. But basically, if we put these two surveys together, we think this offers us the very best shot at actually reaching that 90% goal given to NASA by Congress. And like I said, team effort. So thanks, and I encourage everybody to take a look at some of the lightning talks we have down there by my colleagues Tommy Grob, Eva Lilly, Tim Spar, Jason Suris, and Ned Wright. And of course, Joe's talk tomorrow on EOIs. Thanks.
All right, thank you very much. And now moving on to our second to last talk, Dr. Robert Warrick, researcher at the University of Hawaii on NEOs in the isolated tracklet file. And so over to you, Dr. Warrick.
Thanks, Kelly. Can you hear me?
Yes.
Awesome. Okay, so we're going to talk about NEOs in the isolated tracklet file. Next slide, please. So just as an introduction, so the vast majority of NEOs are found by the survey telescopes, but of course we're very dependent on the follow-up from other telescopes. Now, one large issue we have is the majority of tracklets. So a tracklet is a set of detection that also tells you its motion across the sky. They don't actually post to the confirmation page. What's called their digest score, which is an estimate of how likely it is to be an NEO, is just too small, really. So the NEO CP really only wants those objects with a score greater than 65. Another problem is sometimes the initial orbit estimates of our NEO candidates, it's just simply too large for follow-up telescopes to find, even though the same survey telescope may have imaged the same object in another lunation. Objects also become too faint, the weather can become not ideal. So what really happens to these tracklets? Well, these tracklets are dumped into what's called the isolated tracklet file. It's a rich repository for data mining. Some of the tracklets are in fact 20 years old or older. All the unlinked low digest score objects also end up in here. More importantly, it also includes was not confirmed confirmation page objects. And it's actually easier to link tracklets through their previous data that's in the ITF than it might otherwise be to do a visual search in pre-covery images or pre-discovery images. Another important thing is a lot of the times recoveries can happen, but it's not immediately recognized that an object has been recovered. So a single night tracklet might appear on the NEO-CP for a recovery opposition, but it also works the other way. There could be previous, oppositions that were recovered as a single tracklet. So being able to link these things can help us improve the orbit considerably. Next slide, please. So the isolated tracklet file itself, it's actually a lot of work has been gone into reducing it in recent years. So there's only about 10 million detections left. Now, while this seems like a lot, it's actually about half of what it was just a few years ago. This corresponds to about 3 million unique tracklet names. And there's only really a handful of observatories that are in the top, 6 here that I've listed. So it's really dominated by observations from Pan-STARRS and Catalina. It represents the vast majority of the file, and that's really where I've been focusing on is linking tracklets from these two surveys. Next slide, please. So previously, I've reported on doing linking of the ITF. So the first run through it was just to link every possible object, the so-called low-hanging fruit, things that are easy to link. The objects, the vast majority of their main belt, they're not very interesting on their own, but being able to remove them from the NEO-CP means linking the remaining objects become easier. There's also a large case of, for example, Hungaria asteroids, where these often appear on the NEO-CP, and sometimes they receive follow-up observations when it's not technically needed because there are enough tracklets in the ITF that the orbit is actually should be very well known. Removing objects too, it's a massive help for surveys like Pan-STARRS, because for any object that can be identified based on a catalog, we don't have to visually review it. It can be batch submitted to the Minor Planet Center immediately. So that's really a huge time saver on our end. Now, for our original survey, merging it in the MPC and removing it from the ITF was a very manual process. It took quite a long time to have this done. So it was a significant undertaking just to do that part. At the last PDC, I actually reported on finding an initial batch of NEOs. Now, they're more computationally intensive to find than main belt objects because their motion changes more considerably and there's a much wider range of their motion. But again, shrinking the ITF by removing the main belts means there's fewer tracklet comparisons that have to be done. One major problem with linking NEOs in the ITF is it's easier to get mislinkages, especially if you consider a very few tracklets, such as maybe 2 tracklets, to see if there's potential NEO candidates. Looking at older tracklet data too with NEOs, it often happens that there's no way to actually confirm with additional data whether the object was real or not. It may have, the errors have grown too large, it may be too faint, so it can be very difficult to find NEOs in previous data. Next slide, please. So this is just more of a pictorial representation of what exactly happens to link something in the ITF. So there's a tracklet on the left. It has a little circle and a P1 designation. I've plotted its, based on initial orbit, what its path across the sky would look like. Now, you'll notice near the bottom right, there's actually a second tracklet, and it's color-coded by the angular speed. But the idea is you look for tracklets that are moving somewhat parallel to the expected motion, and you try to fit a test orbit. And if the orbit looks good, the residual check is good, you can accept it. Next slide, please. And then you move on to finding additional tracklets. So eventually, once you found a few tracklets, additional tracklets line up very nicely with the path, extending even into previous oppositions. And you can very quickly build large lists of tracklet linkages to have removed from the ITF. Next slide, please. So the goal in this work is to auto-magically find NEOs. So I've taken the code, which before in the previous runs was very much a manual effort, and it's actually been adapted to run automatically every day. Every day it pulls the latest ITF data, so tracklets that were observed even in the previous night. It links through them, and it's able to link NEOs to a much lower digest score than what would appear on the NEO-CP. The most important part of this is linking objects that would have posted to the NEO-CP. So I mentioned finding Hungarias. There's also Mars crossers too. So this code, as it's running now, every night around dark time, so around new moon, it's able to link up to about 100 objects. A lot of them are Hungarias and Mars crossers. A good fraction of those I would have expected to post to the NEO-CP. So even if it doesn't necessarily find an NEO in a given night, it's very likely to find objects and remove them that would have posted, thus freeing valuable follow-up time for other objects of more importance. Now, there are still some improvements to be made. So currently, it requires at least 5 tracklets to actually submit, and it submits to the new ID pipeline at the Minor Planet Center. So this automatically takes care of designating or extending the arc of an existing designation. So at least 5 tracklets are needed for it to automatically submit it, but it's not yet automatically submitting NEOs. At this point, I'm very much manually checking it. I'm also able to manually check cases where there's fewer than 5 tracklets. So a lot of 3 tracklet NEO candidates might come up, and I have to look at those, whether they're just a numbered object that wasn't correctly identified or just a mislinkage.
Hey, Rob,
Yeah.
sorry, I couldn't find a pause there, but we're at time, so you want to wrap up soon.
Okay, yeah, next slide. So one immediate important part is Apophis. This was actually used to find Apophis. Now, the original run before the Apophis campaign was it actually checked everything. A direct result of the campaign was to put in a minimum digest score. So it only runs if the digest score is at least 6. And this vastly improves the speed at which it can run a single night and look for the potential NEO candidates. Next slide. Now, this year, I've actually found 6 objects. So there's 2 additional ones, 2021 GM26 and GN26 that aren't listed here. Of the 4 NEOs I found from this year, 2017 FS188 was actually found as a 2 opposition object. The most important object here is actually 2021 AF8. So it's a 400-meter PHA. I was actually eventually, once the arc was extended a bit, able to find it back in 2015 data in an image recovery search. And thanks to Marco, we found a 3rd opposition. And so now this is an uncertainty 0 object at the Minor Planet Center. So it's very well known. I believe it's actually on the Goldstone radar list to be observing soon. Next slide. Yeah, so in progress, in summary, progress is still ongoing. It seems that far fewer objects post to the NEOCP now than did before. I've only found a handful of NEOs. Now, you know, it's not very surprising. The NEOCP does work really well. This is really meant to focus on objects with motion that otherwise wouldn't have been found. But the fact that it was able to find Apophis shows that there are corner cases that this is really a well-suited tool that isn't provided by otherwise. So thank you.
All right, thank you. And to our final talk of the session, to Dr. Michael Kelly, Associate Research Scientist at the University of Maryland, on catching near-Earth objects in survey data. All right, Dr. Kelly.
Great, thanks. Yeah, thanks for the opportunity to talk to you about Catch. I work at the Planetary Data System, Small Bodies Node at the University of Maryland. PDS is the archive for much of NASA's planetary science data. So next slide, please. So motivation for this is that ground-based NEO surveys are producing millions of images per year. It takes specialized tools that, in order to keep those data accessible and relevant. We've been hearing a lot about that in this session. So key application is, of course, object pre-recovery, and I don't need to motivate that for this audience. Next slide, please. So our solution is Catch. We call it the Comet Asteroid Telescopic Catalog Hub. This is designed to quickly find comets and asteroids in wide field time domain survey data. At least it's optimally designed for that. The point is that we're archiving these types of data at NASA Planetary Data System. We want to make these data searchable. We want it to be accessible so that the general astronomer would be able to use it. We also want this tool to be generalizable in the fact that we can adapt and add new surveys with a minimal amount of effort. In addition, the tool itself is open source and you can deploy it on your own data set if you like. So next slide, please. So you can, it's running right now at catch.astro.umd.edu. We have 2 parts to it. There's an API backend, and anybody's allowed to use that. There's also a web-based front end, and that uses the API directly. When you search for your object, it gives you a list of detections and basic metadata on it, and you can also visualize the data itself in the browsers. Next slide, please. Currently, we have 3 surveys loaded. Archived at PDS is 2 phases of the NEAT survey, so the Palomar TriCam portion and also Maui Geo DSS portion data sets. We've also added SkyMapper data release 2. This is a Southern Hemisphere survey from Australia. It's not ideal for moving targets in terms of its cadence. However, it's an excellent way for us to scale up the amount of data in our archive or in our database so that we could demonstrate that it works well and should be able to work in the future. Next, please. So the problem here is needle in the haystack. There's a lot of survey data, and the asteroids or comets we're interested in are just moving through a small portion of them. So it takes efficient algorithms in order to identify what data is really meaningful. And the most important part of that is really eliminating data that we don't need to search in detail. So you want something that says, In this fictitious survey figure, we have data going from the sky survey taking data from time 1 to time 2, and it's moving in RA index space. Meanwhile, the object itself is moving in some other motion on the sky. What we need is an algorithm that says, well, look at the images near the middle of this data set and ignore the ones that are early and ignore the ones that are late. And that'll give us, that's an important improvement in speed rather than testing every image in detail. So what we're using is a technique that is, next slide, please. We're using a technique that is actually part of Google Maps and Google's spatial searching. So this is a library called S2 Geometry, and I'm going to spend a few slides just talking about why this is such a neat algorithm. In database speak, S2 Geometry indexes the sphere, and it does this with a space-filling fractal curve. What this curve does is maximize locality, and that's what I'm going to explain here. There's also some other benefits to this library, but let's talk about that one in particular. Next slide. So here is a portion of the sky that we want to index. Indexing is really important for databases. Databases work well with one-dimensional columns in one-dimensional data. However, the sky is two-dimensional, and we additionally have a time dimension that we're interested in. So what we do here in this example, let's start with just a straightforward thing where we're going to index this space. Next slide. We'll start with 0 up at the corner, and we'll draw a line going up and down. Next slide. And we'll just kind of paint the whole survey. Thank you. Paint the whole portion of space from this number from 0 to 1. That way, if our search algorithm says we need to find data near 0.35 on this line, we can easily identify where in that line, what image we're looking at in the database. So next slide. So let's focus on a small portion of this data set. Say our algorithm says we need to look for a near-Earth object in this corner. Next slide. In the database itself, it's broken up because of the way this index is developed. So we have, at the bottom, we have 4 portions of the database that are useful for us to search in detail, but it's interlaced with large portions of the database that should be ignored. So next slide. This is where the space-filling fractal curve is really important. Next slide. So if we search on the same corner here, we're actually just looking at a continuous portion of the data set. And that means we're reading the disk fewer times, and we're really accelerating our ability to examine that data. Next slide.
1 minute.
Thanks. So that's what I've described to you is actually the development version of Catch. What's running right now is a slightly different technique, but our development version will be deployed sometime this year. What we're going to do is add Pan-STARRS data release 2 data as it is archived at MAST, and that'll give us another order of magnitude of database data to work with. And also this year we're archiving at Planetary Data System Atlas and Catalina Sky Survey, and we'll keep the Catch tool up to date as those data are coming in. One important thing that the development version is doing is searching by uncertainty ellipse. So it's not just going to be searching the nominal ephemeris position, but you have the opportunity to search by the uncertainty ellipse as given by Jet Propulsion Laboratory, or you can actually add your own search area around the object as you please. And then we also would like to do some integrations with Minor Planet Center. One may be some automatic NEOCP or potentially cometary object queries. So there would just be a page where everybody could just see what's going on every day. Okay, thank you.
All right, thank you. And thank you to all of our speakers. And so we will have a question and discussion period for the remainder of the hour with all of our speakers. And folks have been very busy in the Q&A window already answering a lot of questions, and so many have been addressed. And so I'll catch some of the ones here at the end, but I just want to ask really quickly using chair privilege. We have this combination of surveys and MPC talks and isolated tracklet file NEOCP, all of this all needs to work together. Are there any comments from the panelists on this whole system working together and what might be needed or in order to not flood the system with the new surveys coming on board and to be able to handle it all effectively on all sides, with everybody doing their part to make sure that things aren't overwhelmed. Any comments on that from our panelists?
I can make.
Sorry.
I was going to say, I can make one comment. I mean, I exclusively use the ITF as it's provided by the MPC. So any survey data in there, like Pansares, Catalina, whoever, that's available to me. So I can already use everything that there is.
That when it goes up orders of magnitude.
Well, it's scales, right? It's just a computer question. Yeah.
Yeah. And Federica.
Yeah, I can speak from the MPC side. So we're really working on modifying and improving pipelines to be able to deal with this also type of data like ITF from ITF, and NUCP object. And as also Rob was saying, the impact that are coming from the recovery from the ITF. So we're trying to have the most automatic as possible, at least from our side, so that won't need a lot of manual intervention.
And since we have surveys on here too, any wish list for the surveys to help you in your job?
Yes, yeah, that might be really helpful. They're already doing a really nice work. I mean, Rob is sending a lot of ITF to ITF and also a lot of identification, Andreas Doppler as well. So we're receiving a lot of that from the community, and this also helps us in improving our pipeline in case we see errors or bugs, and it's really helping us a lot.
Okay, thanks. There's a question here from Boris Shustov about NEO Surveyor. What is the working temperature of the IR detectors?
It's about 40 Kelvin. That's our requirement.
Oh.
Yeah.
Oh.
Can you hear me?
Yes, yes.
Okay, great.
And he was also asking about the total budget.
Let's see, total budget is, so it is B through D costs are sort of in 600 million range, something like that.
Mm-hmm. Thanks. Thanks, Amy. I have also a question for LSST team. That's the problem of super constellations, which is coming soon. It is important for the wide field telescopes. Maybe they know what to do in this situation. Now, my question is, what you know about this?
Yeah, it's a good question, and there were a lot of questions in the Q&A about mega constellations and satellites. It's an issue. We're working with SpaceX to evaluate their mega constellation and what we might be able to do to work with SpaceX to mitigate their impact. We're also just trying to evaluate what the impact would be if nobody did any mitigations. It's worth thinking about that it's not just a SpaceX problem. There are other mega constellations that are intended to go online in the next decade or so. The night sky is going to be changing for sure. So one of the things that is worth keeping in mind, though, is that it really does depend, the impact does depend on how bright the satellites are, which is something we can work with the people launching the satellites to try and mitigate. And it also depends where you look from the ground. So, and where your telescope is located and what time of year it is, things like that. But so one of the things that I am kind of worried about is what happens during twilight, because this is when the satellite problem is the worst. However, on the bright side, it does look like what happens is that we lose perhaps a small part of the detector where the satellite has gone through. And even if you are pretty conservative about how much of the image gets wiped out by the satellite, it's a very few percent. So one of the things that's been kicked around, interestingly enough, is like, okay, what if you delay your observations so that you are pointing where the satellites aren't, so basically skipping the satellites. If you can know where the satellites are very precisely so that you can calculate that ahead of time and fold it into your scheduling, that might be possible. It's hard, but it might be something that we can at least add another layer of mitigation through that. However, if you just say, I'm going to go to a part in the sky and I'm going to wait until the satellite clears, the exposure from LSST are so short and the time of the overhead for slewing and reading out the image is so short in comparison to the image. So basically we have a very low overhead, that if you wait for the satellite to clear your exposure, you're actually perhaps going to cost more than just taking the exposure and throwing away that part of the image. So it will have some kind of impact. If we just threw away the images, it probably would be a few percent. But again, it depends where you are in the sky and whether it has a preferential impact on some kinds of visits.
Okay, we have a question here from Alberto Vladnisa. There are many asteroids that are discovered when they're already very close to Earth. What can be done to improve the detection? Is to try to improve the lead time. Any comments?
Yeah, I mean, I think this is kind of one of the objectives of doing these advanced surveys is we really do want to try to optimize them in such a way that we are finding the objects when they're years to decades away from any potential close encounter, ideally, so that we have more time. Especially for the larger objects where, you know, civil defense would be very, very difficult because it's just so big. So the idea really is to try to find these objects and calculate an orbit for them where we really can see where they're going to go and hopefully, you know, have years to decades. We know from previous studies of mitigation efforts that it just takes that long to really be able to do anything that we would like to be able to do in terms of deflecting an object or moving it out of the way. We need lead time. So that's one of the big objectives. With Surveyor, that's really what we're trying to plan for is finding these objects when they are well away from us.
Right. And a question from Lord Dover for Lynn. Given you will obtain inversion quality light curves for a large number of objects, eventually over multiple apparitions, is there a coordinated effort to produce convex shape models?
So there's not an effort from the project itself. However, this is the kind of thing that the LSST Science Collaboration is working on. And I don't know if they have a coordinated effort to produce shape models at the moment, but that's the kind of thing that's really in their wheelhouse and is where I would encourage you to go and talk to people about setting up that kind of collaboration.
All right, thank you. And yeah, you all have addressed a lot of the questions in the chat already. Do you have any questions for each other? Again, bringing together kind of this interesting group here of different aspects of the pipeline.
Michael Bush had a question there, and I'm sorry, I just wasn't fast enough on the draw to answer it. But this is about the small impactors with the Rubin Observatory as well as NEO Surveyor. So the upshot is the Surveyor fields obviously go down to 45 elongation, and that's as close to the sun as we can look. But just a little bit about how the sources are extracted. So our nominal sensitivity is predicted based on taking 30-second exposures and then combining them into 3-minute, what we call visits. So all the plots I've shown have been based on those 3-minute visit exposure sequences, but we are downlinking these 30-second exposures, and we are also running a fast pipeline in parallel that should be looking for faster moving objects up to a few tens of arc seconds per minute. And so that is the way we would look for some of the smaller things. But basically, no, we're not going to be able to find things that are impacting tomorrow. That's pretty difficult, I would say, on average. But faster is possible.
All right, just trying to see if there are any other questions. And certainly there are other, the operating surveys not represented here and have lightning talks or posters, so please be sure to check those out, because they're complementary also to the surveys coming online, and all have different missions. Let's see, okay, here's a question. Do you see, to Amy, do you see space debris with NEOWISE? If so, do you provide the data to the space debris tracking institutions?
Yeah, that's a really interesting point. So, you know, in fact, we have a series of conjunctions or close approaches with OneWeb satellites this very week with NEOWISE, a couple dozen of them. And just, you know, to the point, you know, SpaceX is lowering the altitude of their Starlinks down to 500 some kilometers, and that's getting pretty close to NEOWISE. So yeah, we definitely do see a lot of things in our field of view, and in fact, they look like raindrops streaking through the images. We just publish everything. We put everything out through our archive, the NASA PD or the IRSA image server, the Infrared Science Archive, hosted by NASA. So we don't do anything special with the satellite observations other than just publish the images in the extracted source list. However, I will note that there was recently a paper that was published looking at some of the satellite data. I just saw it not too long ago. So people are using it for that purpose. And there's certainly lots more of it nowadays.
I think time for one more question, at least. There's a question, I think, for Lynn for the proposed Twilight survey. Why 1 second exposures as opposed to 2 seconds or 5 seconds, for example, from Dave Tholen?
Yeah, so why 1 second exposures? It's a good question. Mostly that's because we had these series of white papers that, in this process for defining the survey strategy, and that's what they asked for, was 1 second exposures. We could go and look at what the impact would be to have longer exposures. But there is also a constraint that we would like it to use sort of about 15 to 20 minutes at twilight, and you want to get a triplet. And so making longer exposures means you cover less area. But I think that making the exposures a little bit longer might be an interesting thing to investigate, sure.
All right, and we're pretty much at the end of the hour.
Lori from this morning, and we are ready to start with our talks. The first one on the list is Dr. Joe Maciero, scientist at Caltech, and the title is Characterization of Near-Earth Asteroids from NEOWISE Survey Data. So take it away.
Thank you, Marina. And thank you for giving me a chance to tell you about the exciting results we've gotten from NEOWISE. Next slide, please. So just as an overview of what NEOWISE is a PI-led mission funded by NASA's Planetary Defense Coordination Office with our PI, Amy Mainzer, University of Arizona. And it's an all-sky thermal infrared space telescope surveying from a low Earth polar orbit. And so every 6 months, we take full images of the sky, and we search those images for new and known near-Earth objects with the goals of finding new objects and providing characterization data, in particular diameters and albedos, for all the NEOs that we observe. We do this in 2 bands simultaneously at 3.4 and 4.6 microns. We're currently operating passively cooled at around 77 Kelvin. Now, the discovery and characterization of these objects is really important because the population characterization allows us to put individual objects in context, whereas individual object characterization is obviously important for any future either mission planning or planetary defense preparation. Next slide, please. So how do we get the diameters from our thermal infrared observations? So what I'm showing here are the spectral energy distributions for 4 different near-Earth objects with different albedos on the left, and on the right are 4 different main belt objects. The vertical bars show the band passes that NEOWISE is currently using. The cyan is W1 and the bluish one is W2. And so you can see that W2 is probing the thermal emission of these near-Earth objects. And so we can use that to constrain how the thermal flux is being emitted, and thus how big the object is once you know its orbital, its distance, and its phase angle at the time of observation. Once you get a diameter, you can then use any visual observations that you have to constrain the albedo, as you can see from the left half of the curve, where the albedos, the objects of different albedo, their spectral energy distributions pull apart rather dramatically. Now, we still are on the Wien side of the spectral energy distribution, and so our diameters will not be as sensitive as they were during the cryogenic NEOWISE phase when we were probing the peak of the thermal emission, or as they will be for NEO Surveyor, which is also designed to probe the peak of that thermal emission. Next slide. So the results of our 7 years of survey are shown here. In blue are all the previously known near-Earth objects that were observed and characterized by NEOWISE, and in black are the near-Earth objects that we discovered as part of our survey. And so what's interesting about our discoveries is that NEOWISE tends to find objects that are fairly large, 200, 300, 400 meters, even up to a kilometer or larger, but that tend to be very dark, so albedos of a few %. And so these are objects that are being missed by other surveys that survey in optical light because they are so low albedo, and typically they're coming at unusual orbits, either highly eccentric or highly inclined. And so NEOWISE is especially sensitive to these kind of objects and fills this niche in the global survey for near-Earth objects. Now, measurements are no good without quantifying the uncertainties. So in the next slide, what I'm showing is our diameter uncertainty as we can get from comparing to other populations. Now that we've been surveying for 7 years in reactivation mission and with just the 2 shortest wavelengths, we can compare the diameters we get from those measurements to the diameters we got from the cryogenic neowise phase when we were probing that thermal peak. And that's what's being shown in the top panels here. And we find that there's about a 30% uncertainty induced by using only the short wavelengths compared to the diameters we got during the cryogenic mission. In the bottom, I'm showing our comparison of the reactivation diameters to diameters from other data sources, such as radar or occultation of near-Earth objects. Unfortunately, there are only 11 unique objects in this measurement, and so we can't really get as good a handle on the distribution as we got for the cryogenic data, where we had a larger population. But we can see that the standard deviation of those measurements is around 40%. And so this is a good way of quantifying how certain we are for any individual object that diameter we're getting from our thermal infrared measurements. Obviously, once you're probing the thermal peak, you're much less sensitive to uncertainties in the beaming parameter in the Needham model, and so your diameter accuracy improves to the 10 to 15% level, as we've seen with the cryogenic WISE and as we'll get with NEO Surveyor. Next slide. Now, the uncertainty on albedo is a further problem because we have this is a combination of your uncertainty on diameter and your uncertainty on H magnitude. And so for main belt objects, your H's are pretty well known. Even with a single photometric point at low phase angle, you have a good constraint on H. But for near-Earth objects that are at high phases, as you can see in the two panels on the right here, a single measurement at 60-degree phase can lead to a very large uncertainty on your H magnitude. And this will feed directly into your uncertainty on albedo. And so you can make assumptions based on what we get from the albedos of the main belt objects. But for individual NEOs, it becomes very difficult to predict how well we know the albedo of that object without knowing how well we know the H magnitude. And so there's a paper that came out earlier this year in PSJ that discusses this a bit more and how we can quantify these uncertainties and make them better. Next slide. So I want to step aside here and talk now about what we could do with NEOWISE for the exercise object 2021 PDC. This is a short discussion. There's more data about this, more discussion about this in my extended abstract. But when we looked at the orbit of 2021 PDC, we saw that it would not be detected based on its distance from the Earth and the spacecraft and its estimated size range in our normal survey patterns. However, because it was discovered early enough with enough warning, we could, in theory, replan the NEOWISE survey for the 3 weeks in June when it's passing through our field of regard. And so instead of the nominal 10 passes over the object that we could use to detect it, we could replan the survey to follow it over that time period and get around 300 exposures of 2021 PDC, which we could then stack to build up a deeper image of this object. Now, I checked these positions on the sky. They're not in the galactic plane. They're not in a very confused area. So it looks like we could stack them. However, the trade-off for this, and the reason we're surveying where we are right now, is that this would dramatically increase the heat load on the telescope and could potentially reduce sensitivity by the end of that observing campaign. Basically, we'd be pointing off zenith and more towards getting more heat load from the Earth on the spacecraft. And so as that 3 weeks ran on, the temperature inside would go up and potentially we would lose some sensitivity. So for our estimates, if we say about half of those data are useful, then we can have 150 exposures co-added, and we would get approximately a 3 sigma detection on a 100-meter size object. Next slide. So assuming we did get a 3 sigma detection for the exercise object, running our data through our normal Needham fitting pipeline, and using the orbit that is known. Now, there's sufficient orbital data before this in the exercise that we know the distance to the observatory and the distance to the sun and the geometric parameters. So we were able to get a diameter constraint of around 160 meters plus or minus 80. Using our normal processes, we would probably say that this is a decent upper limit of around 240 meters.
Seconds.
Yep. And we could pass that on to mitigation planning by early July. But over the course of June, we'd be able to restrict more and more further down the size. So we'd be able to reject multi-kilometer objects early. Next slide. And so in closing, I just want to say that NEOWISE has been asked to plan to continue the survey through June of 2023. So we've been extended for 2 more years. And orbital evolution will be monitored as the sun comes out of solar minimum. So we're going to see how things go. But it continues to perform well, and we don't expect any degradation over the coming 2 years. And so we look forward to all the new discoveries that we'll get with this. Thank you.
Okay, excellent. Thank you. That was on time. Okay, now we are moving to our second talk. Dr. Maxime Devogel, observatory scientist at University of Central Florida, and he'll be talking about polarimetry as a tool for physical characterization of potentially hazardous NES. Okay, you have 8 minutes.
Thank you very much, Maria. Can you hear me well?
Yes.
Yeah, okay. So next slide, please. So let's first start by defining what is polarimetry. So polarimetry is the measurement of the linear polarization of the sunlight scattered by an asteroid's surface. So you've got a situation here where you've got the sun, which is emitting light, which is unpolarized. And upon reflection on the asteroid's surface, the light that will be re-emitted toward an observer will be in a state of linear polarization. And polarimetry is the technique that will measure this linear state of polarization. So next slide, please. So the polarimetry is mainly dependent on the phase angle. And the phase angle is the angle between the sun, the asteroids, and the observer. And as you can see on the right, the phase polarization curve for typical asteroids always have the same shape. And so at low phase angle, the value of the so-called PR per meter, which is normalized difference between two intensities, is negative. And it will be 0 around a phase that we call inversion angle. And at higher phase angle, it will turn to positive value and will increase until a phase angle in between 80 to 120 degrees, depending on the asteroids, up to what we call the maximum degree of linear polarization. And next slide, please. So all asteroids have the same shape, but the absolute value of the polarization will be strongly dependent on the albedo. As you can see here, for example, in blue, it's an example for the asteroid Phaeton, which is a very low albedo asteroid, and the polarization is very high for Phaeton, up to like 44% of linear polarization, and Bennu is actually, and Hyugu have been observed to have even higher linear polarization. But if you take a more moderate albedo, like for example S-type asteroids, S-type have like in the between like 20% albedo, and their polarization is much lower, from 5 to 10% for the maximum degree of linear polarization. So if we manage to obtain one single measurement for an asteroid at a phase angle higher than 40 degrees of phase angle, we can very quickly and very easily get a good estimation of its albedo. Next slide, please. So why is it important to observe NEOs in polarimetry? Right now, most of the polarimetric observations have been obtained for bright main belt asteroids. And the reason is that it's in order to get a good polarimetric measurements, we need a very high signal-to-noise observations. And if you look at the histogram of all polarimetric measurements for asteroids, the histogram is peaking around 10 to 20 degrees of phase angle. This is because main belt cannot be observed at phase angle higher than 30 degrees. But if we took only NEO measurements in the dashed histogram, this histogram is peaking around 60 to 70 degrees. And if you look back at the phase polarization curve on the right, you can see that the part of the phase angle that we can sample for near-Earth object, it's much larger for main belt asteroids, and we can access the maximum value of polarization, or we can measure the slope of the positive polarization branch, which will inform us about the albedo of these objects. So next slide, please. So, and it is very important to get Pmax, because actually the relations which link the polarimetry and the albedo, which is called the Umov law, is actually linking the maximum degree of polarization with the albedo. So there is some proxy for example, for main belt asteroids to be able to get an albedo determination with low phase angle measurements. But these proxies are much less accurate than if you were actually measuring the Pmax. And this law have been actually calibrated for the moon, with the moon, but the surface properties of the moon is widely different from sorry, the regolith properties of near-Earth asteroids. So we need to get more observations of near-Earth asteroids in order to calibrate these relations specifically for near-Earth objects. So next slide, please. So what can be done now actually already? Here you've got like all the polarimetric measurements that have been obtained so far for near-Earth object, and it's a phase polarization curve, but this time in a log-log scale. It's in a log-log simply because it's easier to visualize all measurements that have been obtained so far. And if you go to the next slide, please, you can see that the measurements that are on the up part of this plot are all for very low albedo asteroids like Ryugu, Bennu, or Phaethon. They are all less than 10% albedo. So if you go to the next slide, you will see that for 2021 PDC, if we get like one polarimetric measurement at a phase angle higher than 40 degrees, if it fell into that blue shaded area, we will like right away know that it's actually larger than 150 meter. And if you go to the next slide, you can see that we've got like other gap in this coverage of the phase polarization curve, but we've got like one asteroid, which is JD6, which is a 40% albedo. So if you go to the next slide, you will see that we can define another regions where we know that it should be between 10% and 50%. And so for PDC, that will mean that it's between 120 meter to 150 meters. And so you understand what you can do next. If you go to the next slide, you will see that most of the observations that have been obtained so far are for for S-type asteroids. And all the S-type asteroids have albedo ranging from 15% to 35%. So in the next slide, we can define another shaded regions in the phase polarization space that will give you albedo between 15 and 40%. And this will give for PDC diameter in between 80 to 120 meters. And finally, in the last regions, in the next slide, you will see with very high albedo objects. And in the next slide, we can define a last regions.
Seconds.
Okay. We can define a last regions, which will PDC will have a diameter less than 80 meters. So right now, it's just like a simple subdivision of the phase polarization curve. But if we can obtain more polarimetric observations, we can refine this classification and more accurately subdivide the phase polarization curve to get a more reliable albedo determination. So in the next slide is my conclusions. Polarimetry is very effective to obtain albedo informations. One measurements can reduce the uncertainty by a factor of 2 to 10 times. And we need more observations to better calibrate this polarimetry albedo relations. And more polarimeter are needed, and more specifically on large aperture telescope. So thank you very much for your attention.
Okay, thank you very much. Okay, and we have next speaker, Professor Vishnu Reddy from University of Arizona, Challenges in Differentiating NEOs and Rocket Bodies, 2020 SO Study.
Thanks, Marlena. Can you hear me?
Yes, I can hear you well.
Awesome. Okay, so a quick overview of the study we did starting last year. There's several people here. I'll identify them as I go through the slides. Next slide. Okay, 2020 SO. So this object was discovered by Pan-STARRS-1 in September 2020. It was temporarily captured in November of last year. It had two close approaches, one in December and one in this February, a couple of months ago. And due to its low orbital velocity and Earth-like orbit, Paul Chodas, one of my co-authors, suggested it could be an artificial object, more specifically a Centaur 2 rocket booster. So there you see a picture of Atlas Centaur there. The stage we're interested is marked in that yellow line towards the top. This was launched in September 20th, 1966 from Kennedy Space Center. So it was actually for landing Surveyor 2 on the moon. The upper stage itself went into heliocentric orbit after pushing the spacecraft towards the moon. It's a relatively large object. The length is about 10 meters by 3 meters, and unfueled mass little under 3 tons. Next slide. So the goals, what we wanted to find out was whether it was an asteroid or a rocket body. For me personally, I want to see how good is Paul at predicting these things. And if it's a rocket body, I wanted to know if it's an upper stage from Surveyor 2 or not. The challenges we faced were like it was relatively faint when it was found in September, V of about 21.5. So you couldn't really do IR characterization with things like RTF. So we're kind of limited to broadband color. So can you tell the difference between an asteroid or rocket body with just colors? And the thing is, eventually it would get brighter. We knew that, and we wanted to see if we can actually do some spectral interpretation because we didn't have many spectral libraries, so to speak, of analog materials, especially of rockets that have been launched 50 years ago. So that was the other challenge we were facing. Okay, next slide. Okay, a lot of information. I encourage you guys to download the talk and look through it. So basically, what I'm showing here is the different observing windows when we observe the object. The green and blue lines show the discovery and, of course, the exiting of the Earth-Moon system. And then on the top right side, you see magnitudes. You see the dips. Those are the 2 close approaches. The purple line is when we did the first LBT observations. These are broadband colors. And the red line show the IRTF observations, which were 3 of them. So next slide. So so since it was really faint, the only thing we could throw at it was the LBT. These are twin 8.2 meter telescopes that the University of Arizona has access to. So this work was done by my grad student, Ben Sharkey. What we basically did was we did slow and low resolution spectra of this object to kind of get a color spectrum. So we did GNR on one side of the telescope and INZ on the other side. Next slide. So here you see some results. So what you see here is a low resolution visible color spectrum, so to speak, of the object. Those are the black boxes that you see, the 4 colors from GRIZ. And then you see spectra of what you call typical asteroid taxonomic type, an S type and a D type. Definitely it's not an S type, possibly a D type, but the slopes were still too steep for 2020 SO. Next slide. So we couldn't quite get visible spectra of other objects like other centaurs in Earth orbit with the LBT. The telescope quite wouldn't track. So we used this little telescope that's on top of our department. It's a 0.6 meter Newtonian, and we did low resolution spectroscopy of it. It was done by my grad student Adam Battle. So what we did was we went and culled through all the centaurs that were ever launched and found the one that were still in Earth orbit. Several of them were launched in the 70s to put satellites in geostationary orbit. So those upper stages were still around and they were the same model. So we went and we looked at other centaurs and tried to compare the spectra of those centaurs with 2020 SO. Next slide. So here I show spectra of 3 different centaur rocket bodies in Earth orbit we got with this telescope. The black lines is the LBT spectrum of 2020 SO. The spectral slopes are pretty similar. There's slight difference in spectral slope in the shorter and longer wavelength, and that's primarily due to the difference in phase angle. And of course, these centaurs have not quite been in space as long. They're about 45-ish years old. 2020 SO, if it was a centaur, it would have been 54 years old. So, but the trend seems to match. That's what I thought. Next slide. Next, the object became bright enough to observe with the IRTF. So again, we see those observation plots, phase angle on the left, visual magnitude on the right side. So this is the first spectrum I'll show you is from the first red line. And the object was, barely observable with the IRTF. It's a visual magnitude of 19.3. And then, and of course, subsequently. Next slide. So here I show you a spectrum of 2020 SO. So what you see are the gray circles are the IRTF spectrum, and overlaid on top of it are those centaur spectra we got from this little telescope I showed before, and also the LBT data that we got of 2020. So those 4 red dots you see are the 4 slow in color, so to speak. And you can see they kind of match pretty decently. You know, the overall trend seems to be the same, but we don't quite see any absorption bands. So that was another thing. So we waited a little while when it did the first close pass. So we observed it on 2 nights. So, and then next slide. And so here we start seeing absorption bands. So same 2020 SO, but at much brighter. So we see absorption bands at 1.42, 1.72, and 2.29 microns. But we didn't have good lab material, analog material to compare it. So the only way we could get a comparison is to actually observe another centaur in Earth orbit with the IRTF. And anybody who's observed with the IRTF knows that its field of view it's not known for its field of view. Let's say it's 1 by 1 arc minute, and trying to put a satellite, a rocket body in Earth orbit into its field of view is nearly impossible, but we managed to pull off that. And next slide, I'll show you a comparison of a centaur in Earth orbit with 2020 SO. So let's move to the next slide. So here you see the red spectrum is that of 2020 SO, and the gray spectrum is one of a centaur in Earth orbit. They both show the 2.29 micron feature. The 1.42 and 1.72, they're not quite there. You can see it, but you got to really isolate the features to see it. So I think, at least we can tell that 2020 SO has spectral property consistent with a centaur rather than that of an asteroid. But we wanted to know what was causing these absorption bands. So we had to go into the historical records to find out what materials were there on this rocket
30 seconds.
Yeah, next slide. So it turns out there were 3 main spectrally significant components to it. One is the 301 stainless steel, which most of the body and the engine belts were made of. The other is this polyvinyl fluoride, which is a thermal paint, insulation, and then aluminous mylar that was covering the avionics deck. So we think that the absorption bands are coming from there, basically. So next slide. And in more specifically, polyvinyl fluoride has absorption bands exactly at the same wavelengths that you see on 2020 SO. So you can see the top, there's a little table. It shows the absorption bands on the polyvinyl fluoride spectra we got in the lab and that of 2020 SO. They're almost 1-to-1 match. So we're still investigating. Next slide. I think that's my summary slide. Yeah, we're still investigating, how to do spectral mixing and stuff. So we've demonstrated that spectroscopy can differentiate artificial and natural objects. It was a relatively fast turnaround. We figured out in 2 weeks that 2020 SO was not like an asteroid, something else, And definitely we have to factor in things like space aging or space weathering, especially when you're trying to interpret spectra of things that are 54 years old and made artificial. So with that, that's my talk. Thank you.
Okay, well, thank you very much, Vishnu. I think that my co-chair is having some technical difficulties, so I'm going to introduce the next speaker. Stephen, are you there?
Yeah, no, I'll go ahead and do that. Sorry, Marina. Yeah,
okay,
it's, the next speaker is Dr. David Dunham, Chief Mission Design Engineer with KinetX Aerospace, and he'll talk about accurate NEO orbits from occultation observations. Take it away.
I acknowledge my many co-authors as well as many individual observers whose help was crucial to the success of these endeavors. I have way too many slides to show the many new results, so I'll be able to stay on give 1 or 2 sentences only for each, and you can just get a quick glance of each. Please get the longer version of my presentation with more explanation on the link I give at the bottom of my conclusions slide. You can get it from the PDF of this presentation on the Session 6B webpage. Next slide. After an introduction to IOTA's work, I will talk about the 2019 Phaethon occultations. Since our abstract was submitted, we've had successes with 4 occultations by Apophis, more than 10 times smaller than Phaethon. Next. IOTA began in the 1960s. We've measured the sizes and shapes of hundreds of asteroids, and with NASA and the MPC, we archive the observations for all to use. Next. The work began with visual observation of lunar occultations. Next. Around the time of Apollo, Gray's expeditions inspired a generation of young astronomers. Next. Special techniques and equipment were developed. Next. IOTA's emphasis changed to asteroidal events in the late 1970s. Next. Many interesting main belt events have been recorded. Next. Some of us developed techniques to video record occultations from multiple pre-pointed remote stations. Next. The first asteroidal occultation documented by a coordinated plan of mobile observers was actually for the large NEO arrows, all visual then. Next. Phaethon is the parent body of the Geminids meteors and is the flyby target of Japan's Destiny Plus mission. It was imaged by radar in 2017. Next. This rare U.S. event was found by Isao Sato in Japan. This was by far the smallest object whose occultation we had tried to predict and observe at that time. The prediction error ellipse was shrunk considerably with JPL orbit 685 that added Gaia observations. Next. This shows the sky plane plot of all of the observations where the star was successfully monitored. The JPL prediction was accurate to under 1.5 kilometers. Next. This shows in more detail the 6 positive chords fitted to the radar shape model. Next. This allowed 6 more events to be observed with increasingly better predictions. Next. This shows the increasing accuracy of the A2 non-gravitational parameter with the addition of occultation results. Next. There will be more opportunities before Destiny Plus flies by Phaethon in 2028. Next. Jocelyn Desmar found 2 bright Apophis occultations in the US early this year. The orbit and occultation path were updated with new radar data the day before the second of these 2 events. The link to IOTA's occultation page is at the bottom. Apophis occultations page is at the bottom of this slide. Next. 3 green dots show the locations of stations that recorded the March 7th occultation south of Oakdale, Louisiana. The lines are 107 meters apart, which is 80 meters on the sky plane. So that way we ensured getting at least 2 positive chords with our net. We have 13 stations around this place, but only 6 observers actually set all those stations up since we had multiple stations. Next. The equipment of 2 remote stations that recorded and precisely timed the occultation. Next. Based on the March 7th data, orbit 207 was computed and used by 2 observers in Greece and 4 nights later. They both had a miss. This was also the case for most of the stations for the March 22nd US occultations, but Roger Venable's easternmost of 5 large telescopes recorded the occultation. He saved Apophis's accurate orbit. Next. Downweighting the March 7th data allowed accurate predictions for 2 more events on April 4th and 11th, each recorded by 3 observers in New Mexico. Next. The residuals for the 7th March occultation relative to the best fit orbit stuck out like a sore thumb, likely due to the error in Gaia data for the star, which is the eclipsing variable NY Hydri, which has a period of 4.8 days. Next. This plot from Paul Latango's poster shows the dramatic decrease in the error of Apophis's A2 non-gravitational term with addition of this year's radar data and then the occultations. Next.
1 minute, David.
We have 2 occultations in the southwest next week, but both are in evening twilight. Next. After FACON in 2019, occultations by the much smaller Apophis demonstrated the astrometric power of small NEO occultations, allowing their paths to be propagated accurately far into the future. For NEOs, occultations nicely complement radar observations and can be made at much larger distances from Earth to improve studies of Yarkovsky and other small forces acting on NEOs. We hope that the pursuit of NEO occultations will inspire a new generation of observers to improve on the techniques that IOTA and others have developed for modal station deployments, similar to the way lunar grazes motivated my generation decades ago. Someday your occultation observations might save the world or part of it by allowing accurate prediction of an impact. A link to the longer version of the presentation is at the bottom. My next and last slide. Just links are given here to many other occultation resources. Thanks for your attention.
Okay, thank you very much, David. Okay, and our final speaker for the session is Dr. Javier Roa, who is a navigation engineer at NASA's Jet Propulsion Laboratory / Caltech. Okay, take it away, Javier.
Thank you, Stephen. Can you hear me okay?
Yes, we can hear you.
Great, so it's great to be part of this session. Next slide, please. Let me start by discussing what impact monitoring is and why it is important to develop a new method, because we already have the Sentry and Clomon systems in place, and they have been quite successful in the past. So it's really important to explain why we need to revisit this problem. We could start by defining impact monitoring as identifying and characterizing all the virtual impactors that are compatible with an asteroid's orbit uncertainty distribution. So this concept of virtual impactor, a VI, was proposed by Andrea Milani some 20 years ago, and it can be defined intuitively when looking at parameter space. So this diagram at the bottom of the slide depicts the uncertainty distribution in parameter space, with the gray ellipse representing the covariance ellipsoid. And physically, what this means is that the true orbit of the asteroid may be found in this region with a certain confidence level. So the VIs, the virtual impactors, are these regions in green, and they are subregions of the uncertainty distribution that actually lead to impacts. So what this means is that if the true orbit of the asteroid falls inside one of these regions, it means that the orbit will impact the Earth at a future date. There are multiple challenges specific to impact monitoring, and here I am listing some of the most relevant ones. So first of all, there are usually many VIs, and sometimes they are not clearly distinct. So separating them can be quite challenging. Also, the impact probabilities we are dealing with are typically very small, down to the 10 to minus 7, 10 to minus 8 level, and that complicates the characterization process quite a bit. Also, the set of parameters defining the orbit of the asteroid might be pretty complex, including, for example, non-gravitational parameters to model different sources of perturbations, and this needs to be handled automatically by the system. And also, since we are dealing with the entire NEA population, we will always encounter pathological cases, such as Earth-like orbits, strong nonlinear effects like close encounters, and so on. So in terms of the methods available, Monte Carlo simulation is possibly the simplest and most robust method for estimating impact probabilities. And it is actually a great solution for solving what I'm listing here as the third and fourth challenges, because it is really completely transparent to a set of parameters defining the orbit, and it can also handle strong nonlinearities very well. However, the problem with Monte Carlo simulation is that you don't really get any insights into the dynamics, and it cannot really be used for separating the VIs when the dynamics become complex. And also, when estimating very small probabilities, this becomes an issue from a computational perspective, just because of the number of samples that you need to propagate in the future. So because of the limitations of Monte Carlo simulation, Andrea Milani again proposed the concept of the line of variations, which is really a very elegant concept, which essentially consists in identifying a privileged direction in parameter space so that you can run a Monte Carlo simulation along this line, this one-dimensional space, instead of over the entire ND space of parameters. So with this method, it is fairly easy to separate the VIs and also to compute very small probabilities very efficiently. But the problem with the LOV is that when defining this kind of privileged direction, one usually needs to make some assumptions related, for example, to how the parameters relate to each other And that really complicates the treatment of arbitrary parameters like, again, non-gravitational effects in a systematic way. The same applies to strong pathological cases, because those guys can really break the underlying assumptions of the definition of this one-dimensional space. So the number of cases requiring manual intervention has been increasing, and it will continue to increase in the future, especially with all the new surveys becoming operational and the expected increase in the rate of new discoveries. So this really calls at this moment for a new and more robust system, and this is what we've been working on for a couple of years now. Next slide, please. The method we have developed is based on incorporating what we call the pseudo-observation, pseudo-impact observation, to the orbit determination process. And this impact pseudo-observation is a mechanism for constraining an orbit determination filter by forcing it to converge to an impact solution, as long as it is compatible with the observational data that we have. So the way to do this is that the residuals of this pseudo-observation are just the B-plane coordinates at a certain time of close approach. So if you drive these residuals to 0, you're actually getting to an impact solution. So the diagram on the left starts by depicting how the usual orbit determination pipeline would work, where you feed a set of observations to the orbit determination filter to produce a nominal orbit and the uncertainty. So what we are doing here is we are incorporating this impact pseudo-observation to the set of available observations, so that when passing them through the filter, the solution that we get is an impacting solution, again, as long as it's compatible with the observations. We also get a measure of the uncertainty of the fit that models the extent of the virtual impactor in parameter space. One of the main advantages of this method is that we introduce no simplifying assumptions about the dynamics or about how the parameters relate to each other. And another nicety is that with this method, we can reuse a significant part of our operational orbit determination pipeline to develop this impact monitoring system. Next slide, please. So here's an example of how the method works in practice. These plots represent the scale B-plane for an example close approach. In particular, this is the 2080 close approach of asteroid 2000 SB45. And the filter starts from what is marked here as iteration 0, and then moves along the weak direction towards the center of the Earth. That is the circle that you can see on the plot. And the string of gray dots are Monte Carlo samples that show how the uncertain distribution maps to the B-plane. So with the line of variation method, you would sample a number of points along this line and then interpolate to find impacts. But with the proposed method, we no longer need this one-dimensional search, because the orbit determination filter naturally marches towards an impact as long as the uncertainty region is really compatible with impacts. Because the data constrains this orthogonal direction marked in blue, so the filter cannot really move out in that direction because the data would not allow that. And on the right, it's just a zoom-in view of the Earth's cross-section for the same case. The blue ellipse shows how the uncertainty of the impact solution maps to the B-plane and spans the core of the Earth, and that's by design. That's the control we have over the pseudo-impact observation. Next slide, please. So this new method, this new algorithm, has been implemented into a new impact monitoring system, a JPL, that we call Sentry2. This is an older version of the slides. The new system is called Sentry2. Okay. And Sentry2 first runs an initial Monte Carlo exploration to identify all the possible close approaches, and then runs the orbit determination filter from selected initial guesses, incorporating this impact pseudo observation. So it tries to converge to an impacting solution. And then once we find the VIs, the third step is to characterize them by estimating the impact probability. And for that, we use importance sampling to get a minimum variance estimate. The system has already been running for a few months, so we have collected quite a bit of statistics about its performance compared to the original Sentry system. And Sentry2 successfully handles non-gravitational parameters in a systematic way, which was one of our main goals. And it's also more robust than the original system when facing pathological cases. That was other of our main goals. In terms of runtime, it's quite comparable to Sentry and orders of magnitude faster than direct Monte Carlo simulation, as you can see in these numbers here. And finally, one good advantage of this method is that the orbit determination filter provides the uncertainty of the impacting solution. So that's very useful for conducting negative observation campaigns to rule out the VIs. And that's all I have, and I'll be happy to ask any questions in the Q&A round. Thank you.
Okay, thank you very much, Javier. Okay, that concludes talks for this session. We'll have the question and answer session for the remaining time, and we'll run it the way we ran the session this morning. We'll divide the time up into segments for each one of the speakers. Can I just remind the panelists, if they have questions, to also put them into the chat area as well, so that people can follow in the forthcoming days. So with that, I will hand over to Marina for the first set of questions.
Okay, so we have the first one is for Joe Maciero, and since I don't see any particular questions posted, I'm going to just ask one myself. So I know that you can do 8 to 10 observations per day with NEOWISE, and obviously you have enough to start estimating periods based on thermal data. It's very sparse, but you've been observing for many years, and I'm just curious how that effort is going.
Yeah, so the biggest problem with this is that our return time is between 94 minutes and 3 hours between data points on the light curve. So for anything with a shorter rotation period than that, you have a big problem with aliasing. For longer rotation periods, we do see a lot of long period observations and a lot of changes. So Sarah Sonnet has been leading some work on looking at the Jovian Trojans, for example, to look for binarity. On the near-Earth object side, since they rotate much faster, it can be harder, and you need a lot more observations to be able to back out a period.
Okay, thank you. So Stephen has the next one for Maxime, I guess.
Yes, thanks, Marina. So there are several questions for Maxime. We have a question from Jan Grunsman. Would you see some use in brackets resolved, close brackets, polarimetric observations of asteroid in rendezvous or flyby missions?
Sure, yeah, that will be very interesting. Actually, we currently lack any polarimeter on any spacecraft that visited an asteroid. And so right now it's really difficult for us to calibrate the observations that we are getting from the ground to the truth on the surface of an asteroid. So having some spacecraft with a polarimeter will really help. And also we are observing some asteroids like Phaeton, for example, that shows variation of the polarimetry as a function of the rotational phase. So that means that the polarimetric properties on the surface of these asteroids vary over the surface. So they are heterogeneous. And right now, we don't know what is triggering this variation. Is it albedo? Is it regolith surface properties like grain size or something else? So having spacecraft observations will really help calibrating these observations.
Okay, thank you, Maxime. There's another question for you from Paulo Tanga. Which telescope size do you need to have a good enough signal to noise and polarimetry for 2021 PDC, which is quite faint for this technique?
Yeah, PDC is quite faint, but actually there is like a polarimeter which is forced to on the VLT, and with the VLT and like a long enough exposure time, we might be able to get like enough signal to see if it's a high polarization or low polarization. Because if it's a high polarization, like if you got a polarization of 50%, you can get like 50% plus or minus 25%. You will still know that it's a high polarization. If you observe like closer to 0, 1%, you will still have like a good, nice information about the albedo determination. That will not be as precise as I show you on the plot, but it will still be very useful.
Okay, thanks. I have a quick question, Maxime. You mentioned that you could determine the albedo from a single phase angle polarization measurement as long as it's greater than 40 degrees. What would the uncertainty in that be?
Right now, it's quite hard to assess the uncertainty because we are lacking enough polarimetric observations with good albedo determinations. So if we can have a survey that can obtain reliable polarimetric observations for asteroids for which we have reliable albedo, we should be able to calibrate this phase polarization curve. And of course, like getting 2 measurements will like greatly decrease the uncertainty, or having another information such as the taxonomy would also decrease it. But we really need like more observations in order to get this assessment. But I would say like I show in the plot between like 20% on the albedo.
Okay, thanks. And well, one other quick question, although it may require a long answer, so you may need to be brief. And this is from Sean Marshall. Why is there a relation between albedo and degree of polarization? And what is the physical reason for it?
This is mostly due to the fact that if you've got like a very bright surface, upon scattering, there will be more light that will be scattered. So there is a higher chance of multiple scattering. And when you've got like multiple scattering before like reaching the observer, you will randomize the scattering plane. So that will result in more unpolarized light that you're observing. If it's very faint, it will be mostly single scattering.
Okay. Thank you very much for that. It was very brief. With that, I will hand back over to Marina.
Okay, so we still have several questions for Vishnu. So one is from Marco Fanucci, saying that I saw that since this object has been confirmed to be a space debris, the MPC removed it from its database. Where is the data of orbit determination stored now? Do you know?
I think you can still get it out of Horizons. So I put the object number. Maybe I think might be a question for Paul or somebody else. The astrometry itself, I don't know where MPC puts it. You used to be able to pull it out of by searching 2020 SO, but the object itself is available on Horizons. You just have to go in the satellites. No, I think it's spacecraft, and then you put in this number that is there in the chat room. You should be able to pull it.
And we have another question from graduate student Lord Dover from University of Kent. Is there a dedicated list of defunct rocket bodies or other large debris lost objects?
Yeah, I think unfortunately not the ones in heliocentric orbit. You know, there's kind of an informal list that Bill Gray maintains of whatever we detect. But for in Earth orbit, I think we have a good catalog. It's maintained by the Space Force. So just go to space-track.org and you can download the whole catalog of all the objects, and then you can sort it by rocket body. It's one of the keywords they use.
So, and finally, question from me. I know that you did some light curve observations, so period measurements, kind of elongation. Is it consistent with rocket body?
Yeah, I think so. So I mean, I don't know if you can show slides now, but the second backup slide has a nice light curve off 2020 SO. If people can download it, they can see it. I think Peter Britfis did the observations on the inbound, and we did the observation on the outbound. The periods match within about 0.4 of a second. So the period is about 9.6 seconds roughly. So that's useful.
And the amplitude?
Yeah, the amplitude is, it's pretty high. So it's about, I think somewhere around 2.5, 3 magnitudes at least, so it's a very elongated object. And of course, I think there was some bistatic radar observations also that showed the elongated shape.
Okay, thank you. Well, I think we are going to be moving on to the next set of questions for the next speaker. So yes, Stephen, take it away.
Yeah, so these are questions for David. I have one very quick question maybe you can help us with, David. So on I think it's page or slide 8 of your talk, you mentioned about the A2 term for Phaethon. And you mentioned that it's, the difficulty in determining that is the mass loss rate due to strong thermal heating near perihelion being the main driver. Could you comment on that in a bit more detail?
Not too much. That's just I asked David of Fernotia about the A2 of Phaethon. But Phaethon is well known to be shedding mass from the Geminids meteors we see each December, and also the dust trail that was directly imaged by the Parker Solar Probe. So that's probably the main driver for Phaethon's A2, I believe, more than the Yarkovsky effect. But I don't know that anyone has actually done a calculation of one versus the other effect. That would be an interesting paper for someone to write, since we have a good determination now of its A2. So that's about all I can say about it.
Okay, thank you very much. Okay, I will hand it back to Marina for questions for Javier.
Actually, I have one last question for David. So on March, when was it? On that occultation was on March 5th, when presumably you ended up with a long axis of Apophis. I missed it. What's the latest estimates for dimensions? Did you measure dimensions during occultation?
Yes, we did, but they were very crude because we're right at the limit of our video resolution, of 60th of a second. So we, if you look in our skyplane plots, we give the solutions. They're all around 400 meters or so. We think that they are actually showing larger than, because we're detecting the Fresnel diffraction pattern, the lower part of the Fresnel diffraction pattern. So I think our occultation results give a diameter that's too large. Of course, we believe the radar diameter must be the most accurate. And we look forward to fitting your shape models, at the different aspects for each of the occultations to our what we've got at the moment. One advantage, of course, of the few systems that we have that can record faster than video rate, like Kaiju Troth using a QHY camera with the 20-inch telescope, and of course Plango Tango with that beautiful results with a portable 1 meter scope that they have at Observatory de la Côte d'Azur. Those will actually give measurements that you can really use relative to the the radar models and so forth. It'll be very good. But we have just a couple of those stations, and most of it with video, though it's pretty crude in what we do. The occultations don't really give very good shape information for such small objects, but they do give nice, accurate astrometric points. And as I said, with the bigger scopes, we can start getting better shape information. So.
Okay, well, thank you very much, David. And finally, for our last speaker, for Javier, I guess I didn't see any questions in chat. Maybe they'll come up later, but I have 2 questions. First one is, can you say a little bit more about those anomalous cases like minimums 2020 CD3 and how this new method is handling that? And also I'm curious if Sentry 2 was actually used during this PDCO exercise on Apophis.
So starting with 2020 CD3, we actually tested the method with this case to see how it worked, and it worked fine. It was able to split the different close approaches even when it was temporarily captured. So it was just a matter of, it took longer. So it was really a matter of like letting the program run. But yeah, it was able, first of all, with the initial exploration, to detect the close approaches, and then the filter starts converging systematically to the different impacts. And we were getting like impacts almost with a separation of a week or so when it was temporarily captured. So yeah, it was successful in that regard. And then what was the second part of the question?
Did you apply the Sentry 2 for the PDCO exercise on Apophis, when they started discovering it from scratch?
Yeah, and we used it in the end to do the final rule out when they had the final updated radar measurements and so on. So yeah, we did some study with that, mostly we're interested in seeing how you can handle the Yarkovsky effect with the method, because it's introducing this non-gravitational parameter was one of the, of course, the main motivations for this project. So yeah, that was one of the test cases that we played with, and it was just proving that that the method could handle that fine. So
Okay.
I do see one question here on the chat from Jorge Perez.
Well, go ahead.
It's yeah, so he's asking what are the lowest probability impact events that you can detect with the pseudo observation technique, and there's really no limit to how low you can go with the technique itself. It's really the initial exploration what limits the completeness of the system. So when you know nothing about the asteroid, you just run like an initial Monte Carlo exploration with, say, 10,000 samples or so, and that tells you where the close approaches are. And then from those initial guesses, you try to converge to an impact. So it's really that initial exploration what drives the how low you go with the impact probability, not really the pseudo observation technique itself. And then regarding the question about the pathological cases in which you would have to fall back to Monte Carlo, so we didn't really encounter any case where the method didn't work, but we observed that when you have very strong nonlinear effects, like very close encounters,
Javier,
it becomes a numerical.
It's,
Oh,
I'm
okay.
sorry to interrupt you. It's 11:00. I would like, you know, we will need to sign off. So Stephen, would you like to close the session, please?
Yes, thank you everyone for the great talks and for staying on time. I just want